Day of the Polinsar workshop, second day on biomass. We'll have this morning two sessions with the first results of biomass, continuation of the session of yesterday. We'll be co-chairing with Dean. And the first presenter is Roman Guliev. He will present the first assessment of the interferometric performance of biomass and for forest state retrieval.
So, good morning everyone, and thank you for joining 9 in the morning after party. So my presentation has two main aspects. First, I wanted to speak towards the product development of forest height, but second, I wanted to speak about the science of forest height estimation and interferometric performance. It's the first P-band satellite in space, and therefore, there's a lot to learn. Okay, about the product, so there was already some releases of heights. Our aim, our goal is actually to estimate height at 4-hectare resolution. But before speaking about the product, I wanted to speak about the science. So, and scientists, how science works, scientists build hypotheses and they test this hypothesis or assumption. And since it's the first satellite of P-band, we had our assumptions and we want to test it on real data. First assumption is a simple one. Larger baselines make larger decorrelation. This is all known, but we want to test it. And let's test it. So we take first baseline. It's a spatial separation of the two different acquisitions of biomass. And we can build so-called coherence. Just it shows how the two measurements correlate. That's the one baseline. Now we move satellites more further from each other. Second baseline, you see that the image becomes darker, and the third one even darker. So it means that our assumption about larger baselines make larger decorrelation is correct. That was a simple one. The second one is whether decorrelation is purely geometric. So what I showed is geometric decorrelation. Yes, we move satellite from one another. Geometry causes this kind of pattern. So to test this, we now take the same geometry, 3 different acquisitions with same baseline, and we build the same measurement, the same coherence. But you see that still, if I take the same baseline but at different time, I see different patterns. It means that there is something else except for geometry. So coherence is not equal geometric decorrelation. Okay. You ask whether it's ionosphere. I show you one example of ionosphere. Actually, I showed you coherence images after correction for ionosphere. That's the worst case of this stack of 6 images. So you see, especially on this ascending orbit, a very difficult pattern of ionosphere. On a descending orbit, it looks like this. But you can apply correction. So we need, in the case of biomass, to have fine co-registration. So after correcting for a blockwise shift correction, especially in azimuth, you can get rid of the effect on the coherence of the ionosphere. Okay, the third assumption is that geometric decorrelation can be split in two different orthogonal directions. One in range, another one is in cross range or in volume. And also here we say that already larger forests make larger volume decorrelation. We can test this assumption. In other words, we kind of factorize the coherence into different components. Okay, how to test that? This one, a more difficult one. So you see that here, coherence, I plot against the reference height, JEDI, scaled with the baseline. So it varies from 0 to 2 pi, and I plot my data, my coherence, against reference measurement, and you see the specific pattern of coherence. So coherence decreases with the increasing baseline and forest height. And I can do it for other baselines. So this is the smaller baseline, medium, and larger baseline. And you see this kind of pattern. So first, what you see that the ground is not at 1. This actually the effect of the range decorrelation. As I said, we can split 2 different directions of decorrelation, and one in range, one cross range. What you see on the ground is the range decorrelation. How to test it? We can also check the theory. If you plot the decorrelation on the ground for different baselines, you will get a linear trend, and that's in line with the theory. We know that range decorrelation should scale linearly with the baseline. And you also can estimate the critical baseline from this plot. This will be a critical baseline estimated from data, but you can also, of course, use the theory and estimate this critical baseline. You can correct for this range decorrelation, and your coherence then will be kind of volumetric. So yes, they can then move these histograms here by compensating for range decorrelation, and you will get volume decorrelation. So you see that the volume decorrelation, it correlates with the forest height, and that we can already use to estimate forest height. So this assumption was correct. So we can use this already to apply very simple Hamburg type of inversion. You can just take this coherence and correlate it with the forest height, and you will get the result. But we want to do something more consistent, and we want to account for temporal decorrelation first before inverting the height. So how do we do that? First, we need to understand how temporal decorrelation looks like. And often the assumption about temporal decorrelation is it's only real. Again, we can test this hypothesis whether temporal decorrelation is only real or not, and we can take the phase. So if this component is real, and I can take the phase of coherence, and it will be equal to the phase of the geometric decorrelation, because temporal decorrelation is real. Okay, let's test this one. For this, we need phases. So I take the phases, which are now taken over the ground, and I take them for different baselines. So this is one baseline, and it's the same baseline, but taken at different dates. So these are the phases over the ground, and you see, again, that the pattern of the phases changing depending on the date. It means that temporal decorrelation is not just a real component, because otherwise this phase would be consistent and constant for different dates. You can also see it from the triplets, as Kostas was showing yesterday. But here, for me, it means that I cannot use the simple real decorrelation, temporal decorrelation model. Okay, so this assumption was wrong. Now I'll go to the dual baseline approach. So since I need to account for temporal decorrelation, one way to do that is to say that temporal decorrelation is not a real component which which can be factorized with just coherence measurement, but it only affects the volume, and we have a ground to volume component here. And we do the dual baseline approach, so it means that we invert the height from different two baselines. We have 2 complex measurements, so 4 parameters, 4 measurements, and we have here 4 unknowns: ground to volume ratio, temporal decorrelation, and forest height. Okay. So how our data look like for dual baseline approach? So this is example of dual baseline coherence, baseline 1. So this is the baseline of 30% of critical baseline. The coherence, the phase, which will be used for inversion. And first, before we do the inversion, we need to understand whether our data, whether our measurements correlate with the reference. we do it here. The coherence I already showed, it was correlating with the reference. But the phase, you see also, it kind of correlates. It's also not bad. Okay, we take the second baseline. The second baseline is larger. It's 45% of the critical. You see coherence and phase. So the larger baseline decorrelate more, so you see coherence smaller. The phase is also rising because they have larger baseline. Okay. Okay, so these are basically the 4 measurements which we use for inversion. 1, 2, 3, 4. And we invert the forest height from them, and we invert 4 parameters. 1 forest height, ground to volume ratio, and 2 temporal decorrelations. And we apply pretty much standard algorithm without doing anything, and we get some correlation. So it's actually the worst case scenario. So it just apply algorithm as it is, without fitting or without doing any magic. Okay, so of course we test this on other test sites, one in Amazon and in Indonesia. And you also get your correlations here, so you see it here. It's a bit more deviation, more variance for Sumatra because of the larger slopes here. And so a few last things I wanted to mention is that ESA and DLR have history of AFRISA campaigns, and the most recent one was taking place last year in November. This is the team. And the most important test sites were here, Lope, Ipasa, and Monda. And the idea was to actually acquire the airborne data which align with the biomass ascending and descending orbits. This is the example of one acquisition here of FSAR, and this you see that aligned. That's what we normally have, but this time, for me at least, the highlight was that we have also the long strip of FSAR aligned with biomass pass, and it's a very nice reference, just comparison or reference. So you see it doesn't here, it's not crossing the orbit here because it was COM4, but if you take the COM5, then you see that they're aligned. Okay, if you didn't believe me about the correlation of the forest height derived from biomass with the JEDA, you can also compare it with ELVIS, airborne. So this is the airborne LiDAR here. You can see that the patterns which LiDAR shows pretty much similar to the one from biomass. And if you don't want to wait until you have all the biomass passes, you can start filling in the gaps with TandemX and also apply some fusion algorithms. That's it from my side. Thank you for your attention.
Thank you. Is there any question? We have a little bit of time, so don't be shy. Not that early in the morning. Klaus.
Now, as we have collected the first stack, can you see anything in terms of baselines? What would be the preferred choice of baselines for you, if you can choose? Are we fine with the settings that we have now, or would you suggest any changes?
So for the current phase, we have a bit shorter baselines, shorter progression. So in the interferometric phase, there will be a bit larger step. And that is good because I tested it with their current progression, 15%, 30%, it was a little bit small. But for the interferometric phase, it's already planned to be slightly bigger. That is good. So I think the current setting is okay, but I would still take some time to actually do further analysis also for other regions, not just, let's say, this one.
Is there any other question?
Okay. Thank you a lot, Roman. I have just a question about the performance. Could you show just take the coherent and relate it to the forest high, and then you using the dual baseline? Do you recognize do you quantity the performance? How is improvement?
Performance of dual baseline with respect to single baseline inversion.
Right, from single to
So for
dual.
the single baseline inversion, it would be difficult to do because we have temporal decorrelation. Of course, you can use polarimetry here and and try to use different polarization with same temporal decorrelation for different polarization. But I think that the more consistent approach now is to use the dual baseline or try to optimize coherence based on, let's say, free acquisitions.
But with respect to single baseline, how many percent we can improve?
With respect to single baseline,
Yeah.
I would say you can actually make the similar performance also from single baseline. The problem is that you have to fix parameters when you do single baseline inversion, and it's not good, let's say, from the perspective of the science and consistency of the inversion. You can do that. You can try to fit parameters, take them from just experience or whatever, but I would stick to their either dual baseline or some kind of optimization.
Okay, thank you, thank you. Is there any question?
In the display where you have the airborne campaign and satellite data, we can see there's a kind of difference. Is it just the display, or you see some differences? And
Airborne here.
yes, on the airborne.
Yes. So I didn't mention that. I intentionally not. So we don't have forest height now derived from airborne because it's
Okay.
just a polarimetric image.
It's just a footprint.
So everything forest height except for FSAR. So and Mark and the DLR team, they are currently processing interferometry here. This is just one image here.
Okay.
Yeah.
The LiDAR is
And I didn't want to compare the radiometry and their polarimetry of satellite and the airborne because it's still a bigger report to be done about it.
okay. Thank you.
Okay, okay, okay. Thank you a lot, Roman. Thank you.
Thank you.
Okay. Okay. So we want to welcome the second. We want to welcome the second talk about the first demonstration of forest structure monitoring with early B-band biomass Polinsar data. Welcome, Nuela Romero Berg, please. Okay.
Thank you. Thank you for the presentation. So it's good that Roman was before me because now we're going to see how we do use the satellite for the first time in space with fully polarimetric capabilities and interferometric capabilities, and how we are going to use also single baseline approaches. To get what? In this case, what we want is not to estimate an absolute value of height. We want to get insights into the forest structure, and ultimately, what can we say with both polarimetry and interferometry about the changes in the structure. So we've seen already this week many times this scene. We have seen it upside down and all the way around. This is a scene that starts in Gabon. It crosses several countries. It's very large. You see as the one that Roman was showing now with the different campaigns. We also go through Congo, the Republic Democratic of Congo, and we end up in the frontier with Angola in the Congo River up there. So now if we take this scene, what is polarimetry telling us? We take a crop around the river. We already saw in yesterday's presentation with Costas that we have very strong dynamics in the scatterers, and we get our Pauli RGBs of this crop area around the Congo River. And we have our stack of 6 images going from the 7th of October to the 22nd of October. This belongs to COM4 data. We still have some baselines here. And we have a very rich environment with polarimetry. We see all the areas covered by the water around the river, and then we see in these darker colors the surfaces, and then we start to have some vegetation, not very high or tall vegetation in this area. We start to see the green colors. This is fine, but if we compare from the 7th of October to the 22nd of October, we barely see any contrast or any changes from the beginning to the end of the stack. This is okay, it's just been a couple of days. Now, we also have interferometric information. Here we can plot the HH coherence. Remember that this acquisition from the 19 was heavily affected by slow ionosphere effects, but you see we are getting the crop and we're still fine. And we start to see the changes, where we start to see the correlation in these 3 days baselines around the river especially. Why? This is the water moving. And this is something that we need to keep in mind, take into consideration when we are going to use interferograms, we are going to deal with this temporal decorrelation, which is no longer a scalar. And now, the problem with interferometry, if you like the problem, but what happens here is that these strong dynamics components, we cannot explain it by just looking at interferometry. So what we want to do now is to combine the information given by polarimetry and interferometry and try to explain the dynamics that we do see with interferometry with what polarimetry is giving us. How are we going to do that? We go to our classical two-layer model. We don't need to get too deep into the equations, but interferometry gives us sensitivity to the vertical component, to structure, to height. So we can distinguish different scatterers located at different scattering phase center heights. So we can model this very simply if we're looking at a forest with a two-layer model. We have an extended layer, which is the volume, which is located on top of an impenetrable ground surface at ground level. The ground is modeled as a Dirac delta, and the extended layer, we have it described as with the vertical reflectivity profile. This is the model, and what we measure is the normalized Fourier transform of this. What we measure is what we have on the right-hand side. We have the component of the ground in the exponential. This is the topographic phase, and then we have the volume-only coherence reflecting how we have described the vertical reflectivity profile. And then we have the ground-to-volume ratio, how much power is coming from our response from the ground versus the power coming from the volume. And this is the only component that is dependent on the polarization. We will also keep this in mind. Now we also have polarimetry. Polarimetry is giving us sensitivity to the orientation, the shape, the dielectrics of the scatters, but is doing all this in a flat two-dimensional plane. We lose the structure information. Can we combine those to say something about different scatterers at different heights? And this is the link that we make here. So we can relate the polarimetric information as a function of the interferometric coherences in the equation that we have there. Now we take this link and we exploit it to do what? We have a complex scene, many scatterers, we have a high entropy scenario, and what we want is to simplify it. So we make a ground-to-volume separation in order to get simpler scattering components that we can analyze by means of polarimetry. We do this in this case single baseline. We stay relative to our system. We know we're dealing with temporal decorrelation, and we can do this by following a very physical criteria. We can use polarization. We optimize polarization to get the scattering phase centers that are closest to the ground and that are farthest away from the ground and closest to the top of the canopy. If we do this, we come from the full polarimetric signature now to having two simpler components that we can further analyze, the ground on the left and the volume on the right. We stay on analyzing the ground. Why? Because it shows us this strong dynamic behavior of the scatterers. It appears on the ground. And we also need to consider, this is why I'm plotting here the forest-non-forest mask, that of course we are separating, and we are doing this assuming that we have a volume and that we have different scatterers located at different phase center heights. Of course, if we're looking at surfaces, we are separating nothing, so we get the same signature at the ground or at the volume. We stay on the ground, and we can further analyze this. We have already used interferometry, we have simplified our signature, and we use now polarimetry to say something more about the scatterers and the structure. What can we do with the ground? We can go back to our classic polarimetric decompositions. This is a very simplified one from using Bragg and Fresnel components. This is assuming that the ground, we can divide it into surface scattering and dihedral scattering, where we have trunks and we have forest. We get the scattering coefficients, we build our scattering matrix, and we assume that our model ground, ideally, is a contribution from this surface scattering, from the Bragg model and the Fresnel component. And it's a mixture between them. Now we analyze the polarimetric signature of this modeled ground component, and we do it by looking at the full polarization states, at the whole polarimetric spectrum, not only at the optimized ones. So we take the projection vector here, and we just perform a normal distribution, and we project it over the polarimetric signature, the T, which is normalized by the power, because we want to focus on the type of scattering mechanisms. So we go through alpha and beta. Alpha goes from 0, blue, this is surface type of scattering mechanism, to red, which would be dihedral type of scattering mechanism. And in the vertical component, we have the line of sight rotation with the beta angle. In principle, what we want to have here is at pixel level, we want to have a two-dimensional histogram, a two-dimensional representation of the polarimetric signature, where if we are looking at symmetric scatterers, it depends a little bit, but the line of sight in the vertical axis should remain relatively constant, and this would allow us a better representation of how is the scattering mechanisms. Do we get surfaces? Do we get more contribution coming from the dihedral moving around polarization? We do this, and we would have, or we would go from pure surface scattering on the left, modeled Bragg component, to different mixture, different ratios, until arriving to the other pure dihedral scattering. Of course, this is our ideal model. Now we deal with real data. We do this at pixel level. By doing this for each pixel of the image, we can just come to what contributions we have at image level of surface versus dihedral by projecting our real ground signature that we have already separated onto the model one. We come back to our problem. We wanted to use both polarimetry and interferometry, and now we are at a point in which we have already separated our signature from the ground, and we can already analyze it with polarimetry. So this is what we get. Now what we have in the bottom row is the polarimetry of the ground component only, and we start to see the reflection of the dynamics from the beginning of the stack until the end of the stack. We see the changes of the flooded area around the river. Are with these funky colors some ghost? Can we explain what this is? And yes, if we go to see what was happening here, by introducing polarimetry and optimizing the polarization states and separating the ground from the volume, we can compare now. What we see there is actually the tides, is the water table moving up and down. I know this is very small, but basically if we take the days of the interferometric acquisitions and we compare them, we see that this is the plus minus 1.5 meter difference in the water. And now we want to quantify this. So this is a visual inspection. How can we move from this to something more quantitative, to some numbers? And then we can use for that our mixture ratio. And focusing on that crop, you see how below 50% in blue, we would see surfaces, and above those 50%, we see the dihedrals. And in the first acquisition, the 7th and the 10th, we had high tide in both. Then we go to the acquisition in the middle, it was low, so the coherence comes back, but we cannot explain it why unless we look at the polarimetry, and then the tides come back up again in the last interferogram. And that is exactly this 1 meter change in the water level height. It's exactly what we are seeing there. We can further analyze this at pixel level with the full polarimetric signature around all the polarization states. We can take one area, one point, and we can go to its interferometric and polarimetric signatures. I always like to plot the coherence region because it shows us how much information we're missing if we're looking at just a single polarization, but how rich we have, or how much information we have when we include the polarimetric information. And we see that indeed our model even if very simple, it's consistent. We go from something that has a dominant dihedral contribution in the first interferometric pair, from a 70% was here, we come down to a 20% and we come back up to an 80% dihedral contribution when the water level is high. This, we cannot explain it by just looking at the coherence regions or at interferometry, because we have different decorrelations coming from different sources. If we compare this to the full polarimetric signature, where we don't have the ability to separate in height these scattering phase centers, we lose this contrast. So this contrast, we can only achieve it when we separate and we analyze the full polarimetric spectrum. This is not just only a particular case of this image. We have analyzed different ones. So I was just including here another example, just to see. This one was also shown yesterday. This is in Namibia, and this is another river. We also have the comparison with the delta. And you see how we move from almost no contrast in the first row, only with polarimetry, to a lot of decorrelation that we cannot fully explain only with interferometry, to something that relates to this water level moving up and down. So we expect, this is just comparison of the mean scattering alpha. I didn't say it before, but again, it's full polarimetry versus what we can do when we separate and we go to the ratios. So we expect to be able to explain these strong dynamic components at p-band that were not observed before, and we didn't know exactly how this was going to play out. And we can explain it very well using both interferometry and polarimetry, and exploiting the best that both techniques give us. And like this, we start to characterize not only forest structure, but also its changes. And in this case, we're speaking about very small changes. We're not speaking about big deforestation. So we do expect to be able to say something more about it. So this is just the beginning. And this is where I would like to end today here my presentation. Thank you very much.
Thank you very much, Noela. On time and very good result.
Thank you.
Any question? Yeah. So.
Hi there. Thanks, nice talk. If I understood that correctly, that almost all the dynamics you're seeing are coming from the ground return or double bounced, but the actual biomass inversion is based on ground cancel data. So is the implication of this that actually that is almost unaffected by these dynamics that you're seeing here? In other words, do you see any changes in the volume term, which is the one that would really screw things up?
The volume, so far, in what we have seen here, stays very homogeneous and very constant, and much more similar to the full polarimetric signature. If you want to focus on the volume, if you want to focus on absolute forest height estimation, if you want to focus on biomass, maybe that's exactly what you want. But for us here, the point was to get as clean as possible something coming from the ground when we think in terms of separating the electrics versus structural changes. This was the main challenge for us, because in polarimetry you are sensitive to everything, but all this polarimetric change analysis, mostly you are driven by radiometric change. So we wanted to be driven by structural change instead. So we want to get this surface dihedral. And we see the strong dynamics in the ground. We don't see them in the volume. Yeah.
Oh, you go.
Okay, thank you very much. Yeah, very interesting. And I'm quite involved in inundation monitoring with ALOS. So it's really interesting to see these time series of the P-band data. And just thinking, given the fact that the kind of water table has such an effect on what you see in the biomass data, and also, I mean, here, this is a kind of during the con phase. I mean, when you have like 3 days baseline, you can really follow the kind of the patterns of whether it's like inundation in the Amazon or it's like tidal changes like here in Gabon. So I was just kind of wondering, operational scenario, you will only get a very kind of short time window sampling kind of when you're passing over. I mean, the observation strategy for biomass is not designed for mapping kind of rapid phenomena like inundation. But the fact is, in your imagery, you will have a certain inundation state that you will have to take into account when you do the inversions and everything. So maybe a question to Klaus as well for the biomass or for the geotrees sites, whether those sites that cross over some water bodies, if you're thinking of including like gauge data as well as part of the, because I mean, it will affect what you see in the imagery, right? So yeah, so it's more like a comment. It's not really a question. It's more a comment and reflection of what we're seeing here, which I think is really exciting. And maybe a secondary objective after 7 years to have a look at more kind of dynamic kind of water table kind of monitoring. Yeah, so sorry.
Yeah, no, everything good. No, it was, for us, it's what we can say is about structural change with 1 month or 3 months is not much.
Yeah.
And I thought this was for us very interesting because it's another feature, it's another aspect that you need to consider, but at the same time, you can use in the positive way.
Yeah, I mean, maybe the question is here, I mean, can you say, disregard from the fact, I mean, some areas then, I mean, in your observation plan, you will have acquired at a certain inundation stage. So can you kind of disregard that when you're doing the biomass inversions? Because, I mean, you actually, that is a parameter that you actually don't want to measure in the case of forest biomass, right? Yeah. So can you actually, is it disturbing or is it just a side effect that you can invert, you can do your biomass inversions regardless of whether it's inundated or not anyway? Yeah.
I think you won't have that effect in the volume component, a bit related to what Sean was asking, because they do this ground cancellation and you don't focus on river basins.
Yeah.
If you look at the changes over this full polarimetric signature, or you look at the changes of the volume component, you don't see them.
Okay.
Or if you see the correlation, it will come down and then come up again. So you average that, or you don't break that down. Okay. Yeah.
Thank you.
Yeah, thank you.
Thanks, Nalia. So I have a quick question. Have you considered modeling the double bounce between the canopy and the ground? Because I see that modeled very little. I think that has a huge impact.
What do you mean modeling the double bounce exactly?
Oh yeah, the interaction between the ground and the canopy. Not between the ground and the trunks, but between the ground and the canopy.
Okay. I mean, for now, we were using the simplest model of the ground, dihedral versus plus surfaces, but just to see first what kind of sensitivity you have. If you start there and you don't see anything, then you don't continue. Versus ground versus canopy, I'm not sure exactly if you mean going farther down into some more complex model there. Yeah, this is something that we would do. Once we start from the simple thing, and you see you are sensitive to that, then you can move into something more elaborate, maybe.
That part of the modeling, I think, is required to really understand the interactions at P-band. We've been neglecting that part for a very long time. I think that part is important.
For the moment, to the forest scenes that we were observing now, there was not much changing. So that's why we focused on these ones.
Okay.
You're welcome.
Thank you a lot.
Thank you.
Yeah, interesting. Yeah. Thank you.
The next talk will be provided by Mikhail Orbazayev from GFZ, and he will show us some interesting results from biomass satellite data acquired during the commissioning phase of a Brazilian forest.
Hello everyone from my side. My name is Mikhail Orbazayev. I'm a project scientist at GFZ, Helmholtz Center for Geosciences, based in Potsdam in Germany. And today I would like to present some first results on sensitivity from biomass backscatter data to forest biomass in Brazilian forest. So the main motivation of this study was an outcome of a workshop that was organized by us together with INPI and ESA in October last year on carbon emissions and removals estimates from remote sensing across different Brazilian forest biomes. There are three main outputs from this workshop. So the first output is mapping of secondary forest extent in Brazil is quite challenging. So in the figure, on the left side in the bottom, you see three different products of secondary forest extent over Brazil, and you see very different estimates of area of secondary forest and very low portion of overlapping of these three products. So hopefully with the biomass mission data, we can map secondary forest extent more accurately. We also, through the workshop, enhanced and strengthened collaboration with Brazilian stakeholders, with Ministry of Environment and with Brazilian Forest Services. So they are very interested in the biomass high-level products. And through this enhanced cooperation, we also submitted a proposal to Biomass Plus Innovation Code together with INPE on integration of biomass data with Brazilian reference data. And the proposal called Be Pronto, and PI is my colleague Viola Heinrich. So objectives of these studies are the first early assessment of biomass backscatter sensitivity to forest biomass across different forest types in Brazil. So we have not only Amazonia in Brazil, we have also Atlantic forest, which is kind of subtropical forest. We have tropical dry forest and savannas. We we assessed also performance of biomass data relative to L-band SAR backscatter from ALOS-2 data. We checked how the correlation between different acquisition dates and reference data are consistent over time. So we compared biomass data acquired during COM1, COM2, COM3, and from operational phase with reference data. We also investigated an impact of ascenic and descenic orbits on the correlation between biomass and reference data. And finally, we assess sensitivity of biomass backscatter to secondary forest age. So study area is Brazil. This is also the second motivation of our study. What you can see, Brazil is a very rich, data-rich country in terms of reference data. You see a nice distribution of reference data over all biomes. So in cyan colors, you can see NFI, National Forest Inventory data distributed over Cerrado and Caatinga. There's also some field measurements are done in Amazonia biomes. And in Amazonia, we have also very dense sampling of airborne laser scanning data. And in orange colors, you can see biomass orbits that were collected so far. So we used biomass level 1B detected ground range multi-look data with a pixel spacing of 25 meters. So these data are not yet radiometrically calibrated and not normalized for topographic effects. As reference data, we use INPI ALS data collected in 2016, 17, and 18. There are in total more than 900 ALS tracks. Each track has a size of 500 meters by 10 to 15 kilometers, so it's quite a long track. So in the total sampled area from ALS, it's more than 650,000 hectares. So actually we have a lot of high quality canopy height measurements. But since these data were collected almost 10 years ago, in 2016, 17, and 18, we also excluded areas affected by major disturbances, so we used a global forest change product to exclude these areas. We didn't apply any growth rates because it's quite tricky, so it's tree species dependent. And to invert height to biomass, we use allometry following Ometo et al. 2023 paper. And in the bottom, in the figure on the bottom, you can see a sampling design of National Forest Inventory data. There are more than 8,000 plots with a size of 200 by 200 meters, so 4 hectares. Within one primary sampling unit, there are 4 subplots where the actual tree measurements are done. So 4 subplots, each of the size 50 by 20 meters, and all trees with diameter greater than 10 centimeters are measured. And then we can use pantropical allometry to convert DBH to biomass, and aggregate these estimates at 4 hectare scale. So here I will show first results of biomass L1B backscatter and NFI AJB correlation. So I took one orbit that crosses entire country and covering biomass ranges from dense tropical forest in the northern part to Cerrado in the southern part. So the data was, this orbital track was collected in June 2025, so it's COM1 data. As expected, we see stronger correlation with biomass at crosspole, at HV and VH. So we're expecting this. For comparison, I plotted here correlation between backscatter from ALOS2 PASA2 data at HH and HV over this exactly the same NFI plots. What we see is also a stronger correlation of biomass data, even it's not properly calibrated yet, but we already have a stronger sensitivity. We can also express this stronger sensitivity to forest biomass in terms of ratio of delta backscatter to delta biomass, so how backscatter changes in relation to changes in biomass. So the bigger is the ratio, the more sensitive is the signal to biomass at certain ranges. And you see in green and dark blue a higher ratio compared to Polinsar data. So this is what we would expect from literature, and yeah, we see it also from biomass data now. Further, we check how is the correlation between biomass backscatter data and, for example, canopy height is consistent over time. Here's an example over one area where we have 4 LS tracks, and the correlation between biomass and LS-based canopy height from COM1, from COM2, and from COM3 data. What we see is a similar correlation at crosspole, so from COM1 to COM3. We also compared biomass backscatter data from operational phase, the data collected recently in December. So there are 6 stacks, 6 orbits covering Amazonia. Here's just one example from a track collected in mid of December in ascending mode. And what we also see, again, a stronger correlation at crosspole compared to copole, and potentially ground notch data or backscatter at 30 meters will further help to resolve biomass at higher range, for example, greater than 200 tons per hectare. So we also compared, we investigated how is the correlation consistent between ascenic and descending orbits. Here, one example of biomass stack of the data. For example, in the middle, we see data collected every 3 days in descending mode in blue, and in the same date, but in the ascending mode shown in red. So in the central Amazon, and we did exactly the same for the another orbits collected in the western part and in the eastern part. So every 3 days, a stack of biomass amplitude data. Here, what we see is R square on the y-axis, and on the x-axis is different acquisition dates, and pairs of ascending and descending. In blue, data collected during ascending mode. In red, data collected during descending mode. So we see a consistently higher correlation for the data collected during ascending mode. We see this for all 4 polarizations. It's still unclear what is the reason for this. Maybe it's diurnal effects, and maybe it's ionospheric effects. What I have learned yesterday is the ionosphere is strongly affects the data during the afternoon and the evening. To some portion, it's also a sampling error. So because ascending and descending orbits samples slightly different areas. But in case of sampling errors, the R square should be kind of more random. Shouldn't be that constant, I think. And finally, we investigated sensitivity of biomass data to secondary forest age. Again, I took this one orbit crossing the country and overlaid with map biomass product, secondary forest age from map biomass product. So in different red gradient colors on the right-hand side, you can see different ages of secondary forest. And what we can see is also a stronger correlation of biomass signal for certain secondary forest age classes compared to ALOS2 data. So in ALOS2, we see a kind of signal saturation at certain age, while in biomass, we see constantly increase in the signal. To summarize, we did the first comparison of biomass level 1B products with available reference data in Brazil. So the data are not yet radiometrically calibrated and not normalized for topographic effects. We observed that correlation remains stable over time, so from different acquisition dates and reference data. We also showed a higher sensitivity of biomass data to forest biomass compared to ALOS2 data. We also showed a stronger correlation of biomass signal at ascending mode than at descending mode. We expect further improvements in the data processing, so when the data will be radiometrically calibrated and terrain normalized, and when the geolocation will be improved, we expect also even better correlation. So the next steps in this study, we will assess high-level biomass products, for example, ground notch data or backscatter 30 meters. We will further stratify this analysis by biomes, forest types, and forest management activities. We plan also to incorporate JEDI measurements. For example, we plan to determine optimal spatial scale at 1 hectare or 4 hectares, so what spatial scale biomass correlates with JEDI, and what is a minimum number of JEDI samples are needed at these scales. Let's say more than 2 or more than 5 JEDI samples over a given scale. And as I mentioned in the beginning, we submitted a proposal to Biomass Plus Co. In order to advance operational uptake of biomass products by national users. And at the end, I want to acknowledge Brazilian Forest Service, INPE, and ISA for their open data policy. Yeah. Thank you.
Thank you, Mikhail. Is there any question? Okay. You were saying that you were expecting to have data with terrain normalization, and this is a discussion which is ongoing to understand if it makes sense, because terrain normalization is made when you don't have any penetration. You just, let's say, calibrate with the surface where you project.
Yeah.
But here we have penetration. We have a forest which is not isotropic, with effects that might not be corrected by just correcting with the topography the way we are doing usually.
Yeah.
But something that you could use is the level 2A product, this ground notch product. The idea is to remove the contribution of the ground, so to have like the backscatter only of the part of the canopy.
Yeah.
We generated this product during the commissioning. We are not generating them currently because we are still improving things, but they should be generated very soon, and they will be the base for the algorithm to retrieve the HGBD.
Yeah. Cool. Interesting.
But maybe the one from the commissioning could be useful.
Yeah. So this is level 1C data, right?
2A, level
2A.
2A.
Okay.
It's level 2A. Level 1C is just co-registrated
Yeah.
level 1A.
Yeah.
Klaus, you had...
You compared the backscatter data to different sites in Brazil.
Yeah.
And the model looked a bit different for each of the sites. Can you explain these model coefficients with some structural elements on ground, or is this different forest types, or how general applicable is this exponential curve to explain backscatter HV relationship?
Yeah, we have different forms of logarithmic function for ALS and for NFI, for example.
I mean, this slide here, you see, if you go down, and here you see that the curves look a bit different. They're not.
Yes, they are a little bit different. Not sure how we can. Well, we can generalize this function, definitely, but it will be then only for this area, and then we can also check if it's applicable somewhere else.
I'm mainly interested if you can explain these differences with differences on the ground between these different forest areas and how general applicable these general curves are.
Thank you very much. It was a great presentation. I was curious as to whether you try to also validate height projects, because it seems like a lower hanging fruit in your project here.
And well, for height, we just compared with LS as shown here. So yeah, we compared signal with the height, but yeah, we didn't compare biomass derived height, for example, with LS height. So I think it's still not available yet, biomass derived height, so high level products, maybe for some experimental sites, and yeah, we need to check if we have reference.
Yes, Elena. Yeah.
Yeah, thank you. I'm also very impressed about this correlation that you get. It's very interesting to see. My question is a little bit, did you play it around? Because here I see it's at 200 meters. Does it mean you have done a very strong averaging window?
Yes.
So did you play it a little bit around, which was the best actually to avoid the noise that you have inside?
We didn't, but yeah, it will be definitely interesting. So yeah, 200 meters, you see also mean canopy height is around 20 to 30 meters because of averaging over a larger area. But yes, at 100 meters, maybe at even at 50 meters, I assume the correlation will be lower, but yeah, we can also check it.
Mm-hmm. Okay, yeah, thank you very much.
Okay, thank you very much.
Now we welcome the next talk by Maurizio Santoro about assessment of early biomass data for the context of global biomass estimation. Welcome.
All right. Well, good morning, everyone. I am presenting here on behalf of a group of people at Gamma Remote Sensing, but actually you should start at the end. Well, you should not start with acknowledgements, but rather have them at the end. And so I would like to acknowledge CCI Biomass and Next Gen Carbon projects. Why do I do this right now at the beginning? Because the angle that I'm taking in this presentation is a little bit different compared to previous presentations, because here we have really an application. And we would like to see how biomass data can serve these applications. And these applications are global biomass mapping. So the background is the following. Maybe you know above ground biomass is an essential climate variable. And as part of a set of 50-something, 55, I think, climate variables. And they are set with some sort of requirements. And these requirements by the Global Climate Observing System are, for example, in the case of spatial resolution, temporal resolution, quite stringent. So you need to get at the hectare resolution, you need to get maps with the long time record, approximately 30 years. So CCI, Climate Change Initiative, is one of those activations where one would like to implement remote sensing measurements to derive these time series of observations. And CCI, being a large umbrella, has one of its components, the CCI Biomass Project. And the CCI Biomass Project stands out to produce these kind of global maps to serve climate and carbon modeling community. So not the local user, not the farmer, but really to give a full portrait of the distribution of biomass globally and to give it over a certain time sequence. So right now we're working on its version number 7, which means approximately 18 years, which will be released then later on in spring this year. And this is somehow our baseline. It's a 1 hectare product, and it's based on what is available nowadays. C-band, L-band SAR, because it covers really several decades. It's more or less consistent, but it's not the best for biomass, as you may know, because of the short wavelength. Then we integrate this with LiDAR observations of vegetation structure, again spaceborne. And this is a little bit the ingredients that are used to create the kind of map that you see on the bottom right. That's one of these 18 maps that we are going to release very soon. On the left-hand side, I just want to show you why it is important to use several measurements. With just one type of measurement, you would not do the job of creating the map on the right-hand side. You would have large artifacts, you would have things that are not really matching what you have on the ground, simply because neither C-band nor L-band are really measuring biomass. But if you start to combine them, you exploit a little bit of the advantages of both frequencies, and if you combine them, then you get to a sort of result. So the map on the left-hand side actually shows you how much we weight C and L-band. Red means it's completely L-band, blue means it's completely C-band. So for the tropics and for the most dry areas, very dry areas, we have an L-band component because C-band isn't contributing at all there. And if you look into the boreal zone or a little bit more temperate zones, is a mixture. And probably towards the northern latitudes, you go into more into C-band. Okay, so this is now the stage. And now let's move on. And so the role of the biomass mission in this case is it's a novel data stream and it's P-band. So we are, of course, interested to see how much does this really nice set of observation contribute to what we're doing now. Not for the past, but maybe for the future. So there are two ways that we can follow. Either we ingest the level 1 data, so the direct observation from the satellite, and we decide we take backscatter, and this will be, at the moment, our primary candidate for doing this, just because we want to explore this in first place. Or the second pathway that we may want to follow is, let's take level 2 data and then see how this may compare with our AGB products and see how they may be combined. Thing is, at the moment, we are discovering the data. And that's the nice component for us. It means that we can look at the signals, we can look at the maps and see how can we make best use of it. At the end, the question is, how do P-band observation contribute to wall-to-wall quantification of carbon stored in vegetation? That would be our ultimate goal, to provide an answer. So overall, we have 8 months of data. So we take the data from these first 8 months, and we would like to understand a little bit how these measurements can contribute to the quantification of AGB. It's an early stage of the mission, so we pursue a signature analysis of the biomass measurements. And biomass standard products, we are interested, point 1, in the backscatter values. Later on, we will look at coherence, we will look at polarimetric measures, and so forth. But right now, we want to explore primarily the backscatter. It's a standard observation, So let's see what comes out of it. The second thing that I would like to mention here is that we are going to compare the set of predictors used by CCI biomass retrieval, so Sentinel-1 and ALOS-2, with the measurements that are coming from biomass. And the third thing that I would like to show you in a couple of slides is also how do these observations from biomass match with either a CCI type of product, AGB, or with heights coming from a global measuring system like ISAT-2 mission. Okay, so this is the situation. As I said, backscatter values, and let's start diving a little bit into the data. So, you know, you could pick data from anywhere in the world. We picked them a little bit from areas where we have experience. Gabon is already known to you from all the presentations so far. It's more or less in that region. We decided to look at an area in Queensland corresponding to the site of Injun, which is more like a dry tropical region. And we took an area in central Siberia around Krasnoyarsk, which is also very known to us from previous experience. The common thing in all of this, it's a lot of images. So if you look into Gabon, for example, for the area that we take, we have in total 26 images from June to January 26. Central Siberia, we have 34 images from the commissioning phase, plus 7 from the tomographic phase along a certain track. And we look into Queensland, it's around 13 images just from the tomographic phase. That was sort of a third choice that we took, so no commissioning phase data there for the time being. Yeah, you can see a little bit different types of above ground biomass values, up to 600 tons per hectare or megagrams per hectare in Gabon, much less in Siberia, 250, and a little bit less in Queensland, 200 tons per hectare. So I will dive a little bit into these kind of sites. One note about the processing, we took the SLC images, level 1A, a multi-look to 100 meter, just be comparable with the CCI products, which are 100 by 100 meter. So it's a multi-look window of 2 in range and 14 in azimuth. We use the Copernicus dam for terrain geocoding and to put everything into common reference frame, which will be then 2 by 2 degree tiles. So everything you will see, it's referred to a 2 by 2 degree, 200 by 200 kilometers, more or less. We did a co-registration between the SAR and the DM, which was really nice after refinement. And everything was done in gamma naught, so compensation for the pixel area. We may want to discuss why, if this is going to alter the radiometry of the measurements, as Clément just said before, but at least we are also removing a large part of the effect of the topography just by itself. Not that it will matter very much in these kind of examples, though. Why did we take SLCs? Just because in the future we would like then to look at the coherence images, at polarimetric features, and so forth. So it's just the start of the work. So let's see, first of all, if I take all the images from June to January this year, and I put them together, let's see what happens. I have 2 sites, Gabon and Central Siberia, 2 by 2 degree area. To the left, you will always see top left, it's the mean backscatter of all the images. To the right is the standard deviation in time of the backscatter. Bottom left would be the number of observations, and bottom right would be the CCI AGB. We're not going to explore here so much the relationship between biomass and the AGB and biomass satellite values. More or less, my focus here is the mean backscatter changes depending on the orbit, and the standard deviation changes quite a lot, which rings a bell saying, if we combine commissioning phase data and tomographic phase data, the temporal information isn't there yet, okay? Not so much. So we move actually to the next one, where we actually see what happens if we just take the tomographic phase data. And then the standard deviation goes quite down. So it's not this 3-4 dB standard deviation. We are close now to 1 dB standard deviation in time, okay, over 7 images. So meaning, let's split tomographic data from IOC data in terms of what we want to understand. So if we look just at these 7 images, more or less from a stack, both in Gabon or that's in Siberia, you will have a nice mean backscatter image, and you could see some association between the biomass from CCI bottom right and top left of these 4 panels, the mean backscatter. Okay, That's nice information. We move on. Let's see now the temporal profiles. I warned you, the temporal profiles may not be representing at all what's happening on the ground. And indeed, Central Siberia, that's just 1 pixel. If you click anywhere in this stack, you would get this kind of profile. A backscatter that changes in time from summer to the left, and then after the start of the tomographic phase, which is this vertical black line, you will get then tomographic phase data. And the message here is please do not compare data prior to the tomographic phase and data from the tomographic phase, because it's obvious that this is not a signal due to temporal variability of the signal. Okay? We're going down something like 12 dB, and that's not realistic. As a comparison, I just put what we get from C-band. Very few images in this area from C-band. And you can see the variability, it's just 2 images, so not really in line with what I hoped to do when I started this work, comparing different signals. If we go to Queensland, however, then you can see Queensland is a more variable situation where it rains during the summer and autumn, which is actually the time when Sentinel-1 was acquired, the blue dots. And then we have a drier season, which is actually what is captured by, in the biomass data set. And there I was surprised to observe that you have a variability of about 1.5 dB every 3 days. So that's not incidence angle, because that's very, very much confined. I don't think it's a temporal thing. Could be ionosphere, but I did not really see any really evident sign of ionosphere, even when processing the coherence data. So it was something that I was, okay, I was not expecting such a variability at a pixel level. In Gabon, we have, for this particular pixel that I clicked on, but it's more or less the same wherever we look, we have a large variability throughout the IOC time frame. And this is really a high biomass data pixel, and that's not really what I would expect to happen throughout months that go from July to November. The commission, also the tomographic data is a little bit more, in this case it's 2 data points, so not really telling much, but again, there's a variability for this distributed target of about 0.5 dB. And still, if I click on other points, I would see, again, this kind of variability of 1 to 5 dB. So my message here would be a recalibration of the IOC data, because you have a really wonderful profile of P-band measurements over now 8 months, and that may let you learn so much about the physics of P-band observations, which is quite new in areas that were not imaged, for example, even by airborne systems like Siberia. So if I click a little bit harder, that was the first message. Now, if we compare PL and C-band, let's see what happens. So we take Gabon, and I take Sentinel-1 C-band, ALOS-2 L-band, and Biomass P-band, everything cross-pole. So if we compare ALOS-2 and Sentinel-1, it's what we would expect, larger range of values for ALOS-2 compared to C-band. If we compare C-band to Biomass, it's in more or less the same kind of situation, larger range of values for P-band compared to C-band. If we start comparing L-band and P-band, which is the one on the right-hand side, you see a blob. And how can you explain something like this? Just wait a second. We move to Queensland. And in Queensland, we just compare here Sentinel-1, so C-band with P-band, because it's a low biomass area. And you can see towards the high biomass values, which mean the high backscatter values, again, P-band is more elongated compared to C-band. But in the low range, there's a large spread, which is a little bit in line with what we would expect. P-band is sensitive to this high biomass. In the low biomass, there may be some effects that are confounding. So all in all, the message is P-band is more sensitive to C-band in high biomass, which was what expected. The opposite occurs somehow at low biomass. And there's no apparent difference for this particular example between L and P-band. So my message that goes in my head, how much can P-band contribute with respect to L-band will not be solved by this kind of plot here. Not meaning that P-band has a significant contribution. It's just what we get from the data nowadays. The last slide I would like to show you is about comparing biomass backscatter measurements with AGB and canopy height. So we look into Gabon, first of all. And to the left side, you have CCI biomass AGB values compared to the HV from biomass satellite. And you may discuss, is the CCI biomass a good map or a bad map? Whatever you may think about it, this is data. And there's a wonderful agreement in terms of trends between the CCI biomass AGB and the backscatter HV. Okay? So this is for us a diagnostic to see how much would biomass contribute. And that would actually contribute. Then above 200 tons per hectare, the simple backscatter HV starts becoming more or less the same type of value. If you do not trust CCI biomass, you may want to trust a little bit, at least the heights coming from a sensor like ISA2. And that one tells you the biomass values of the satellite increase up to 30 meters, and then you get a constant type of situation. Okay? And 30-meter scale up to more or less around 300 tons per hectare, more or less, or a little bit less, a little bit more, but we are in that range. Okay? What I would like to stress here is also the spread of the values. Not just the trend, but also the spread. So for a single CCI biomass value or a single canopy height, you have a large variability of biomass satellite values. And that will be essential when any of us will create maps or estimates of AGB from the biomass satellite data. So the uncertainty associated may be relevant. And something that then can generate quite some discussions when the first data will come out. If we look in Queensland, again, it's a nice increase, regardless if it's CCI biomass or ISA2 height reference, up to the very highest levels. So it's a pretty nice situation, and it's encouraging. This is more or less something new that nobody has, to my understanding, seen before. This is wintertime P-band data compared to either biomass from CCI or canopy height from ISA2, and the sensitivity is very low. Okay. So as the case was for L-band, also for P-band, the P-band signal has a very little sensitivity to forest structural variables in wintertime. Dry, frozen conditions, like minus 20 degrees, which then may also be the case in very dry conditions, also in non-boreal environments. So in conclusion, you have a certain agreement. It depends on the site. Sometimes it's very strong, sometimes it's very weak. But that also means for us that we need to look into more sites and more seasonal conditions, because that's then the founding, the fundament for the stability and the robustness of retrieval methods. So all in all, my conclusion here is a set of recommendations and evidences. So actually from 8 months of data, and it's great that you have already like 8 months of data available on your desk to work with, we have clearly some clear features of P-band signals from forests. It's a data set that is complementary to C and L-band data. However, it's too early to conclude exactly how P-band may fit in a retrieval scheme like CCI exploiting C-band and L-band. We need to see a little bit. We need to look at more sites to get this comprehensive overview of at least the backscatter signatures. And the next step is, of course, backscatter is really like a low-level product. And we have seen that if you move into coherence and if you move into polarimetric features or you combine them, then you start having a much better situation. And reprocess IOC datasets. And, well, there's a side note about errors also in the frames. So when you go to reprocess, please take a look at this to get fully consistent datasets. Thank you very much.
Thank you, Maurizio, for giving the whole picture in 3 continental. Yeah, we have time for questions. Yeah.
Thanks, Mauricio. Good as usual. It sort of relates to the question asked for Noelia, that our intention is to invert to biomass using the ground council data. And the airborne data show clearly that if you just use the backscatter data, you get very low sensitivity to biomass. When you do the ground cancellation, you get much better sensitivity. So my question is, do you intend to sort of redo this analysis with the ground cancel data? And is it up to ESA to make it easier for everybody to actually already be supplying ground cancel data, or ground cancel backscatter, to actually let people do that sort of analysis?
The two questions are clear, both have a yes answer. So we are going to redo the same study, so the same type of really the sites and everything with ground council data, with coherence, with Polinsar data, everything really in that, following this scheme. So this is the scheme is set, and now we are going to put in more and more measurements. And the question is whether I think so. I'm providing higher level data products will be useful for the majority of the users of the biomass data. If biomass wants to have an impact, these data should be provided.
I have to say thank you, Mauricio, for the direct recommendation. In general, if there is anything you would like to see ISA to do or to see to be added, feel free to say it, so we add them to the recommendation and we'll push it to implement it. It's planned to be done. We don't know exactly when, because we're still working on improving the processors. You could see already during the commissioning phase, as you said, that this data should be used, handled with care, because even it was improved every subcom, and Muriel has a presentation later on the processor, and you will see it's still improving, and there will be still some improvement. At the point when we'll be happy enough with the processor, we'll reprocess this commissioning data.
Yeah, thanks a lot for this presentation. I think it's already interesting to see the sensitivity on the height or the structure of the forest, right? Because you have very different biomes that you're covering, even though you have not employed now the ground notching part, but still I think it's interesting. So I think this is something that we can learn of, right? To see where we are sensitive to which kind of height or structure, and especially it's also interesting to see seasonality. My question would be a little bit in terms of seasonality. Did you see also over Gabon some differences in terms? But you had only 2 passes, I understand.
No, there was a
actually would be interesting to see for the sigma 0, right? Because you have rain and non-rain. Do you have kind of variability here on the sigma 0 estimation?
Queensland and come on. So in this case, this particular pixel had 2, but actually it was a full TOMO stack. So if I had clicked somewhere else, I would have had more TOMO measurements and less IOC measurements. I did not see anything. It's more, what was really a little bit surprising was this, maybe it's here not, but the Queensland. For Gabon, it's the same. The red dots, they oscillate without any apparent explanations in a ribbon of 1 to 1.5 dB at a pixel level, 100 meter. And I computed the ENL, and the ENL was about 5, equivalent number of looks. So biomass at 100 meter is quite noisy to come to this kind of question or answer that you are asking now.
So during the in-situ campaigns, when we have this Afriscat and Tropiscat, we could see daily oscillation and also oscillation of trends related to the rain effects, for example, and even seasonal effects. So it could be noise, it could be calibration to improve, or it could be physical effects that we observe, that the scene is changing.
But then you had a very dense temporal sequence, and here you have a 3-day, and before, so that's why really the message is get the IOC, because it's, then you have at least 1 year of measurements. And with 20, 30, 40 measurements, you can learn quite a lot about.
Okay, thank you a lot for interesting discussion, but we have to keep moving on. Thank you a lot.
Thank you.
Mauricio.
The last talk of the session will be provided by Laurent Ferro-Famille, and he will present about ground notch SAR tomography.
Thank you. Thank you for the introduction. So I will I'm going to present a method that is able to integrate ground notching into tomographic focusing. So the first part of the presentation will be dedicated to the principles of this method. So we'll do simple signal processing, but we need to do this to understand how it works. And in the second part, I will apply it on this very nice tomographic data set taken in Brazil. So I would like to acknowledge my co-authors from CESBio, Polimi, and Aresis. So tomography, everybody knows in the room, but I just recall it for those of you who don't know. It's a technique that currently combines acquisitions performed from slightly shifted trajectories in order to discriminate the elevation at which some scatterers are located within a 2D resolution cell. So by doing this, you kind of focus a beam, and within this beam, you are able to estimate reflectivity and also polarimetric features that help you to reconstruct the vertical profile of reflectivity. So this is a tomogram which has been processed 15 years ago after the Parakou campaign in French Guiana, and everybody can discriminate the scattering coming from the ground and the one originating from the top of the canopy, and this was at the beginning of the story for star tomography, following the pioneer work from Andreas Reiber and others. So this is why tomography is implemented in the biomass vision, for this ability to discriminate in elevation. And currently, the sensor is operated in the tomosar phase, so some stacks of 7 images are built to produce tomograms like this one, which has been processed by our colleagues from Polimi and DLR and Aresis. And this phase will last 1 year and a half. And after this phase, we'll move to another phase, which is dual baseline in SAR with only 3 images. And of course, there will be a severe loss of resolution from the tomosar phase to the dual baseline one. And already you can see on this tomogram, which is an excellent result, that the resolution is not exactly the same than one we had using airborne data sets. We are losing descriptivity, of course, because we have a reduced bandwidth. And in this case, when we move to the dual baseline in-SAR phase, we will have even less vertical resolution, and we need to, if we want to take profit of this spatial diversity, we need to be able to separate the contribution originating from the ground and from the canopy, and this is why ground notching is very useful. Okay. It is particularly useful to estimate above-ground biomass using by selecting a layer located, as described by Dean many years ago, at a given elevation above the ground. 30 meters is seems to be a good choice for such a height, and this has been confirmed on many sites, which show that in this case, if you select this layer in the forest canopy, then you can relate tomographic intensity in HV to biomass using a log regression. This choice has been explained by some geophysical features, and also by the fact that at such an elevation, the ground echoes were were minimized. So when you deal with lower resolution data, you need to implement a filter which helps you to discriminate, to really separate the ground contribution from the canopy one. And this has been done a few years ago by the Polimi team with a very simple tool. You just take one image, you subtract this image from another one with a specific weight, and at the end, what you get, the intensity, is the reflectivity density of the forest weighted by a transfer function here, which is a sine, okay? It is this sine. So what you get at the end is the sum of this reflectivity times this sine, and if you select correctly the baseline, you get a maximum of this sine, which is located around 30 meters, and then you can select the response you are looking for. This is how it works in theory. In practice, you may have some problems when there is a topography in range direction, and when the forest is not as uniform as you would like it to be. And of course, you need to compensate some geometrical effects, and this is the price to pay for the simplicity of the approach. Okay. So the tomography, on the other hand, is based on the same model, but we acquired images from many positions, And from this position, from these measurements, we try to resolve this inverse problem. We are measuring correlations, and we want to estimate the f of z, the reflectivity distribution in elevation. And this is to do this, we need to inverse this sum, which is a Fourier transform. And in practice, many colleagues propose to use non-parametric Fourier-based methods because they are very convenient and they are physically sound. You can predict the performance. So just a little bit of signal processing. We need to. This is useful for what's coming next for the implementation of the notch. These techniques can be shown to in fact to satisfy an optimization with constraints. They both, the classical beamformer and the Capon technique, aim to minimize a power subject to a gain which is equal to 1, so that we are measuring exactly the value of the reflectivity at a given position. And the difference between Capon and beamformer is in the choice of the matrix which is used to compute the power. If you select this kind of, if you take this solution, then you will minimize the noise at the output of the filter, and the tomographic focusing is a simple Fourier transform. If you select another choice, then you will try to minimize also contributing, originating from other positions in elevation, and then you will have the Capon solution, which is adaptive. What can we do? Some illustration of the characteristics of this solution by looking at the transfer function, which is the Fourier transform of the filter. And what you measure when you perform tomography is f of z0 at a given elevation, and this is the sum of the total reflectivity density weighted by this filter. And this filter has this shape in a biomass-like configuration. Of course, you see that when you scan volume positions at 20, 30, 40 meters, you aim at measuring exactly the reflectivity at this position, this precise position, but in fact, you're also sensitive to ground contribution occurring here at 0 meters. And to measure the perturbation that the ground can provoke, you can compute this ground to volume leakage ratio, which is given by the weighting function you use. So, and how do we implement ground notching in the tomographic configuration? We start from the original formulation of the beamformer and Capon, and we add a simple constraint, an additional constraint. We say we want the gain to be equal to 1, and we want to have a gain of 0 at ground level. We solve this problem, okay? We do some calculation to solve it, and the solution is very simple. It can be written like this. This is an interpretation. The first part here is a projector on the space which is orthogonal to your constraint. So you want to have a gain equal to 0 exactly at this location. And the second part is a compensation of the transfer function of this projector, so that you are not biased. Okay. The expression is closed form, and it's very, very simple as the beamformer and Capon solution. And you see that in using simulations, it works. And some colleagues, my colleagues from Polimi and Aresis asked me if we could try to, because very often we are not exactly, we have difficulties positioning the ground level exactly at 0. We may have some ground contribution occurring from elevation located a bit below or above the assumed ground level. And in this case, we still have some perturbation. So to fix this, there are different techniques. We selected the one which is based on a slight modification of the covariance matrix. It's very simple, so no work. And by doing this, you improve the rejection ratio by about 10 dB compared to the original technique. So now, application to real data. We use this very nice data set acquired over the Tumucumaque Park in Brazil. And the vertical resolution is 30 meters. For the airborne image I showed at the beginning, it was around 12 meters. So there's a change. We cannot expect to have exactly the same description. And these are the coherences which have been shown, prepared by Francesco Salvatera. And you see that we see a very fast decorrelation of features due to both the volume and also to temporal effect that makes that the coherence converges very fast to 0, but the phase information is still useful, so this is why we can perform tomography. So the first step before applying ground notching is ground locking. You need to know where the ground is and to know exactly at this position. Otherwise, you will in fact, kill or you will cancel some responses coming from the canopy, or you will miss the ground. And the technique we are using will be presented by Francesco Salvaterra in another presentation. I don't insist on it. And this step is critical for ground notching. If you don't perform it well, then ground notching is useless. So some results. This is a range profile. Okay, so this is reflectivity estimated by the Capon estimator. And here we just multiplied this reflectivity profile by the transfer function of the different filters. So this is the interferometric filter, the ground notching by Mauro by the polymeting, which is a square sign. So it is symmetric around 0, but it has a very strong null at the assumed ground location. And these are the beamformer and Capon solutions. So you see that they are asymmetric. So they let go through the filter the canopy. This is what we want, and they cancel the ground contribution, and of course they have some side lobes occurring well below the surface. Okay, but you see that the ratio between the power, the selected, and the spurious peaks is very large, and by comparing the tomograms on the right and left-hand side, you see that simple tomographic focusing is good at selecting the canopy response, but still lets some parts of the ground contribution go through the processing. So in this case, ground notching may improve the ground to volume leakage. And this is what you can see on these images. These are beamforming focusing results at the ground level plus 20 meters, 30 meters, 40 meters. Same thing after ground notching. We don't see many differences. I could have shown a ratio image. You see some differences, but in the tomographic mode, you can clean your image, but if you don't do it, this is not dramatic. You will not have a huge difference, okay? We expect to have have a much bigger difference in the dual baseline INSAR mode. And this is what we are studying here. Here we are moving to the only 3 images. So the resolution, the vertical resolution becomes huge, 60 meters. So here this is the tomographic Capon spectrum. So this is the one with 6 images to know. We take this as an estimate of the true reflectivity. And we compare with the filters that are provided by the INSAR notch filter and by the beamforming and Capon ground notch filter with only 3 images. You see that the selectivity is a little bit worse than what we had before. Here we had some very low level here, but it is still much better than the INSAR filter, where you see that these lobes are high. And these contributions do not correspond directly to the canopy, and they will be interpreted as so if you only use the 2 images. So here we expect to have a better isolation. Some application on the data. Here on the left-hand side, you see the unconstrained tomographic results. Okay. And these are the ground features, and you find them in all the other images. In fact, due to the very huge resolution, you cannot separate ground from canopy. You need to consider them both at the same time. By using the ground notching, you have a much more homogeneous map, and you don't find again the ground features in the image. And we compared this image with the results obtained by using only the first 2 images, the interferometric ground notch filter, and by doing the ratio of these 2 images and using the histogram, we see that the difference is centered in 0. We have a pretty narrow distribution, which shows that they agree mainly over the whole image. The 96% of the estimates lie within 2 dBs. 2 dBs, if we agree with the relationship found by Dean many years ago. This corresponds to a bit more than 100 tons per hectare if you convert them with this regression line. So this is not negligible, and now we need to know which one is right, if we should actually implement the tomographic one or stay linked to the interferometric one. And one advantage of this ground notch tomography is that you can notch the ground and still scan in elevation. So you can find a map at the supposed canopy level or above the level, and this can be useful to further analyze the forest. And of course, it can, by using this ability to scan the forest, you can adapt the technique to other biomes like smaller trees and other regions, not only tropical forest. So in conclusion, this presentation showed an extension of ground notching to configuration having more than 2 images. And it permits us to combine ground cancellation with traditional vertical scanning. It is particularly useful when you have a very coarse vertical resolution, so tool baseline INSAR, and it could be applied to AGBD estimation, forest disturbance, and change detection, etc., etc. So I thank you very much for your attention.
Thank you, Laurent. I see already a question from Mathieu.
Thanks, Laurent. Great work. Thank you. I have a question. Does it work with only 2 images, with one baseline?
No, in fact, the one which works with 2 images is the one made by Polimi, by Mauro, in 2020. And this one works with a number of images you want to fit, so 6, 7, or 3.
Yeah, okay.
And it will be more useful, I believe, with a low number of images, because then, in this case, you have natural problems to separate ground from canopy.
But if we lose one image during the insert phase, then we stuck with the classical cancellation.
Yes, so you can use it only with 2 if you want, yes.
Yeah, so there would be 3 different configurations, right? Today we have only the configuration with 2 passes. This would be in case we lose one of the 3 passes in the end phase. But there would be 3 passes configuration if we have them 3, and a 7 passes configuration from the tom phase.
Yes. So the filter can be applied in any of these configurations.
Okay. I think there was a question there. Yeah.
Hi. Thank you, Laura, for the presentation. So if I understood properly, so you modify the Capone and beamforming PSF to have a 0 at the ground level, no?
Yes.
So then I have a question regarding this ground notching, because it is based on the destructive interference of the ground signal, no? To cancel the ground.
I'm sorry, I cannot hear you well.
So yes, the ground notching is based on the destructive interference of the ground component.
Yes.
So then you mentioned that you need to know exactly the phase of the ground, no? So for this, but I have a question regarding also temporal decorrelation, because in order of this destructive interference to work, it's not that they have to be in phase, but also that they have to have exactly the same magnitude. So if there is different temporal decorrelation, also the ground notching will not work between the images. So then my question is if you have analyzed this or if you have seen this in this.
Yeah, we wrote a paper a few years ago on the requirements on correlation for ground notching. Of course, if the images are completely uncorrelated, you just subtract noise. I mean, you cannot. In fact, the condition to use the ground notching is to be able to perform tomography or to have a reliable phase, interferometric phase. So these are the same conditions to apply interferometry. Of course, if it decorrelates, then you can't.
Okay, thank you.
Thank you.
Okay, thank you. If there are more questions, I would propose to close it now. You can discuss during the coffee break. Before going, I have an announcement. So, information on the guided tour of tonight. So, the pickup point will be at 6:30 at the registration desk, so at the entrance. And the drop-off point will be at 8:30 at Prezersnov TGR Square, so where the pink church is. And it could finish a little bit earlier, in case it's faster. So at 6:30 at the registration desk.
So for the last biomass session of the day, what we will do is we will go a bit more into depth on the biomass retrieval. We will then have Muriel explaining how all the stuff that you heard in the last 2 days is ingested into the biomass official processor and what is there and what is still to be done. Then we have a talk on the level 3 product. It is a bit into the future because it needs a global coverage, so it's more an outlook. And then we have 2 talks on the biomass map, so how to access the data on our platform. Be careful, we swapped a bit the sequence of talks, so we updated just right now the sequence, so don't get confused. First speaker is Maciej, and he will talk about the level 2 retrieval.
Yes, thanks Klaus. Hello, so I'm Maciej Soja from Wageningen, and I will be talking a little bit about another assessment that we did of the idea was to assess different P-band observables for AGBD estimation over the Amazon, but we kind of changed it a little bit because we use data of opportunity in different places, so it's not so much over the Amazon. And abstract was a little bit, it's also a little bit different from what I will talk about. So I will first give an overview of the biomass data that I had available for this work, and then I will investigate the radiometric stability in time and see how much it varies from date to date over different environments. And then I'll go through biomass estimation potential from backscatter and tomographic data, and then I will sum up, right? So we have these different levels. These are the level products that are kind of useful to mortals. I'm not talking about level 0 or raw data or anything like that. That's for the geniuses who presented yesterday. I'm interested in generally speaking, I'm the guy who takes level 2A for biomass. For biomass, takes level 2A into level 2B, right? So from council backscatter to AGBD, that's what my role is. But if you look at the data that we have available from the tomographic phase, so I'm not using IOC phase because there's a lot of issues that have not been, the data has not been reprocessed yet, right? So there are a lot of issues there which I don't want to deal with, and so we take the tomographic phase data only. For level 1B, we have, I think as far as I understand it, there is one full cycle, major cycle, I think it's called, or global cycle. I don't know which one it is, but there's one cycle with 3 swaths covered. For level 1C, which is the core register, the single complex images, we only have, they're being processed now, and I think we only have 1 swath, and it's not over all places either. So there's not a lot. And then for level 2A and above, we have, as far as I know, there is nothing available. So I had to go do something that is, I had to go and look at level 1B and level 1C data and see what I can extract from that. Right, so this is of course the first image we saw, and I was hoping to get this when I downloaded the data, and yeah, but I got a lot of this, right? A lot of different issues. Some of the issues you can recognize as RFI or ionosphere. Some other issues are just bugs in the code that were discovered. Some other issues are actual natural effects that we try to understand. Right, so most of them have been resolved. A couple of them are during. There's an ongoing investigation, and yeah, so we are almost there. So when it comes to backscatter variability, I had a quick look. I wanted to see some place where you have extreme conditions, but of course the last couple of months it's been winter, right? I had a look at a place near Omsk, Siberia. I had a look at HV backscatter, and I had images that I thought were quite good in terms of RFI and ionosphere. But of course, I could see some offsets between the images. I should also add that I had to mask out some areas because there were some artifacts, right? And then I want to understand if these offsets are because of radiometric problems, or these are natural changes in the forest that are caught by by the radar. So what I did is I studied the offsets between pairs of images, overlapping images, and I essentially minimized the sum of square differences with an offset applied, and just try to estimate what offset do we need to apply to each image so that in the overlap areas over this entire region we will get minimize the differences, right? And then I decomposed, using a very simple approach, these estimated offsets into a swath-dependent thing, so like incidence angle-dependent thing, and a date-dependent thing, just to see how much it varies across dates, and disregard from the fact that we have different incidence angles. So for this boreal forest in Omsk, near Omsk, I could see this. So these are the estimated day-to-day offsets together with their standard deviations or uncertainties. So in the beginning, in November and early December, we had quite a lot of variability, and then it stabilized a little bit. You can see the temperature in the middle, and then you can see the precipitation at the bottom. These are from NASA, from the NASA power system, which is like a combination of, as far as I understand, of model-based and remote sensing observations, right? So these, in the beginning we had quite a lot of variability, and then it decreased. There are several possible explanations. One could be, weather, although I don't think the weather played such a huge role here. I think maybe it was ionosphere. I don't know. Yeah, we're still investigating this. These are fresh results. So then over a tropical forest in the Amazon. So this is around the city of Manaus. You can see the city. I don't have a pointer, but like in the middle to the right a little bit, to the right of the image a little bit. You could see that the stability was really good, right? So this tells me that, probably that what we saw for the boreal image was related to ionosphere, or how it affects also the radiometric calibration, the correction of the ionosphere effects. Here we see a very stable, nice and stable behavior, which is good news, I think. And then I also did it for a transect over Africa. The same thing, same conclusion. It's very nice and stable between dates. I cannot find statistical significance in terms of the variability from date to date, let's say. Okay, so what I did then is I removed these estimated offsets, and I created a mosaic. And here I just show for the area near Omsk, because that was where these offsets were the most visible, and this correction worked the best. I don't have any reference AGBD data for that area, so I will not show any biomass estimation results here. But I will go to the tropical forest instead. This is Gabon, right? This is La Lopa. And I show these 2D histograms for the three polarizations. This is sigma naught. It's an average of multi-temporal acquisitions from the tomographic phase. And then on the x-axis, we have ALS AGBD from 2015, I think, right? So there's a 10-year time offset. I see a really good relationship. There is a loss of sensitivity in the higher end, but it's not, I would not dare to say that it's saturation, right? And when I fit this red curve, which is actually fitted to the medians of the box plots, just to kind of model the median, and I do an estimation of biomass, I get these residuals, right? These box plots here, and there seems to be very little bias when you do this. Of course, this is like same data for training and validation, so we typically don't want to do that, so that will follow, right? Anyway, I use this one of these this HV model, I think, to create this carbon map, which you can find online on the ESA website. There is a news item. ESA Biomass goes live with new data now. There is this transect, and we converted simply estimated carbon by dividing this biomass map by 2, right? And there is a transect showing how
this carbon density changes as we go from Angola to the left all the way to Chad, or up there. Yeah, so it's of course a first attempt. This is a first test. We will work on it and we will improve it, and we will do a more rigorous training validation. But this is where this comes from. So I did something else as well. Courtesy of Misha Urbazayev and Martin Herold, I got access to AGBD little maps over the Democratic Republic of the Congo, where they have about 1,000 transects of ALS, and then there are estimates of AGBD, right? And what I did is I processed the tomographic phase data, everything that I could find from tomographic phase. It was hundreds, close to more than 1,000 acquisitions, I think. This is a pretty large. This is a pretty large area, right? And then I compared the relationship that I see in the western part and to the relationship that I see in the eastern part of DRC. And as you can see, the relationships differ. Right, we see much less sensitivity to AGBD for Eastern DRC, and the question is why. And I talked to Jérôme yesterday about this, and one possibility is that there are different topographic conditions. So Eastern DRC has more sloping terrain, and we've seen this before, that in sloping terrain we see something that is often misinterpreted as saturation. If you have sloping terrain, the ground effects cause a loss of sensitivity to biomass, which is often misinterpreted as a saturation. So we think that this could be one explanation. Another could be that there are different types of forest. Of course, we will look more into this. So when it comes to topographic effects, as I said, we can do tomography. And until last week, I had never done tomography, but I downloaded level 1C data and I started testing, and it's actually super easy to do tomography from level 1C data. Thanks to all the people who talked yesterday about all these corrections and all this great work, we can actually get data that are pre-processed to such high quality that we can do tomography without doing all these tricks and topographic corrections and radiometric corrections and all these things. We can just essentially do it, inverse Fourier transform in the vertical direction, that's it. And then you get this profile. This is over, again, near Manaus in the Amazon. I use one of the LiDAR transects from that area, which were acquired by the EBA. I don't know what that acronym stands for, I'm sorry. But it was acquired between 2015 and 2018. I think Misha also talked about this data set. So the tomogram looks really nice. It follows the ALS-THM very well, except for maybe the areas near the river, right? You can see at the edges of the river we have a backscatter that goes higher up than the actual canopy height model. So this is quite interesting. Of course, this is our first results, from last week. So I really, I really had to work a lot to get this to work. But once I figured it out, and I figured out the phase corrections, then it's all easy. So this is another transect, also from that same image, but another different transect. This is really cool. This shows, like, when you look at the total backscatter in the middle, and you compare it to the LiDAR mean canopy height, which is a well-known proxy of biomass. It is not always the best proxy of biomass, but it is consistently a good proxy of biomass. When you see that, you don't see the river. There are two rivers that are visible in the optical image, or one of them is visible. You don't see that in the total backscatter, but if you do a backscatter at 30 meters, which is what Dean talked about earlier, yesterday, I think, you can see that the backscatter around the rivers goes down, right? And this is because my interpretation is we lose the double bounce. I think the double bounce is primarily between the canopy and the water underneath, right? We lose that, and we have a better representation of the top of the canopy, which matches the LiDAR mean canopy height better, in my opinion. And then from this LiDAR mean canopy height, we can estimate biomass using like using just a simple model. And I can plot it against backscatter, and I plot it against 3 different types of backscatter. So we have ground backscatter, so that's the tomographic slice at ground level. Canopy backscatter, which is, in this case, actually I took at 50 meters because it showed what I wanted to show better. So it's simple as that. And then the total backscatter. And what we can see, what we can see is that especially in this lower biomass area, we lose some of we get rid of some of the double bounce, which is very pronounced in the ground backscatter part, also in the total backscatter, and the backscatter goes up there, and the relationship gets really much more easier to model and predict, which is something I really like. I would like to make things simple. So to summarize, I see very good radiometric stability, and I think for these data sets that I had, we had very consistent conditions, either always negative temperatures or always positive temperatures with some precipitation. I see very good stability. I think that tomography, thanks to this beautiful level 1C product, tomography is now accessible to everyone, as we said. If I manage to process it, then I'm sure many of you will be able to process it. I had no experience with tomography before. I was afraid. Sorry, I was afraid of tomography. Now I think it's accessible. You know, so we will not provide tomographic products like profiles or something as a standard, as far as I understand. Correct me if I'm wrong. Huh? I'm wrong. Okay. I thought we will be okay. Yeah, but it's not one of these level 1, level 3 products. Anyway. Okay, we will be providing tomographic products, but we'll also be providing these beautiful level 1C data sets, which you can process the way you want. And I see a really good potential for AGBD estimation for both backscatter and tomography. And I think even if we, for some reason, lose 2 of the 3 images and only get 1 image, we should be able to get decent estimates in most places. And of course, work continues. And thank you, Muriel, and thank you, Stefano, for your constant support and, you know, for being patient and everything. So that's it. Thanks.
Questions? Jerome? Tui. Or maybe Tui first. Tui was faster, Jerome. Maybe not.
Okay, thank you, Soja, Marseille. And it's very nice, your presentation. My question is, there was many doubt about the use of Tomosar, and in particular, the slide of 30 meters to concern the crowd contribution and to increase the sensitivity of the Tomosar slide to biomass, meaning that with the backscatter, you can have 0.5 dB per 100 tons per hectare with the backscatter, cleaning with topography, etc. And then with Tomosar, you can have 2 dB per 100 tons per hectare, so multiplied by 4. So if our aim is to look at biomass change, do you recommend later that the Tomo phase will last more than 17 months, or now or at the end of the mission? That I asked Klaus the question.
If you look again, so you're asking if you look again at tomography at the end of the mission, it's not now. The plan is to do tomography and then interferometry, but as we heard yesterday from Jakob, there seems to be enough fuel. And of course, if we have at the end of the mission enough fuel, we can consider to add another tomographic phase at the end. But we should also note that for the explorers, we're very flexible. So if there's any other idea, and I discussed with Kostas during in the morning a bit, we can implement it if the community is asking for it. We can see what we can do and if it makes sense.
Yeah, it's very nice that that Marseille is working on backscatter, and he started with tomography maybe a few weeks or few days ago, and he got a good result. Yeah, thanks.
Thank you.
Thank you very much. It's a fantastic presentation. You and Misha are doing several things, and at this point, I think it's important to reflect on the quality of the ground data that you're using, because it may well be eventually that it's not the remote sensing data that cause the scatter that we observe in these very beautiful plots already, but the ground data. So it's really a call to explore what error could come from the ground data themselves, and there could be many. So I don't know if you want to reflect on this.
So I know that how important ground data are, and I know that you're working on the GeoTrees project. You have ground data. Unfortunately, as far as I understand, we will not be able to use it for training. It's for validation purposes only, right? So we will have to use whatever we have to estimate these parameters, and we will be using dodgy data as well, I'm sure. So unless GeoTrees becomes available to us for the training purposes in some sort, of course we need to avoid, you know, relationships where we have incest, right? Which is where we're using the same data for training and validation. Of course we want to avoid that. But yeah, I mean, I think it would be nice if we could have access to some of the GeoTrees data also for training purposes.
To be continued.
Yeah.
My check? Yeah, that was really useful talk. I'm here.
Oh, yeah.
If I saw those numbers correctly, you showed, I think, that the ground return was about 5 dBs higher than the volume return. Is that sort of number in that presentation? Yeah, so that makes the point utterly clear that unless you're looking at the ground cancel data, you're looking at a signal which is likely to be completely dominated by whatever's going on the ground.
This is actually a Thomas slice at 50 meters, so it's about 20 meters above the forest height in this area. So it shows the trend much better, that's why I'm showing it, but it usually, well...
Yeah, but if you're looking at the thing on the right,
oh, yeah.
I mean, you're saying, but the left-hand side says your total signal is dominated by ground. It's 5 dBs higher than the...
I would not compare these across too much because I haven't it's quick results and I haven't verified the radiometry yet. So I'm not 100% sure that these are, the absolute values are correct here.
Oh, okay, that's important though.
Yeah. So this I didn't...
From that, you must take the ground.
This shows that, you know, ground has a lot of information from the double.
It's got a lot of information. It's also going to really corrupt your total signal. Sorry, I mean, I'm saying something that we all know, but that is so clear on there that I'm very pleased to see it so clear.
You're pleased to see it, yeah?
Yeah, of course I am.
I'm also, so the thing is when you take the slice that's whatever, 50 meter in this case, where we have a resolution, vertical resolution of 30 meters or something, and for this, actually for SLC data, for co-registered SLC data now, we only have 5 images out of 7. I don't know why, if it's a bug in the system or something, but it's a bug in the system. Okay, it's already known that it is a bug in the system. There are only 5 images available. I did this tomography with 5 images out of the 7 that we should have. And so we can, I think that can improve the resolution a little bit. I need to speed up. But,
yes. Now where everyone is happy, then maybe it's time to move on to the next presentation.
Thank you.
And it's given by Muriel, so for a statement on processing status and biomass products.
Good. So, good morning. Yeah, so my presentation, it's for information presentation, it's not technical, and it's putting together a lot of the things that have already been said in the previous days. So here, what I'd like is to give you an idea of what we are doing in the biomass ground segment, where we stand and where we go. So first, a bit of something to remind us. So the biomass had basically 3 phases, let's say. First, we start with the commissioning phase that lasted more or less 6 months. Now we are in the tomographic phase that will last 16 months, and we cover the 3 SWATs, each SWAT coverage lasting more or less 21 days. and resulting in one global coverage. Then we move to the interferometric phase, where we alternate the SWATs every 9 days, and we will have more or less 6 global coverages at the end. So to answer a bit the question of Maciej, so here it's again our major cycle, which is pretty much the coverage of all the 3 SWATs plus the drifting window that we have. So for the tomographic phase, we have our 7 images stacks. So for each SWAT, we have these 7 images acquired, then we go to the next SWAT, then to the next SWAT, and then we reposition in the satellite. This constitutes our major cycle. We do the major cycles to cover the entire globe where we can acquire, and then this gives us our global coverage. As I said before, for the TOM phase, we will have 1 global coverage, while for the INT phase that comes later, we will have 6. And in all these missions, what we do, all these mission phases, what we do, it's our biomass product family. So these products that you can see in the screen now that have already been mentioned by different people are all the products that are under production right now in the ground segment or will be in production in the ground segment or in a part of the ground segment and will be distributed to the users. We have the level 0 that right now are the data with the most limited distribution, only available to particular CalVal users. Then we have the level 1, which is available to everyone, and there we have the single look complex data, the level 1A, the ground projected data in multi-look, the level 1B, and the stack product, which is the level 1C, which is our co-registered images of either 3 or 7 images according to the mission phase. Then we have the level 2s, which are geophysical or quasi-geophysical products. There we have basically the AGBD that Maciej was just talking about, the forest height that was discussed in the morning, and the forest disturbance that we haven't talked too much about. On top of this, we are developing currently with the team a level 3 processor, which is supposed to consolidate the information, ensuring consistency between our AGP and forest height and homogeneity in time and space. This is still under development and its production strategies is still to be defined, but the plan is as well to generate this product and provide it to the users. For these products, we have developed our production model, which pretty much tells us how we produce this data once it's downlinked from the satellite. It's pretty straightforward, so we obviously start taking the level 0 and generating the level 1s. Then we go to the stacking, the level 2, and then finally, once we have all the level 2 done, we will do this consolidated level 3 product. The level 1 A, B, and the level 1C production is data-driven in a sense that whenever we have the data, we produce it. That means that for the level 1 A and B, so the single look complex and our multi-look projected products, as soon as we have the data and all the auxiliary data as input, we produce them, which gives us a latency of about 12 hours in sensing, which is mainly driven by the downlink. For the stack product, we wait until we have all the images acquired and processed to level 1A, which means that we have a latency which is about 9 days for int phase and about 18 days for tom phase. Then for the level 2s instead, we wait for the entire, for level 2Bs, we wait for the entire coverage, which means that we will only have the level 2Bs products available to the users at the end of our coverage, which means 9 months for the int phase and 16 months for the tom phase. And for the level 3, as I say, we are still defining because the level 3 is something that works with multiple coverages. So we have to think if we will produce once we finish a coverage or we wait until the end of the mission or in specific checkpoints to produce. Right now, as Maciej already noticed, we don't have everything running in the ground segment, so level 0 and level 1 SLC and the DGM production are happening and the data is pretty much okay, with some bugs to be solved still. Calibration has been applied at the end of commissioning phase, which means that all the data from the tom phase, which has been acquired since end of November and produced from the 12th of December, are more or less calibrated. The stack is being run right now, but with a limited configuration, so basically we are not using all the calibration modules, but the production is running, and I'm more of that in the next slides. And the level 2, for now, it's on hold, and I will talk more about this later. So a bit of a note on the production status again. So this has been said already a lot, but I emphasize the commissioning phase data is in a special collection which is available to CalVal users, and it has not yet been reprocessed, and it does not have the proper calibration, nor consistent calibration throughout the commissioning phase. So use this data with care. For now, we have been producing the data of DOM phase nominally. We are now in global coverage 1 and major cycle 1. We have processed a bit in a strange order because of when we started. So the SWOT 1 has yet not been processed. The SWOT 2 has been processed to level 1A and B, and some of the level 1C has been processed, but not all, because we have stopped the production to do other analyses that were higher priority. And the SWOT 3 is now being produced and is going to be produced to level 1C. Once we finish all this production of level 1A, B, and C, we start to think about reprocessing of commissioning phase data, and reprocessing of data with corrected software. The level 2A and B is still not produced because we need to wait for the conclusion of the major cycle and for the correction of some newly identified issues. So all the documentation of biomass, it's available online, and if you go to the QR code on the top of my slide, you can access the full page with all the biomass information. And in particular, if you go to the big QR code, you will see the biomass product definition document that will give you all the information regarding the characteristics of each level of product. Here I just compile a bit the main characteristics. So again, go into our family, level 1A, B, and C. The level 1A is our single look complex data, which means we have a resolution of about 22 to 23 by 8 meters, with a spacing which is a bit smaller, with some oversampling. So we have here one look. Our detected product is still in 0 Doppler, but ground projected with a resolution which is now coarser because we are doing multi-look, and the default look configuration gives us a resolution of about 55 meters. The stack product, our co-registered stack, has characteristics which are very similar to the level 1A data. So again, single complex, but that has been interpolated to a common reference geometry. So resolution of about 20 meters by A, and is single look. One note that's important to mention is that for the moment, level 1A and B contain 4 polarizations as you would expect for a quad-pole system. But the level 1C has only 3, because for the interferometric product, it has been decided at some point that we would merge the cross-pole into a single channel. The software instead is able to generate the 4 polarizations, and given all that we observed in commissioning phase, all the polarized effects that we have, we are now doing the work to see if we should, instead of providing just 3 polarizations, provide the 4 polarizations as well for the stack product. A bit on the product. So this is an example of one of the first data sets that we had back in June. So this is a data take, and what we do to produce is that we cut this data take in slices. So the level 0 has a duration of about 117 seconds, which is about 750 kilometers on ground. This level 0 slices is then cut again in frames, and we process each frame of level 1 data to a level 1 product. The level 1 frame, it's about 25 seconds, and then we cut some margins, which gives us a level 1 product of about 21 seconds. And this is what you find in the map for the level 1, level 1C, and the level 2 products. This is an example of level 1 product folder. So the image on the top, it's a quick look that you would find in the preview folder. The product structure looks a bit like I have here on the bottom. So you have a main folder, and inside you have a main product header that will give you metadata that can be used for the query and retrieving information about what the data contains. We have an annotation folder that contains as well an XML with processing parameters, flags, and other important annotation, and also our lookup tables, which will give you information of geometry, like the DEM in the product geometry, lat long, and slope, for example. We have then the measurement, where you find the the geotiff, so the TIFF files that will give you the absolute and the phase of our SLC, and the preview where you find the quick looks and the chimeras. All the files can be accessed individually with the API, and they are also small, so the handling of this data it's relatively easy. Here is an example of level 1C product. Here an ascending and descending pair with a crossing. The product of level 1C looks pretty similar to the level 1A. So again, you have a main folder, then you have annotation folders with the difference that now you have annotations for the primary and the co-registered image. And you have as well the measurement, where you find the absolute and phase, and the previews. And you will have as many folders as you have acquisitions in your stack. There is some important information in the annotations, but also in the main product header that allows you to see if this particular folder is the reference image or not. And that gives you the stack ID, which is the metadata that you need to understand if a collection of 7 or 3 images constitutes a single stack, because the data is not bundled together. They are really just given in the form of individual folders. This is what I was just saying. So here you have the stack ID. And the idea of the stack ID is that it contains, say, a unique way to identify a stack that you can eventually also reconstruct by yourself in case you would like to look for a particular stack. So you need to use this little formula at the bottom that contains the stack, so the SWAT number and the major cycle, the global coverage that we are, and the position that you like to look for. This is the level 2 product family. So basically we have the forest height, the forest disturbance, and the ground notch at level 2A. So basically here we have a much coarser resolution because we are doing multi-look to do the inversion. So for the forest high we have about 200 meter resolution. For the forest disturbance we are 50 meter resolution, and for the ground notch 100 meters resolution. The level 2B, which is produced from multiples level 2As, it's not anymore in the slant range footprint, geocoded footprint, but it's now on a tile of 1 by 1 degrees. So here we have, again, the full family, now forest height, forest disturbance, and now going to the AGB that Maciej was explaining before. And the resolution is more or less similar, except that now for the AGB we have 200 meters resolution. For all these products, we also try to give quality layers to auxiliate the interpretation of the data. Here is basically the tiling grid that we have for biomass. So these are our 1 by 1 degree tiles with a sampling that changes a bit with latitude. Then a quick overview of the processor. So all these products that we've mentioned so far are generated by what we call the Biomass Processing Suite, or BPS, which includes the level 1, level 2, and level 3 processors. This is an overview of the level 1. So basically we do what we need for pre-processing, and then we have the actual focusing. During the focusing, we also perform radio frequency interference detection and correction, antenna pattern compensation, and ionosphere compensation. RFI, as was already mentioned yesterday, it's a big thing for biomass. Here we have implemented 2 kinds of algorithms, a time and frequency domain approach and a frequency domain approach. Basically, we detect and then we correct the data. And we can correct all the polarizations in the same way to avoid introducing polarimetric artifacts, which doesn't work all the time in any case. As I said, the RFI is a challenge, and this you can see very quickly if you look at commissioning phase data, where you see that several data takes are affected by RFI, in particular in Asia. And Arabia, and here is an example where you see nice RFIs which are also somehow polarized, and on the top you have the result without the correction, and on the bottom with the correction. So the correction that we have in place more or less works, but it can introduce some sort of inconsistency in radiometry in time. We have to be careful with the polarimetry in the frame, and since we correct the images at level 1A, A level, we cannot ensure the consistency in the stack, which is also a problem. So in order to not disrupt too much the product, we are now correcting just in particular places. Here's just an example to show you that first you can see the information of the RFI correction in the data annotation. So there you can see which parameters have been applied. And in the annotation, you can also see the amount of RFI that your data contains. And here in the plots on the bottom, you can see some examples of how the RFI looks like in your polarimetric covariance. So this is the mask. So as I said, we are being conservative and we are using for now a mask to correct RFIs. From the IOC experience, so we saw that they are mostly concentrated in these blue areas, and here is where we have the correction activate. It doesn't mean that it doesn't happen in other places. In fact, you will see RFI in other places, in particular in the rest of Asia, where the correction is off, but even in South America sometimes. Moreover, even when we correct the RFI, the data is not fully corrected all the time. It depends on how the RFI is spread in the spectrum and the strength of the correction that we are applying. We also have ionosphere calibration at level 1A. Basically, we correct for the Faraday rotation and the phase screen and range delay, which are estimated during the focus. We have an autofocus module implemented, but is not used at the moment, because since, as Felipe said yesterday, it doesn't work globally for biomass due to the lack of contrast. Just to emphasize, so the level 1A that comes out of the processor looks quite nice. But even after the ionosphere correction, sometimes for strong ionosphere, you can see residual radiometric artifacts like this kind of things, for which we at the moment do not have a correction. I would like to take this point to emphasize that we have quality disclaimers for biomass data, and if you go to the QR code in the bottom, you will see the collection of quality disclaimers that we have. At the moment, it's pretty empty, it's growing, and one that you will see now there, it's this blocking artifacts in the borders, which have been corrected just now with the just delivered BPS version, which will be deployed in the next days. So the stacking does our level 1C products, and here again we have a pre-processing, the co-registration module that puts the images together using the known geometry and cross-correlation. And we have the calibration module where we do azimuth spectral filtering if you want, and INSAR calibration, which is basically multi-squint for the faster varying ionosphere components, plane phase removal, and we also have split spectrum in range implemented, although the conclusions from commissioning phase was that it's not really worth to use it. For the moment, we only have the blocks in green running into production, while for the calibration, we only have the plane phase removal. This is because we have been evolving the algorithm and the software a lot in commissioning phase, and you've seen several teams discussing about this, in particular Polimi. And we will have a next major version of the software in the end of February, putting these things in production. This you already saw a lot, so examples of coherence. I just wanted to take the chance to say that we have layers to support the use of this data. Here you can see the flattening phase layer and the SKP calibration layer. And here one example that you would find also a lot, which is a very bad coherence case. Here you can see ionosphere, this was close to a storm, and also a lot of RFI. So don't be surprised. For the level 2As, I do not talk too much. So we have a forest disturbance product that will be done once we finish a couple of cycles, and the forest high that was discussed by Roman this morning. So we have the single baseline and the multi-baseline implemented in the operational branch, and the tomographic approach as well in the scientific branch. Why this is not in production yet? The fact is that we focus the IOC validation activities in level 1 products, and now we move to level 2. And what we saw when we do the first level 2 validations from production is that there are some issues with the data. And here you see the results of the different approaches. And we identify some software bugs to be corrected and some small evolutions of the algorithm to be done. And this is being done right now. Once this is ready, we will unblock the correction and somehow hope to get the results which are similar to the ones of Roman that were discussed in the morning. So to finish, just to say that all the software, or most of the software is supposed to be open source, and if you go to our biopower repository, you find the majority of our level 1 A, B, C, and level 2 source code. And what is not there, you can also download as a Docker or a bundle and run in your computer with your own configuration to get the result that you like. We don't stop here. We are doing the development of the secondary objective processor. So we are developing a DTM, a TomoCubes, and a forest non-forest processor that hopefully will be used to generate the TomoCubes and Tomo profiles and DTM data to the public. That's it. So thank you very much. Please report whatever issue that you find, because this is how we improve our data. So I leave here my email. Feel free to bother me with whatever question, complaint that you might have. And sorry for the time. Thank you.
We have time for questions. Sean?
Thanks. Nice talk, Muriel. You said that in level 1C you're providing the merged cross-polarized,
yeah.
but you're going to change to the unmerged. Why? I mean, what's the extra information you get by having the two separate cross-polarized?
So one of the things, for example, that we saw is that the AR5, for example, is polarized. No? So I think that the hope here is to give as much of information to the user so that the geophysical retrieval can then use this in the best way. Of course, the rationale of having the merge was what you say. No? So I think we expect reciprocity, so we expect that everything works well with the merge and we get a bit of SNR by doing the average. But because of these artifacts, in particular the AR5, we are thinking again.
Another question in the center.
Hello, Professor. I have just using the BPS processor in the GitHub you provide, but I find it seems that there may be like the configuration files and some necessary running files.
Yes, so these have just been published. So if you go to this website that is written in the second bullet here, you can find the full installation of the BPS to install it and use. We have also the Conda packages available, but they are not yet including the missing part that was missing in the GitHub. This will be done in the next week, so that if you do the Conda installation plus your compilation of the available source code, you would be able to run this. For the configuration file, so AUX-PP1 to process level 1, AUX-PPS to process the stack, AUX-PP2 to process level 2, this should be all in the map, all in the data access together with all the data. There is a specific collection which is called Biomass AUX, where you can retrieve all this data, including also the attitude and orbit files which are necessary for processing.
Okay, thank you so much.
Any more questions? Just a final remark. When you complain to Muriel about any data issues, be very precise. Huh? So it doesn't help if you say, I open an image over Africa and there's some strange striping effect. Tell us the frame. we saw a lot of these messages in the past, so tell us which frame you use, tell us which time step you use. Be aware that the IOC data is not perfect, so don't complain of the IOC data. It's not there yet.
Yeah. But the IOC data is also not public at the moment. So the CalVal people have access to it, not the general public. After the reprocessing with the stable configuration, this will be made available to the public. But Klaus is fully right. Please provide file names and a specific description of the problem, because it helps. Good.
Shall we go to the next presentation? Was there one more question? There's one more question. Actually, we have time, so you can...
okay, sorry, just a quick question. When you showed the Tomo schedule, and I read some part of the manual, okay? So I understood that a Tomo stack for a specific site is available once in all the Tomo phase, a single Tomo stack. Why this morning I could see somebody evaluating with the Tomo stacks the scattering stability. There were 2 or 3.
No. So the level 1C data, the stack data is data-driven. So as long as we have complete the 21 days of acquisition, they are processed. So they are being produced right now, and you can find them in the Map Explorer.
Okay, but I mean, in the acquisition for a specific site,
Yes.
given coordinates, in the total mission, can I have one thermostat or more than one?
I can answer if you like. So you get actually 2 stacks because we get ascending and descending stacks,
Yes,
of
but
course.
just one, yeah.
And maybe for this particular example, they were using stacks that were recorded during the IOC phase. So during the IOC phase, we had stacks, and now in the operational phase, we start with new stacks. So maybe that was just a case where we have where we were lucky. Yeah.
Yeah.
You always have it. You always have overlap between the spots.
But in the operational phase, it's one ascending stack, one descending stack.
Oh, okay, thank you.
But maybe the
Thank you,
next tom
Klaus
phase
and
at the end
Clement.
of the mission.
Exactly.
Would you like to have more tom stacks?
So if you want to, if people want to have more tom stacks, the way is you make a recommendation at this workshop, you let us know, and then we will discuss the implications it has, and maybe if we see a chance.
So now we have already 3 recommendations for an additional tom.
Yes.
Good.
Okay.
So, next presentation about level 3 by Laurent.
Thank you very much. So I'm going to present you an overview of the level 3 processor. So it's, as presented before by Muriel, it takes as input the level 2 products and to provide users with stabilized and enhanced quality products by considering multiple acquisition cycles over the life of the mission. So the motivation, the L2B products are geophysical parameters, AGB, forest height, forest disturbance, also DTM could be included in this list. They are processed at the tile level and they're generated every 7 or 9 months. It depends on at the moment it's 9 months. And the output of this processor are product values and also associated uncertainties. And the level 3 products takes the estimates that were produced every 9 months in the life of the mission and merge them together to eliminate some artifacts or at least reduce the importance of artifacts related to variation from one time to the other or spatial variations that are not coherent, that do not agree with basic geophysical properties you may expect from this product. The best example is forest height and AGB, which should follow a given local relationship, and if one point is really far away from this relationship, it's probably wrong if it only happens at one date. Okay. I'm just going back 2 minutes on the processing of level 2B products. They are processed at each global cycle, so every 9 months, and they are made of. They consist of the fusion of several estimates produced at the track level and consisting of L2A products, and these products should be merged. If we have overlapping tracks, and also should be merged between ascending and descending trajectories. So the objective here is to handle gaps, missing data, obviously erroneous values, with a very simple processing, which is based on the data value and also on quality indicators that are delivered by all level 2A processors. One example with the processing of digital maps, so maps with 0, 1, like forest on forest map, and when we have several estimates produced with over different tracks, and how to merge them. So we convert them to a probability of the state of let's say the non-forest state, and we process this stack of probabilities. And once we have a map which is satisfying for us, we then reproduce at the output a digital map with a corresponding quality indicator, which is using very basic statistical steps. Same thing can be done with continuous estimates like DTM, which do not represent binary maps, but more a geophysical parameter value. And in this case, it's much more simple. You can assume a statistics for the data you are considering. For DTM, the Gaussian statistics is reasonable. For forest height, it would be maybe a log normal statistic. And then we can estimate the maximum likelihood merged results by using as you see, a very simple processing. So once we have this, we need to, in order to process and to compute the level 3 products, take L2B products that are estimated at every cycle, and they are estimated on a very local basis, okay? And we don't average over kilometers to produce them, and they are independent one from the other over the time dimension, okay? And the objective of level 3 processing is to enforce consistency between these estimates. We cannot have a biomass which increases or decreases randomly over time. This is not feasible. And in this case, we want to enforce some relationships of space and time. The scale of analysis is a biomass product type, which is 100 kilometers by 100 kilometers, roughly. And of course, we plan to process forest class separately because they may have different relationships between geophysical parameters such as height and AGB. An example, so we have here a model which relates AGB to height, and these are different ways to estimate a value using this allometric relationship. And you see that depending on the uncertainty you have on one parameter or the other, you have different estimate values. And if you also account for the uncertainty of the model, of the allometric relation, then you end up with, again, another estimate, which this time is much more likely to be the correct one, because you took into account the uncertainty of the level 2A product and also on the regression you computed to link the two parameters. So this is done by this enforcement is done over several dimensions by taking into account the uncertainty of level 2B products, of this allometric relationship for AGB and forest height, with some constraints over time, over space. Okay, we cannot have a sudden change of spatial texture or random temporal variations. And the estimation of the level 3 value is simply the value which minimizes a loss term. This minimization is conducted at each global cycle by taking into account all the past acquisitions, and then when you have a new acquisition, it may change your estimate, the estimate you did 1 or 2 global cycles before, because this one could be erroneous, and at the moment when you measure an erroneous value, normally you don't know this, you need to measure values before and after to estimate to improve the estimate quality. And this is done, this optimization, since we assume very simple statistics, log normal, it's done at the end with a very big linear system, but a linear system which is easy to solve. There are some commonly very common solvers. The dimension of the system is really large. We have 30 million by 30 million matrices, but they're full of they contain many zeros, so it's a sparse system, and there are some solvers which can estimate process a full stack of seven level 2B estimates in less than 15 minutes. So it's really reasonable. Some example, a small example where we simulated some errors because unfortunately we don't have, we will need to wait a little bit to produce some realistic and some to process real data. We simulated an error into these are acquisitions or estimates performed at four dates, and on the second one there is an error on this tree height estimate because of, I don't know, an excessive temporal decorrelation. And Maciek, who estimated the AGB, did not make this error because he didn't use this parameter. I don't know. Let's say let's take this as a scenario, and the objective here is to detect that there was an error on tree height at this date and to correct it. So if we run it if we take the first acquisition, we can run the processor, and these are the losses for the level 2B product, the allometric relationship, and the spatial constraints. You see that there are some small errors. Once you run the processor, you have eliminated a bit of noise, and this noise is considered as coming from the level 2B estimate. Okay. At the end, the constraints on allometric and space relationships are completely optimized. And when we ran the processor on the 4-image stack, we clearly identified that the allometric relationship was not respected at the second date, and then we correct it, and we identify this error as coming from the height estimate. And once we have corrected this error and we have normal, non-erroneous estimates later in time, we see that we still identify the error as coming from this specific date. We thought an error at a given date does not perturbate the estimates you do later during the life of the mission. And then you can correct, okay, this is the erroneous L2B estimate, and at the end you see that the map has been corrected because we use this redundancy and the relationship between height and AGP at each date. And with this ends my presentation. I would like to say that we are eager to finally implement this processor on real data, and we will deliver the data to you, and any feedback would be very welcome, because we thought about some constraints, but some of them might be not well adapted, or you may have some specific needs that we will, if it is possible to satisfy, we'll be happy to do it. Thank you very much for your attention.
We have time for a question. If there's no question, everything is clear, we move on. We move on to the next presentation. Now we move to the map platform. So that's the platform where you can access data. I mean, you can of course access our data also over classical ways, but the map is a new way to access data. And the presentation will be given by Roberto.
Hello, good morning everybody. Yes, I will present the ESA map and the biomass map part, and then my colleague Clément will focus on the biopal. First of all, the ESA map offers two different functions mainly. The first one is the data access on your left for accessing all the biomass data, etc., which are, some of them are open and free, and you don't need specific registration, just an ESA account to access them. And then on the right side of the screen, the collaborative environment for users to develop algorithms, run processors, analyze data, etc. And for that one, yes, you need a specific registration. So users can access data, go to the collaborative environment, but of course, from the collaborative environment, there is a direct access to the data, of course. For the data access part, it is composed of a catalog, sort of backend database containing all the metadata of collections and products, and which is compatible with the standard interfaces like Stack API and other, and which can be used from command line, programming, scripts, etc. And then the data that are stored on the object storage on the cloud. And we have a graphical user interface, the Explorer, which allows you to browse and discover all our data. When accessing data and discovering data and accessing data through the Explorer, you can find, first of all, the collections that are available. And then in a second step of the search, you go into a collection and then look for the products and narrow down your search for the products. The discovery is completely open, so no need for logging in, etc. But then for accessing the data, yes, you have to log in. So the top right button, sign in, will be needed for you for accessing the data. It's still a manual access to the data. So we also recommend to go through a scripted way, since most of you are probably familiar with scripts, etc., to discover and accessing the data. The API of the catalog allow you to discover and access single files within the product, not necessarily downloading the full product, and also to streaming the content of the product, so not even downloading it and just accessing it through your code directly or a subset of the product itself. And then, in that case, when you're accessing a product, again, the authentication is needed. So in this case, it's done through a token, which is made available and which you will insert into your code to be authenticated and authorized to access the data. And then your code will do whatever. Here's an example of plotting, but it can be anything, of course. The catalog is compatible with Stack interfaces, so you can also discover collections and products through the Stack, through a generic Stack browser, which is compatible, and you just point it to the catalog endpoint. you find collections, then you find the products within the collection. And just to show you that you can find here, and it's not the exhaustive list, there is much more files into a biomass product, but you can identify each one of the files so that through this interface you can maybe more easily find what are the names, etc., of the attributes or of the single files within the product to then put them into your code to access them directly. Muriel already went through the collections and the data that are already available, so very quickly, L1A and L1B are made available as soon as processed, a few hours after the sensing, and level 1C are made available at the end of a complete SWOT cycle, and the L2A will be available soon after the complete assessment of their quality. And the second part of ISAMAP is the collaborative environment, which is based on the product algorithm laboratory that allows users to implement algorithms, to execute them, to execute processing, to analyze data, as I was saying, etc. And we have generic functions. It can be scaled, of course, and we can customize for different needs, different user communities, etc. So, for example, we already have the biomass map one, of course, that you know, and the healthcare one, so some customizations for both of them. We will have the flex one ongoing, and we can have more of them, of course. The product algorithm laboratory is mainly composed of 3 components. The processing environment, where you execute pre-built processors, and you can execute them at scale over a large number of products, and it's executed in a parallelized way, or you can have a systematic processing, etc., and generate your results. The coding environment, which is more like a Jupyter Hub, where you can insert your scripts and notebooks and execute them to analyze your data or prepare a future new processor and whatever. And the visualization and analytics component, that is a graphical user interface for going more in-depth into the products, highlights some specific characteristics, bands, attributes, etc., with a dedicated interface. And you can access the platform through the main portal, which will show you all the services that are available, and then each of the maps, of the individual maps, will have a specific portal, like the biomass map and the healthcare map that are available here. And for the moment, we have around 130 users for both of them. Most of you probably are already in there, but I strongly recommend you to go to the join button of the biomass map if you didn't already do it, to be part of the community. Just very quickly, not to forget that the map concept at ESA started with the collaboration with NASA on the biomass map. Then today it's a bit a wider scope, as you saw, with the healthcare and with the other functionalities. But the idea was a co-design with NASA. This is ongoing since a lot of time, before my arrival. And the idea is to have a processing interoperability to allow users to execute their code on either of the platform with the minimum changes or no changes, hopefully, and to have also cross-agency data access, meaning that a NASA user can access all our data, and vice versa, an ESA user can access also all NASA data from JEDI, NISR on their side, and Biomass on our side, and we have geotrees data, etc. So that's it for my introduction on ISAMAP and Biomass Map. You have some guides, user guides on the website, so I recommend you to have a look to them for every of the thing that I just presented. There's a poster outside, so in the coffee break I will be nearby, you can pass by, and we can have chats, you can ask questions and whatever. And we have organized a webinar supported by all the consortium that is developing and operating this platform, so with much more technical in-depth analysis and suggestions, and we can answer all your detailed questions there, which is on the 19th of February. The QR code is the one of the news that has been published. If you are already part of the Biomass Map, you should have also received the notification via email, and there will be a new one closer to the date to recall you and give you the links, etc. And otherwise, feel free to contact me or my colleague Saskia, who is not here, but we will be happy to answer any of your questions. And then I lend the floor to Clément.
It's the next slide. It's just the same presentation. Thank you, Roberto. So you saw this concept of map. You heard before in Muriel's presentation the concept of biopal. But before, I would like to introduce the DISC team, as it was a little bit introduced before. So it's part of the grant segment. It's responsible for the mission product quality and algorithm evolution. And the team is tasked with ensuring that the data which is processed is transformed in accurately calibrated and validated data. So it's calibration of the sensor and processing chain, validation of the data quality, and evolutions of the algorithm. We need to ensure that the product are really following the state of the art, the best that we can do. You have a lot of companies, you see, Acri, Politecnico di Milano, Aresis, DLR, CNRS, SBU, SNT, Wageningen University, Chalmers, DTU, GFZ. The team is organized with different PIs, you can see on the bottom left, plus scientific experts working on the different topics from the instrument calibration, validation of the data. For each product level, we have a PI and we have a group of experts, and also for the secondary objective that you can see on the right. In the composition of the team, I would like people who are members of the DISC to raise their hand, because I think that today we have quite some people. You see, Costas also, there are some people that are shy still. In the team, there are 56 people, so it's quite a large team. We cover really a lot of different type of profiles, and many of the people could not come today. But it's really to represent, to try to encompass all the different aspects that are needed for the mission. As Muriel was saying before, we have an open source processor, not fully open source, but the objective in the middle longer term is to have it completely open source. And this concept of biopal is relying on 3 pillars. The first one being the open source processor. You can find the source code on GitHub. It's accessible. Anybody can get access to it. And if you want to contribute, on the DISC website, actually, you can find some information on the mission. The quality disclaimer that Muriel was saying before, here is just working in progress. You can see a lot of fields that are still missing. We're updating them. And the idea is to have this complete in the next days, next week. And you have a part on biopal. And there you can find all the information, how to contribute. From what should I do if I found a problem in the data, to how can I contribute to improve it. Because we don't want to have 2 people working in parallel on the same thing. People should work in a coordinated way. You have also a code of conduct, how to behave when we work together, what can be done, what are, let's say, the procedure to be followed. And at the bottom, you have some documentation, and you have a link to the GitHub where you find the source code. So there you have the BPS, but you have also additional source code. The idea in the future is to publish additional open source codes that can be used by the community. You can get access to documentation, how to install it, how to run it, how to compile it. And you can, of course, just get the access to the Git repo. Then the Biomass map platform was presented before. So the idea is that you have all the mission data there, the possibility to visualize data, but also to process data. You have really an environment where you can edit the source code, and it's supporting open source. It's supporting also your intellectual property. If you put some information and belong only to you, they will be kept there. And the idea is to connect the source code that we saw before to the platform itself. If you go on the map platform, you have these PAL tools, and one of them is the coding experiment, the coding environment, where there you have access to data, but with the terminal, the map is also connected to the different standards, and you can, for example, just do the git clone and paste the address that we saw before, and in a few seconds you will download all the source code, the latest version. We need a few seconds to refresh it, but then you will have access to the source code of the processor which is in operation. You can compile it, you can modify it, you can do a pull request. It's really the standard Git approach. On top of that, you have on the map platform not only the input data, but also all the additional information, the DEM, geophysical model function, the international reference ionosphere, and some Jupyter notebook to show you how to open the data, how to get the data, because you don't need to download all the product. You can just get part of it, the measurement, for example, how to get all the information to have your processor running. And the third pillar, which is geotrees, that will be presented more in detail later on by Jérôme, I think this afternoon. It's a collection of permanent, well-studied and locally supported sites, open sites, that aims at supporting the Calval of the biomass, but also JEDI and NASAR missions can also be open to other missions dealing with biomass, like ALOS, for example, or SAOCOM. Site for validation must be extensive, cover a range of forest type, tropical, temperate, boreal. You have some requirement. You need at least 10 1-hectare permanent forest plots established, 1,000 hectares of airborne LiDAR scanning coverage, capacity for TLS, capacity to remeasure plots, additional information like weather, and it's following at the bottom. You can see the CIOS guidelines that were defined a few years ago that allow that if you collect the data following this guideline, you can apply them to any mission deriving biomass products. So it's really something transversal. It's a big collaboration. You will have more information this afternoon. And the idea also, which is this biopal concept, is to start with first definition, first implementation of the algorithms. As you can see before, you have the possibility to get the source code, to use them, to compile them, to process the data, because the map platform or the data is already there, to generate a new data set, for example, your own data set, to use yourself as the geotrees data will be open, the validation procedures will also be open and provided in the map to validate the AGBD product, for example, that you generate, and to compare it to the ESA one. And if it's better, you can contact, it will be the DISC team that will do a cross verification. And if your improvement is valuable, improvement is really an improvement, it's compatible with the generation of the data that we have, it will become the new baseline of the mission. And this is super convenient because it's made within the map platform. So we already have all the input data, everything, which is quite large. So it's easy. You have already some templates. So the objective is to roll faster to stable algorithm, which is very important for mission like biomass, where we have only a few years, 5 years of mission. We want to have good data earliest as possible, to have this good data being able to be used, for example, for some carbon modeling or for higher scientific use. And the second benefit is that anybody outside of the core science team can contribute to the product improvement cycle. And Biomass is the first mission to allow to do that. All the mission we have until now is only a small core science team able to access the source code and to contribute. And every PhD student, postdoc student, anybody can access the code and contribute to that. It's very well adapted to R&D mission like the Biomass mission. So as a conclusion, the map will make the connection between the data, the algorithm, the software, and the results. It will bring together data from various spaceborne missions, various organizations to support development of global biomass maps. We could see that geotrees, biopal, and this concept of product algorithm laboratory will make it easier to reproduce results and build from existing work. Biomass will be the first, let's say, open source Earth Explorer, thanks to all this open data and platform. And this concept of map will become the baseline for the future ESA missions. You could see we have EarthCare, which is going in this direction, Flex, knowing that from Flex also you have also open source codes. So all the future missions will follow this approach. Thank you.
Thank you, both of you. So questions to both of them. Aki.
Yeah, thank you. Very nice setup. I was just wondering how, in terms of capacity, how much, say, memory are you kind of allocating per user? So how large areas can you as a user kind of process at one time? Is it kind of one scene, or can you do kind of regional scale processing kind of at one go, or?
So there are two ways to process the data. We have a kind of on-demand functionality where you can use like the processor almost as a black box. You pick the inputs and you generate the outputs that can be useful. For example, as Muriel was explaining, we turn on the RFI correction over some areas only, and maybe you want to turn them off or turn them on over other areas without touching anything. You can just pick the data, change, let's say, the flag, the parameter you want to change and generate the data. And the other place is where I was showing, where you can develop. And then, so we have default configurations that are quite small, but they can be increased. This is completely new. It's the first time we do that, so we are going a little bit in the void. We'll adjust a little bit everything. It will really depend of the needs and of the use case you want to put in place, and then we'll judge. We can allow more resources for special cases.
Yeah, because I mean, if it's one thing to have it as a research hub, and another one to be processing a little bit more data. I mean, it's time stacks of data basically, so it's quite processing intensive. Could be. So yeah, just a comment. Yeah,
it's not possible to allow everybody to generate global tomocubes.
No, but still, I mean, most people are working regional, right?
And when people are happy, if we want to extend it, then we discuss a little bit together to see how to do that.
Great, thanks.
If I can just complement quickly, technically the limitation is the one related to the public cloud on which the platform relies on, which is pretty large in terms of available machine nodes in the cloud of RAM and CPU, etc. The starting setting has been set. We decided some standard setting for the users, but it can be adapted. So your comments on maybe too restrictive environment, etc., are more than welcome and justified, and we can adapt and increase, of course, depending on your needs.
If you need more, contact us.
Okay.
One more question.
In PPT, you say the GeoTrees. I want to know how can I download the GeoTrees date and when it will be published in the website. Thank you.
So the website is published, but the data is not yet there because it's collected and it's under being processed. And I think you should add this question to Jérôme. Maybe he can try to answer now or in his presentation, because he has a presentation this afternoon, I think early afternoon.
Okay, thank you so much.
He will go much more in details. It's work in progress. I don't know exactly when the first public data will be available. But it's on the website that I was putting in my presentation. You can find it easily.
Maybe we keep this question for the presentation of Jérôme in the afternoon, and we move on to the next presentation.
Yes, well, the final presentation of the session is about the biomass, what it is, this product algorithm laboratory, PAL, and it's given by Herminia de Grandis.
Okay, good afternoon, everyone. Yes, today I will give more details on the PAL, that is the Biomass Product Algorithm Laboratory, and it is a collaborative working environment within the ISAMAP framework. I will start giving you some context and a brief introduction to the PAL, and then I will go through each component, the coding, processing, and visualization environment of the PAL, and I will conclude with a summary and some final remarks. Okay, let's start. I will not spend much time talking about the ISAMAP because it was presented by Roberto and Clément. This slide is intended to introduce the PAL as a key asset of the ISAMAP framework. It is a collaborative environment that is instantiated for each initiative and is tailored to each initiative requirements. Currently, the identified initiatives are Biomass, Air Care, and Flex. The idea that is behind the PAL is to provide user workspaces where the developer, the researchers, can experiment with new algorithms, prototypes, scale them to enable analysis at global level and over long time series, and sharing the results and the new algorithms within the community. So this is the landing page of the PAL, as you saw before. The user can access the three components. And the idea in this presentation is to describe each component following the step that a user has to follow has to perform to integrate a new algorithm as a new service in the PAL. So we'll start with the coding environment called experiment, where there is a coding environment, and then we will describe the processing environment called intellect, where the the algorithm is published to the PAL registry, and the associated service is created and then executed. And finally, the user can visualize, analyze the all obtained results in the last component, the visualization and analytics component, also called perception. Okay, let's start with the coding environment. It's based on Jupyter Hub, with integrated Python and R tools. At the startup, the user can choose different environment, different working environment on the top on the right. These environments are depending on software, tool, and data available. Overall, the service within the initiatives are organized by user type. This means depending on user role and the allocated computational resources, let's say. In the Jupyter Hub, in the coding environment, the users are provided with a public and private storage. This is to foster the interoperability within the working group. And in addition, by the coding environment, you can access the output of your job, also the job of the other users, the processing outputs jobs, coming from the processing component, and also all data uploaded by the user that could be external data set, auxiliary data, or something useful for Carval activities, for instance. This is also to highlight that the two components of the PAL can exchange information and can interact with each other. So from the coding environment, I can access the information in both environment, the processing and visualization component. Okay, in this slide, I would like to try to explain how to integrate an algorithm as a new PAL services and execute it as an OGC application service. This means that the service is exposed as a web service and can be accessed remotely by HTTP call. Regarding the stage in and stage out mechanism, as I said also before, we implemented a stack catalog. It means that when the job is running, instead of using a direct link to a specific product, reads a JSON file, input JSON file, which contains reference to the product and to its metadata. And with this information, the processing can download locally the input products that could be accessed by the process. The same mechanism in the stage out phase. This is to highlight that the implementation are compliant with these two standards, the OGC and the stack, that ensure the portability and also the interoperability. Below, I try to schematize the step in this workflow where we start from a coding environment that could be the PAL Jupyter coding environment, but also could be a local PC where the user can experiment the algorithm, the single process, and so on. And after this, it can scale the algorithm in the infrastructure, and the application is being built from a Git repository. So the user has to push the Git project, let's say, with the Docker file, in this GitLab repository, PAL GitLab repository, and this will trigger a pipeline that automatically will build the Docker image, perform some additional steps such as a security scan, but will publish the Docker image of the algorithm in the registry. So once the Docker image is in the registry, the user can, using a zip file which contains information on the workflow in terms also of input and output, can create a new service in the PAL. So here I recorded a demo where I want to show you once you have created a new service in the PAL, you you can execute it. And there are a lot of ways to do it. So we go in the processing component. And first, I show you how appears a new service created in the PAL. So this is an example. We have some information on the processor, the storage required, the computational resources required for its execution, the SQL file I just mentioned, and then the input and output definition, and the additional amount if the processor needs additional external data set. We can process the service in two ways, in standard and systematic processing. In the standard processing, we can give as input a single file or multiple files to perform a bulk processing. And you can select from this catalog, from the ESAMAP catalog, and you have a lot of parameters to set the collection, but also the product. In this case, we draw area. And yes, we select the product, and this is the product, and I can execute the process. Here I can decide where to put my output. And then same mechanism for the parallel processing, but the difference is that in this case, I can choose multiple products from the same access of the catalog. So in this case, the user is able to select multiple products. And in the same way, I can execute the process. As you can see, there are the selected product. And then the last way to execute the service is the systematic processing. This means that the user can define at the beginning a set of input parameters or conditions to select the product he wants to execute. So here we have a temporal window where I decide to process all this product. And as you can see, in the input directory, we have the condition of the product to run this systematic process. So we can also monitor the process. This is the case of the single process. Here you have the different phase. The output file, you can download from there the output file, and you can, yes, monitor with the logs files. Same monitoring interface, but in case of systematic and parallel processing, obviously you have a list of sub-jobs associated to each product you decided to process. So this is the systematic one, and also in this case we have the list of sub-jobs. So once you execute the service, you can visualize your output, and from the processing environment you can go in the visualization and analytics components. This is the next demo. Here you can perform the data discovery. You can access also the ESAMAP catalog, but also the output you just created. In this case, we want to visualize the level 2A biomass product, the forest type. So in this case, we select the window. And with the Add to Map button, you add your product in the map. You can zoom on it. And there is a lot of functionalities to interactively visualize the product, such as the swipe tool, and also the opacity control, the color scales. You can change it, and you can also adjust the range values of your products. And you retrieve the local information of the product. You can also perform some statistics. In the first case, you can draw or input as a vector file an area of interest. In this case, we decided to draw two areas to compare the retrieved output. So this is the second area. And by applying this selection, you can see the output, and moving the mouse over the bin of each histogram, you can retrieve some information. And also below, you have all statistic value calculated. In the second case, you can monitor the spatial variation along a specific direction. Here you can decide the sample distance. And also in this case, you have this information that could be useful to identify along the direction trend, gradients, or some anomalies in the selected product. So yes, all results can be exported in numerical and graphical format. As a last demonstration, we would like to show you the 3D visualization capabilities of the PAL in view of the biomass tomographic data. This is a proof of concept. So we use the meteorological data to study these events. The Medican Apollo occurred in October 2021. Here you can see that in the horizontal dimension there are the wind vector, the eastward and northward, and in the vertical dimension we have the pressure level. So also in this case we can draw a specific area of interest to look at the center of the event. And yes, in this case, we have also a fourth dimension. This is the time dimension that allows the evolution of the event. Okay. Yes, and there are different ways to visualize this output in a grid mode or also with associated histogram and so on. A lot of functionalities in this interface. So, coming to the conclusion, I try to present to you the PAL, to go in details with this environment, and to present it as a collaborative environment that promotes active participation in the platform's growth. So as you saw, the user are enabled to contribute with new algorithms, data, but also sharing their results within the community, within the working group. I go through different components. I try to give you some much details. And yes, I like the fact that this infrastructure is designed to be scalable and portable with the compliance with these two OGC and stack standard. And as demonstrated in this last demo, it is fully operational and it is ready for you. We are working actively to expand this platform with new processor and dataset. And yes, we would like to start developing some notebook example for you in order to promote the platform, but also to foster the biomass data exploitation. And as mentioned before in the previous presentation, we are organizing a webinar, but also we want to provide some tutorial, again, to enhance and ease the platform usage. So that's all. Thank you for your attention.
Thank you very much. Questions for the last presentation?
There's one here.
Thank you very much for this presentation. I was watching your presentation downstairs with the poster session, but now I understand much clearly. It is very important to follow the OGC standards and the CVL infrastructure, so it's quite understandable and easy. But my question is there any special activation needed for the map account to be able to do this? And is there a playground and is there a quota limit that I can use?
Thank you for this question, because I forgot to say that, yes, this kind of workflow was successfully tested on development environment. We are working actively to make it automated as much as possible for the users. And we would like to make it operational within February. So it's a good point.
Thank you.
Thank you.
Is there another question? And maybe for me, a comment. So if you're using this platform, if you're missing any functionality, if you have any way to visualize your data that you would like to have also on the platform, or any other way of doing analytics or analysis, let us know. And we can try to get it on board. So this is really a thing that is currently in the doing, and we learn every day what you need and what you might not need, maybe.
Last chance for you to ask something.
Okay, then we can.
Okay.
I felt the pressure. I had to say something. No, I was just wondering then, can you import other data sources and work together? So.
Yeah, sure. There is this functionalities in the visualization environment, but also in the Jupyter Hub, you can import any kind of external data set, auxiliary data, and so on.
What format should they have?
What, sorry?
What format should they be in?
But to be visualized?
Yeah.
So far, I think the TIFF format, for sure.
So GeoTIFF.
Yeah.
Okay.
Okay.
Thank you.
Any other last question? If not, then we can close this session.
We can close, but we have a few announcements to make, so you don't get away that easily. Huh? So, Costa's announcement. No, so can you display the slide of the training course? So already over the last years, Costas and his team were organizing Polinsar training courses, which were very successful and very useful. So if you want to learn about SAR processing and really going from the focusing of a SAR image up to tomographic processing, this is the course to take. It's quite intense, so it takes 10 weeks, but it really brings you from zero to an expert. The next course will be starting on the 13th of April this year. We will in the next days open the registration, so we can only accept, I think, up to 40 participants per course, because it's very interactive. So keep an eye if you're interested, or if you have one of your students that might be interested, keep an eye on the ESA website, and you can register. This one will be, I think, particularly exciting because you can start working with the biomass data. So it's a really nice opportunity. So that was one. Second announcement, to provide feedback. So we ask you several times, please provide feedback to us, how we can improve. Also, if you have any suggestions, how to improve the missions, or any wish, even if it might sound bold, like do only tomographic acquisition and skip all the rest, or do only single image acquisitions. This is the place to place this, also this workshop is the place to make these recommendations, and then we will digest it at ESA and see what we can do. To help you a bit with this, we have set up a Padlet, so you can link to the Padlet and you can put in your comments, you can make this anonymous or non-anonymous, and we will review this also on Friday. We have a discussion session on Friday to close the workshop. We will have a look at the Padlet and see. The QR code you will also find on the website, so if you have not taken a photo now, you can go to the website and access it there. For the afternoon, we will split in two groups, so the land presentations will be in this room, in the red room. The biomass Calvai stuff and biomass modeling aspects will be down in the purple room. And with this we will close more or less the biomass one, but it's not a complete close. I think during the last 2 days we focused a lot on the primary products, and we labeled this as biomass first results. But there are many more results to be shown over ice, over land, over ionosphere, and these will be shown on Thursday in the dedicated ice and ocean sessions and land sessions, geology sessions. So there's more results to come. And with this, I think we can now really close, and you can go for lunch and be back at 2:10.
co-chair this session with Maxima, which is actually the first presenter. And this session will be about biomass campaigns. So I'm pretty sure that after this one, you will be also convinced that we still need campaigns even after the revolution. So the first presentation will be title is a bit long, so I'll let you put you question mark. The floor is yours.
All right. Thank you very much. So we're going to go through 35 slides in 15 minutes, so I hope you're awake and not too sleepy yet. So this is about the CalVal campaigns that we conducted in a few last years and the ones that are coming up this year. We'll be focusing on radar, of course, and Polinsar and Tomosar activities that we have during those campaigns. So the first one we had was the AfriSAR campaign. That was in Gabon in 2016. Here's one of my favorite pictures with my 3 favorite instruments. So we have FSAR with the dual band, Elvis, which is a LiDAR, and UAVSAR, which in this campaign we flew at L-band. So that was in 2016. This involved a lot of diplomacy, signing agreements, so that it was a long process to get all that done, but we really did succeed doing that, and gave rise to the new campaigns that we're activating nowadays. So there's a lot of people that are involved, not only on the aircraft, but also on the ground. You know, we have to bring along the pilots. Along with the mechanics, a lot of field people measuring trees and different aspects of the campaigns on the ground. So it's literally a lot of people. So in this picture here, we have some of the team. So from DLR, ESA, and JPL. So in 2016, this is the coverage from UAVSAR. So you see the radar images in the background here. The red lines that you see are the coverages from Elvis. So again, just to let you know, so Elvis is a LiDAR. So the density of LiDAR pulses is enough so that we can make images, full images, which is very nice, very different from what we have from space from JEDI. Okay. All of those data are on the web, accessible to anyone. Some of the sites were covered in Polinsar, multi-baseline Polinsar, and Tomosar mode. These are the sites we covered in 2016. So Monda, which is a secondary forest, Pongara, which is a mangrove forest, one of my favorite sites in the world. That's where we find the tallest mangroves in the world. Rabi, and also Lope. So this was a very highly successful campaign. This list, non-exhaustive list of papers, we were at, as of mid-2024, at 82 peer-reviewed papers. So it's probably 100 by now. So this, for us, this is how we see the value of those campaigns, and this is how we can sell to have more of those campaigns in the future. So this is highly fruitful technologically and also scientifically. This paper here, led by Lola Fatoyimbo in 2021, kind of generalizes, summarizes the campaign. If you want to start and understand this campaign, you should start with this paper and then go down the list of these 82 papers that we've made. So, and you can see here, this is 2021, the paper, and we're talking about current and future spaceborne missions. Actually, future is now current, which is quite exciting. So we had so much fun, we decided to do it again. So we had AfriSAR 2, which was mainly focused, again, on Gabon. So DLR went first with FSAR, and they call actually the campaign Gabon X because they focus on Gabon. They covered the same sites as was covered in 2016 with both L and P again. Elvis was also there again in 2023. This is the coverage. So you can see here in yellow are the 2016 lines, and the red ones are from the 2023 lines. So it's much more extensive in 2023. We even went all the way to the Republic of Congo in this case. Again, all that data is available on the web. Just click and download. So we went with UAVSAR twice, not once, but twice again, because we went this time with both L and P. So we fly on a jet, and we have one pod at a time. So we came with P-band, went back to Los Angeles, and came back with the L-band in Africa twice. This is the coverage here. We started with Ghana, which we only covered in P-band. Then we flew to São Tomé. This is where our base of operation was. And we flew all of these lines from São Tomé, extending all the way to the Democratic Republic of Congo. We were quite excited to get permission to actually fly the region. Some of our lines you will see also are overlapping right on the border. That is because we were super interested in the peatlands and the Congo, the Cuvette Centrale, the basin there. Some of those lines are single pass. Some of them are just 2 lines for Polinsar, multiple baseline, and some of them are Tomosar lines. So here is a summary of these coverages. This part is in Gabon. You see the small yellow squares here are the FSAR coverages compared to the UAVSAR coverages, both at L and P. So we covered the same sites, so it's possible to compare the different sensors, those regions, although it's a year apart, right? Here's an example of these images in Pongara, the Pongara National Park. So you can see the Como estuary here and the mangrove forests at L and P-band. So you have some striking differences and a lot of details that come out at P-band as it penetrates more into the canopy. This is a zoom in to this same region, this time with FSAR at the top versus UAVSAR. Some of those lines are in Tomosar mode. This example here is from the Pongara National Park, so the mangrove forest at both L and P band. In the background here, that line that you see here is GLOW 30, so from TandemX, which is an indication of the top of the canopy here. So there's no topography, right? So the mangroves are at sea level. So what you see here is all canopy height. So we're doing very well here at L and P band. Here are some other examples. This is over Monda at P band, at HH and HV polarization. So I'm not going to go into the details of this. Actually, the methods that we're using are will be presented tomorrow by Richard Chen, which is in the back over there. So tomorrow you'll have more details on the methods that we're using for Tomosar. So this one is another area, so in the peatland. And you can see at L and P the striking differences. So P really brings out the features of the hydrographic network. So you can expect that some of these features will come out also with biomass. Here's an example of retrieval from multi-baseline Polinsar. This is the basic technique that we use. This paper is from 2018, so we've been improving it a lot using even neural networks to choose baselines. So we've been improving the method, but this is the basic method that we're using for the multi-baseline Polinsar, if you're interested. So we get fairly good results for canopy height. It varies between 2 to 5 meters, depending on the sites, depending what technique we use, and so on. And well, we have different results. We're also looking for sub-canopy topography, which for those interested in hydrodynamics is very important. So here are some of the results. Here I'm focusing, I'm bringing your focus here to the YX standard deviation. So this is the standard deviation perpendicular to the line. The reason we should look at this is because as we compare the retrievals from UAVSAR to the LiDAR, we have to keep in mind that LiDAR is not perfect either, right? So these are results from the UAVSAR Polinsar retrieval, so RVOG just getting the intersection of the ground versus Elvis. They're fairly good, but 7 meters, 6, 7 meters is not great for if you want to do hydrodynamics. You need to get much better than that, but at least those are preliminary results that show that we can actually retrieve subcanopy topography. And as I mentioned this XY standard deviation, this is, Richard actually did that yesterday. So the results I'm showing you are using Elvis, right? So Elvis has a very dense pulses enough to produce images. If you use JEDI, they're just points here and there. The results are definitely not as good. And if you compare JEDI versus Elvis, you can see that even between the LiDARs, there's a very large error on the order of 10 meters. So LiDAR is not perfect either. So when you compare, just make sure that this is also understood. More results, so UAVSAR and Elvis data fusion for Lope, Pongara, and Monda. So as I mentioned earlier, so we have about 3 to 5 meter canopy height error. And this is comparing L and P. So we have similar results depending on which site one or the other may be better. But we're currently analyzing this data. So when I say we, it's basically Richard. So, and 1 day a week, basically. So it's very, very slow. The progress is very slow. So please hang on. Okay, so again, Monda, Pongara, and Lope, but this time with FSAR. This is Lope and Monda. So Monda, you see the results are not really good. We had some problems with geolocation, but we still get pretty good results also with both L and P using FSAR. Okay, so now we're here. We have Biomass, we have NISAR, and we have JEDI, all at the same time. So for those that are old enough, you may remember Desdini in the early 2000s. So I was working on Desdini, which was a mission concept using radar and LiDAR together. Well, we have it. It actually works. We made it. 20 years later, it's like Biomass. So if you have ideas for missions, think about it now, because it only happens 20 years later. Okay, so this is an area in Ghana. I don't have access to all the commissioning phase data from Biomass, so I saw lots of presentation with Lope and everything. You're lucky. So we have only one site where we have both UAVSAR and Biomass right now. So I'm just showing you one little example. So this is in Ghana, a site with some features, the different forests generate cuts and regeneration stages. So this is a visual image. This is the UAVSAR P-band. And this is Biomass. So the resolution, spatial resolution of UAVSAR is 5 meters with about 60 looks. So you can, of course, expect a lot more details with UAVSAR, but that type of data set will be very interesting to understand the impact of spatial resolution on the biomass retrieval. Okay, so we're having so much fun, we're just gonna go again. So we called it Tropisar 2026. I didn't know there was a Tropisar, so I don't know, maybe we'll change the name. But so this is our NASA's Tropisar 2026. We're gonna go there in Panama, Peru, and Colombia. The main objective is for Calval of NISAR, but we've added a few sites with Tomosar collections for biomass. So these are some of the biomass lines that will be collected over different sites that we're collecting UAVSAR data. We are going to Panama, of course, for biomass. It's not important, but here we have AVRIS data that was collected last year for the Avuelo campaign. So we're just supporting that Avuelo campaign with AVRIS NG. But we're gonna go this time all the way to Peru with 2 sites in Colombia. One of them over the Amazon River in the Amakayaku National Park, where we collect Tomosar data, and also in El Choco, which is on the Pacific coast here. And we are also collecting a Tomosar line here. We're still in discussion between Los Amigos site and Tambopata, so we're unsure yet. Those are the biomass collections with the UAVSAR transects overlaid. So we tried as much as possible to cover some of the sites that are of interest to ESA, that include the GeoTrees site. So we really want to have 100 papers again on this campaign. So we wanted to use that data and publish with it. So we're trying to cover as much of the different themes of the biomass campaign, which include, as I said, GeoTrees. We're trying to synchronize with the biomass tracks. And we have some conservation units, and wherever there's field and LiDAR, we're trying to collect data there. So this is the Amakayaku site. The plan here, actually, it's a racetrack, so we go down, back up, and there's some overlap with opposite headings. So that's going to be very interesting to compare the KZ aspect of the Tomosar retrieval in that national park. The other sites for Tomosar are Los Amigos and Tambopata. So we were trying to do a loop here, but the 60 kilometers that separate the sites make it very hard to do both. So we're trying to figure out which one we'll be doing for this campaign. So again, we're going there with L and P band. So we fly there, collect data with L band, go back to LA, and come back with a P band later in July. So it's May L band, July P band. Quibdó, so that's in Choco in Pacific Colombia. This one is really interesting because of the very high biomass that you find there, which can be around 400 tons per hectare, 500 tons, but it also has a very large topographic gradient of about 3,000 meters. So that's going to be very interesting for retrieval of canopy height and biomass in these types of very steep environments. It also has some flat areas, some mangrove forests, so it's very diversified and crosses several of the biomass transects here, which are also collected in 2026. All right, so I stop here. And I don't know if I have time for questions or...
Yes, I think we have time for us.
Okay.
We have 2 minutes. So yes, I'm sure there is plenty of questions, but yes, we have time for 1 or 2.
I know it was very clear.
But then
yeah, now? Okay. So thank you. The question is a bit like science fiction maybe, but would you think it would be possible to use biomass as transmitter and UAVSAR as a receiver and do some kind of bistatic, or it would be too difficult to process and just not making sense?
That's a pretty good question. I don't know if I don't even know if the bands are the same. Maybe Richard would know more, but yeah. So one of the things we will be trying is to fly simultaneously with a P-band biomass overpass, so we can look at atmospheric corrections or atmospheric effects on the biomass mission. But we'll try our best, but it's going to be pretty difficult.
I understand.
That's one thing we'll try to do.
Okay, thank you.
Okay, thank you.
Okay, so now we move to another Tropisar 2 campaign.
Another Tropisar campaign, yes, thank you. There is no license on Tropisar name, so you can use it again. So there is only my name, Jean-François Nouvel from Onera on this slide, but I have to acknowledge, of course, all the team for the airborne data collection at Onera. Next one. What? Oh, thank you. Next. Yes, thank you. So to start some words about the biomass mission itself. So a lot of things have already been said about it. It's for sure a game changer instrument for the carbon cycle monitoring, and we will have very awesome results with this very nice instrument for sure. Now I'm going to fly much lower altitude and to present the SETI SAR platform. It's a multi-band sensor that we operate since 2007, so it's a long story for now. And one of the very first grid campaign with this sensor was the first TROPISA campaign that we have flown on the French Guiana in 2009. As you can see on this picture, some parts of the instrument is into the cabin, into the fuselage. You see it on the top left picture. And the other parts, and mainly the RF antenna and the power amplifier, are embedded into, accommodate into the underwings pod that you see on the picture in the center. And here are some view of the inside of the pod for different configurations. Main ones for TROPISA are the top configuration. On the left, it's X and L band sensor, full parametric for both. On the left, you have the horn antenna for the X band, and on the right, the patch antenna for the L band. And on the top right, it is a low frequency, so VHF, UHF sensor with a dipole antenna. And this frequency includes the P-band, but not also. It is ranging from 220 megahertz up to 460 megahertz for this antenna. And the bottom configurations are some example with the X-band of X-band sensors. On the left, it is dedicated to long-range operation up to 100 kilometers. And on the right, it is for nadir-looking configuration with digital antenna. A lot of numbers, but just to say on this one that the aperture for the low frequency antenna, is very large with 70 degrees in elevation. So we have to deal with it. It's due to the size of the antenna that is limited by the volume available into the pod, and the frequency that is very low, so the wavelength is large, and so the antenna aperture is large. Anyway, what is very interesting is that we have the full parametric capacity, both for P-band, L-band, X-band, with possibility of range of acquisition distance up to 10 to 15 kilometers, depending on the configurations. With this aircraft, another interesting feature is that it is certified on an airworthiness point of view by EASA, so we can fly on very different countries, and in the past we have flown in Norway, in Sweden, in Tunisia. I will show you some picture after. Of course, in Gabon, in French Guiana, and in Spain, for example, and it is still ongoing. Another particularity for this platform is that it is not for operational use, I mean, not for an industrial point of view, but it is for, we are a research organization, And this system, this platform is still constant evolution. We have upgraded a lot of things since 2009. For example, the inertial system is totally new today. The way we are generating the signal, we are recording the signal is new also with the use of more and more digital device. And we are happy for this because we have a system that is now much lighter, much smaller, so easier to integrate, easier to use. And also a good point is that it allows us to have still better signal quality, also a more accurate trajectory, both for the pilot, with the trajectory is to follow for the data collection, but also for the processing of the data, the SAR data. And global point of view, we are still looking for a better robustness and for a more reliable system in order to be sure that when we are flying, we will go back with a very useful and very interesting signal. Some pictures about different band and different polarization. So this one is from a campaign we have flown in Spain on 2017, full polarimetric. And what is nice is there's a difference of colors of polarimetric behavior into the different fields that you can see on the right. This is some fields for agriculture, of course, and you can see very different color from one field to another. This is for L-band, and this is for X-band and L-band also. And you can see, for example, on the top right of those two figures, the difference once again in behavior for the patch on top with a very different behavior and polarimetric point of view. And this one is with the 3 frequency bands that we use for most of your data collection, with the UHF band on top left, L band on bottom left, and the X band on the right, with the high resolution, about 20 cm for X band. So we can see a lot of details in this urban area, for example. Once again with full parametric mode, and this one is in poly decomposition. Now back to the vegetation and to Gabon for this one. This is a well-known image. We have seen quite the same yesterday, with the primary forest on top and secondary forest on the bottom part of the image. We flew over Gabon on 2015 for ESA. We have flown 7 flights at that time. And for Tomosar and also Polinsar applications. An example of retrieval with for the forest height measurements using Tomosar, and a very good fit between the LiDAR reference and the measurements we have done with the Tomosar. Even if LiDAR is not perfect, it gives a reference to compare with, and we are happy when the fitting is good anyway. And then back to Guyana for the next campaign. We are just preparing. The definition is ongoing. In 2009, the 2 main areas for the data collection were Parakou and Nourag. And what is very interesting is that some ground truth was acquired in the same time with in-situ measurements that were available at that time. And what is very nice is that there is still some ongoing measurements on those areas, so it will be very interesting to have once again data on those 2 different areas, and it will be the priority, the first priority for us for the next campaign. So it should happen on March next year, March 2027. So for sure on Parakou area, and we plan also to fly over Nourag and and maybe above the cow area also for mangrove, measurements of a mangrove. And some ideas for this campaign. So one of the main objectives is to acquire data for Tomosar application and to be able to fly simultaneously with biomass, following ascending and descending trajectories. So the idea is to fly every 3 days, the same plannings and for biomass. Over Parakou and Nurag, as I said, because there are very interesting sites with ground truth information, and over Nurag with more slopes, higher topography variation, and also local instrumentation with a Tropiscat experiment that is recording data on this site for years now. And also, an idea is to perform exactly the same measurements than we did on 2009 to be able to compare between the two data sets. Of course, the coherence will be very low on this 18 years time difference, but it is a unique opportunity to analyze such data with a so large difference in time between the two acquisitions. And as I said, if we have time, we plan also to fly about the mangroves. It has been done on 2009, and once again, I think it will be interesting, if possible, to have the same measurements next year. So this is the possible campaign flight definition for the campaign with different baselines with 10 meters variation from one line to another in order to be able to perform the Tomostack with those data sets. On this one, we have 14 scientific tracks over Parakou, and in addition, 2 tracks dedicated to calibration close to the airport where the aircraft is located. Calibration to perform the radiometric calibration of the signal and to be able to carefully manage the signal quality that we will provide to the community. This is a typical flight for about 2 hours of flight, so something we can perform with the Falcon 20 with a conservative basis. Some lessons learned from the previous experiment. At that time, in 2009, we had some failures into the equipment due to the temperature, to the humidity, mainly about the humidity level. It's very high level of humidity there. Another lesson is that it is important as possible to fly by the morning to benefit for a more stable atmosphere. By the afternoon, it is often raining, or we have much more clouds, much more turbulences, so it's very convenient, very more comfortable to fly by the morning if possible. Typical information is we are to be aware of the magnetic deviation that is very large in Guyana. And when we set the calibration, is mainly for the ground, for the calibration devices we will install on the ground. The setting is tricky, and we have to be aware to this magnetic deviation. Some words about the DEM. At that time, we were using the SRTM data and ALTOA data to perform the DEM, to have the DEM for the ground projection. This time, I think we will use Copernicus data, but this is still something we have to define. And as I said, we have this time a very new inertial sensor with much accurate measurements, and it will be much easier to process the tomogram, from the data. It was somehow tricky on the last experiment, but for this one, it should be much easier. This slide just to say that, as Mark said previously, to perform some airborne data collection is not an easy story. It's not just only to take off, to record data and to land. There is a lot of works to be performed before, to validate all the system, to get everything ready for the experiment. Then we have to organize the freight, the handling of the material from France to Guyana. And for example, for some devices such as the ground calibrator, it takes 2 months to go from France to Guyana by boat. So we have to take this into account, and don't go into the details, but there is a lot of stuff to do before to be able to record the airborne data. Now some words about the secondary objectives. This part was about the vegetation and the biomass, and now some nice picture about the desert and some acquisition we have done on Tunisia. So on the top is the optical Google Earth image, and the bottom is a UHF radar with 40 megahertz of bandwidth. And you see all the details that we are able to see with this low frequency band and the bedrock below the sand with some paleo archaeology possibility. Very nice results also on the vegetation. There is an oasis in the middle of the image. And just some example of image also on a glacier. It was in Greenland, and actually we were there not to look to the glacier, but to look for a part. It was a failure, an accident on an engine on an Airbus 380. And we were on Greenland on April 2018 to try to recover the front part of the engine, the fan. And you see on the right that we succeed in retrieving this part. It was 3 meters deep into the ice. So the radar was the only instrument able to look for and to find it. This is the point on top right. The bright point is the part, actually, and the dark line is a crevasse. So the ground team was not very fun to go there, but they must do. And so some nice image of this area. It's the UHF band with crevasses. The white lines that you see are crevasses. The dark feature is under the surface lake with the water, liquid water. And this is a picture from the aircraft to show you that the scenario is very simple. It's white everywhere. Yeah, just some nice pictures. This is the airport Kangerlussuaq where we were located with the aircraft, with some nice picture at X-band. But this is over the glacier, close to Kangerlussuaq. And this is interesting to see the difference. On the top left, you have a lake with ice on top of it. So you see the ice at X-band, at L-band. You see a mix about the surface with the ice and the water below. And at UHF, there is only the water, so a dark surface, because all the signal is the specular reflection is not in direction of the sensor, so we see nothing on as a backscatter signal. And on the right, you have the glacier with very also different results depending on the frequency band. So to conclude, some key figures about the TRISAR-2 campaign. So a very new, exciting airborne mission to French Guiana. As I said, we plan to fly with over the same areas than on 2009 on Parakou, Nourag, and if we have time, if we have the possibility to add for other areas. It will be a unique opportunity to look for changes with a very large time difference, 18 years between the first TROPISR experiment and this one. We benefit, of course, from the first one on many aspects: logistics, contacts there, handling capacity, possibility at the airport. As I said, we have performed a lot of upgrades on the system, so we are confident to bring back with very nice and very interesting data for science. And this campaign definition is ongoing, so it's time to give us some advice, if you want to ask for different configuration, it's time to do so. Thank you very much.
Thank you, Jean-François. So we have time for one or two questions, not more.
Just one
yeah.
quick question. Yeah. Thank you very much for the presentation. Biomass, try this one. No, I speak probably. Okay. The biomass acquisition for the Polinsar stack been stuck 17th of April for 3 weeks. So the fact that the TROPISR 2 is scheduled in March, can you think that you can move a bit in order to have exactly the same period of biomass acquisition? It should be great.
March 2027, will be the end of the TOMO. Yes, the mic.
Okay.
It will be the end of the TOMOSAR phase, the first TOMOSAR phase for biomass.
Okay, it would be the same time.
Yeah.
Okay, it's 2027.
Seven,
not
yes.
26.
Okay. No, 26 is, no, 27. And the plan is really to fly in the same time than biomass, with I think ascending trajectory in the morning, because as I said, it's yeah. Anyway, we will adapt.
Yeah.
It is a job for airborne connection. Yeah.
But maybe this is a tricky point, because for the first TROPISR, the acquisition time was around 10 o'clock, in the morning. So
I don't remember.
I think so. So now we're obliged to choose between 6 o'clock like biomass or 10.
The question is the aperture of the airport. Is it possible to take off as early? I don't know, but this is the main point.
Okay, so let's see. Yeah, thank you.
We need to go to the next talk by Jérôme Chave from CNRS, and he's going to bring us back to Earth, talking about geotrees.
Good afternoon, everyone. Thank you for organizing such a nice symposium in such a nice city. It's a wonderful city. It's really great to be here. And thanks for the conveners as well for keeping the time. I will talk about this geotrees project that you heard about several times already yesterday and today. This is an attempt to coordinate global ground acquisition mission, which is really like an Earth observation mission from the ground. So there are a number of co-authors who are all part of the executive board of Geotrees. And I'll start by mentioning a picture that was discussed already, I think yesterday and today as well, this Tumukumake transect that was advertised by ESA. This is a place where almost no one has gone. It's really difficult to access in the eastern Amazon. And I've been fortunate to go there in 2024, so it's almost 20 years ago, over 20 years ago. And this is very hilly mountain and very interesting area to look at from the ground. So you see, you're looking at this remote sensing data set, you'd see, this is just the Amazon. But in fact, it's really, it's a Mitaraka mountain. It's very hilly, and a lot of
questions to be asked about the quality of the data and their validation. Unfortunately, this is the area where we have the least information when it comes to ground data. So one of the challenges we're faced with this question of connecting ground data and remote sensing data is that we will have no shortage of remote sensing information. We already don't. And this is thanks to all of you in the room and in the community to be so good at producing these fantastic instruments and launching them and curating the data. But the problem is that the ground data is not on par. So when it comes to validating the products, the reason why we need to think about this problem of validation carefully is that none of these Earth observation missions are actually measuring biomass. They are all measuring some structural metric, perhaps something related to forest height, perhaps something related to forest volume, whatever this means, that may be or may not be correlated with actual above ground biomass. But the ground data is arguably more reliable in estimating above ground biomass, with some caveats that I'll talk about right now. And the challenge here is to ensure that we have a long-term and permanent plot monitoring sites and also international networks that provide this information, curate them, and also fund for this activity, and not rather than assuming that someone, whoever this is funding for the production of these data sets. So this is really much more complicated than it sounds. When we talk about validating data, we've seen a lot of graphs like this one over the past couple of days. Basically having the x-axis is never questioned. Field inventory data is taken as the truth, at least in this community, but it's not. It needs to be questioned. And the y-axis is the results from the remote sensing instruments. And we see, well, there is a bias at high values of biomass because it saturates, or low values. This is a paper, by the way, taken by Mauricio Santoro's CCI biomass project a couple of years ago, but there are many, many other initiatives that are similar. So the question I'd like to ask today is how much do we trust field inventory data, and what do we mean by field inventory data? Are we confident to say some forest has 1,000 tons of biomass per hectare? Do we call that, do we mean dry biomass? Do we agree with this, or is it something different? And so if we don't get the x-axis right, there is no way we'll do a good job at estimating this all enterprise. So one obvious entry point in this question is to use national forest inventories. This is what Arnan Araza and Martin Herold and others have been spending several years at compiling. The blue dots here are national forest inventory plot data. You see, it's not covering all of the national forest inventories of the world. The US and Canadian NFIs are not included in this current version, which is still in review, by the way. There are obvious lags here. As a French, I can testify that we do have a national forest inventory in France, and more examples, but it's starting to cover quite a bit. The drawback of this approach, I mean, this is a great approach. The drawback is if you take only Japan, which is one of the best national forest inventories, you still have some issues. You have many plots, but the high data quality, so this is great. It's not the same situation for all the countries of the world. Some countries are less high quality national forest inventories. It depends a lot on the culture and the difficulties of the terrain and so forth. The cons is that plot geolocation is usually restricted by national law, so it makes it very difficult for us and in the remote sensing community to make any sense of this data if they are at kilometric or 10 of kilometers resolution. And usually those plots are pretty small. So for the Japanese case, the Japanese case, this is a 0.1 hectare resolution. So for above ground biomass estimation on a per plot basis, it's very small. It's not enough actually for statistical purposes. So the alternative is to go on the ground and to measure larger plots, and this is what we are tempted to doing, but it comes at a cost. It's not the logistics involved. This is what the technology of a field mission like ours is involved with. So I'm not belittling the ambition of the Tropisoil campaigns 2026 or 2027. I know there is a lot of technology involved, but I'm sure you all know that it's pretty difficult to go everywhere on the planet and measure trees properly with a correct methodology. And this is what we're talking about today. Now, in a way, before starting to talk about geotrees, I like to lead the way towards some thinking about how to measure best above ground biomass. What are the constraints we have, the physical constraints we have when we think about this quantity above ground biomass? One of the well-known quantities in the literature in forestry and in forest ecology is the relationship between above ground biomass as measured, which is the x-axis here, and a quantity which is the stand mean wood density multiplied by basal area and multiplied by canopy height. So this is really an intuitive approach. For each stand, if you multiply the basal area of the stand to its height and to the wood density, it's sort of intuitively a mass, okay? And so the question is it enough, the three quantities, is it enough to quantify above ground biomass across several orders of magnitude? The answer is yes. So this is just a compilation that I've started to do, but if you have more information and you'd like to contribute, you're welcome. This over 2,500 sites, spanning a range of over from less than one ton per hectare to over 1,000 tons per hectare. In this in Pacific Northwest of the U.S., you have such forests. Not very many, but it does exist. So the question is, if you want to estimate above ground biomass properly, you like to estimate those three quantities. And it turns out that the remote sensing community provides with one of these variables really well. It's canopy height. The other two, not so well. There is some claims that there is a volumetric component of the biomass mission, but what does it mean really? Is it really correlated with basal area or not so much? We don't really know, and we'll learn along the way, but we don't know. To lift one of the unknowns, we've been working on a global map of wood density, which would sort of lift the first unknown. And this is in review now. Sasan Zachi has published another one. There are many others in the literature. We believe that this one is quite interesting. It's based on a new compilation of wood density data across the world that doubles the number of wood density data that we had in the published 15 years ago. So this is a very important component, we believe, of this global problem. It's a 1 kilometer resolution map, and you see the variation from the boreal zone to the tropics, regionally within the tropics, and Australia, which stand out as you may know, there's very high wood density ecosystems. So this is one component. The other component is to have global data for canopy height. So before the era of Biomass, JEDI, and others, there has been a lot of work about airborne LiDAR, and airborne LiDAR is a fundamental component of this validation exercise. Now, we thought 10 years ago that it was a massive lack of information above airborne LiDAR, and we now realize how much has been done over the past 10 years. The EBA project, estimation of the biomass of the Amazon, led by INPE in the Amazon, has been a game changer. There's been a national forest inventory, including LiDAR in the Democratic Republic of the Congo, and a similar project in Indonesia. And some scattered data sets that has been assembled by the group, University of Bristol, by Tommaso Juker, Fabian Fischer, and others. So this is happening already. It's not enough, but this is very important information to know and to be aware of. So there are limits to the airborne LiDAR campaigns. Mark has mentioned some of them, but I'd like to mention again that The ground sometimes in the LiDAR data sets is not really the ground, maybe a Marantese cover, which may be 2 or 3 meters tall above the ground. And so it may, in this situation, what you see from the LiDAR is not the ground, it's actually the top of the Marantese, which is a herb, a grass in the understory, and it may be biasing the ground detection. So it's a problem for ground detection that's well known, but it can, if you don't go to the sites, you sort of forget about this reality. Topography is another problem. This is a site we have at Geotrees, Peru-Açu, in the northeast Minas Gerais. And this is a very challenging place for doing any remote sensing, I suppose, including airborne LiDAR. Okay, so now moving on to Geotrees, what we've been doing is quite simple, I think, is bringing together all these realities and realizing that the success of the TROPISAR mission, of the ARP3SAR mission, is based on having sites with a lot of people able to work and to coordinate activities over the long run, so that when in 2009 the TROPISAR mission went to French Guiana, we told them, yes, you can go to Noura, to Parakou, and it's a long-term station. And over 25 years, 15 years later, we are still there, and we still have the stations operating, and we can still welcome you. Same thing for Lopé, for Ipasa, for the Monda sites, it's a bit different, but Gabon is also welcoming these sites. So based on this concept, we ask ourselves, can we upscale from French Guiana, Gabon, to all the tropics and all the world? And this is the Geotrees concept. So it's a sustainably funded system of recurrent site-based measurements that will serve, hopefully, as a lasting interface between the Earth observation agencies and ground-based 3x3 measurement initiatives. So we want to focus on 100 what we call biomass reference measurement sites, representing the global forest typology, and establish reference documents for measurement, storage, and processing of the data, combine several streams of data, I'll talk about this, and engage the international community through in-person meetings, training opportunities, and scientific projects. And this is a very crucial aspect of it, because I believe that a lot of what you know should be also taught and explained to the communities and the scientists across the world. Everyone would benefit. So to go a little bit on detail, we propose to sample 10 1-hectare plots at the same site to cover at least 1,000 hectares of airborne laser scanning, and to also do 3 1-hectare plots with terrestrial laser scanning. I won't talk about TLS because Kim Caldas is speaking just after me, and he has a lot more, he will be a lot more convincing than me to explain how transformative this is in terms of the data. So we have the 3-layered strategy, and we are combining this. Where do we stand for the moment? This is the latest version of our map. Nothing is completed for the moment. What we mean by completed would be it's put online, ready for access to you. And for the moment, we are still working on the pipelines, analytical pipelines. We say it will be ready in 1 week as just the motto of the map group. Next week, it will be ready. In reality, maybe a month to 2 months, we'll start to deliver the first packages, data packages, and several sites are already ready, actually. We have all the data available. But we're already operating on 43 sites, and we are planning activities on 19 sites, which is, if you think about it, quite amazing. And I'm so happy to hear about the projects in Choco, the projects in Peru that we are co-coordinating with the NASA group, the GPL group, and we are also actively working in Gabon. One thing we'd like to do with the help of ESA is to fly a small footprint airborne laser scanning platform at all 3 sites, Monda, Lopé, and Ipasa, in the forthcoming months. We're still waiting for the money to come. Cheers to ESA, but this is going to happen. Okay, now quickly the pipeline, airborne laser scanning, ground forest inventory. It gets crunched into the analytical pipelines to produce reference information that is put online, available in principle for the validation of biomass, potentially also of the NISAR products and whoever wants to pick up this concept. The data crucially will not be available tree by tree, our cloud points, because this is proprietary to the site PIs, but what we will make available is a quarter-hectare resolution dataset. Doesn't mean that we throw away all the data. All the data is still available, but has to be discussed with the site PIs. This is sort of the discussion we want to enforce between the site PIs and our community. There is no free lunch, so to speak. There is a database platform that can be accessed. It's called the data.geotrees.org. It's pretty empty for the moment for the reason I explained, but it will be populated for over time, and we also try to push the information onto the community so you know that the data is arriving. And finally, we have a fine group of experts, some of them in the room, who are really tasked with advising and providing technical input for this project. Finally, involving the ground research community. I've said this several times over, but it's really essential because you can make big mistakes if you don't know the field, and we're talking global, so it's really important to make this effort over time. I understand, and I'm the first one to be excited and to be able to download the data free and to be tinkering with the data sets. But the reality, if we want to do a good job, we need to work with the local communities and people who actually know their forest. And the establishment of the coordinated networks is crucial for the success over time. So people will not believe us if we, so to speak, steal the data once. We won't do that twice. Okay. This is a really large community, a network of collaborations, 46 sites and growing. And importantly, of course, I'd like to acknowledge supporting partners, especially NASA, of course, CNES, and also the Moore Foundation, the Bezos Foundation, and other partners here cited in this slide, because it's really a costly enterprise. Stay tuned. So in conclusion, the current efforts of biomass validation are based on easily accessible data. It's good, and it's probably the first thing to do, but we need to think ahead in terms of data quality. These methods have known limitations, and I've explained this, and GeoTrees try to take the next step in terms of data quality, and you'll see that in trying to cover especially the tropics will be a game changer in terms of what we learn about the forests and how much trust we can place into the products created by our community. With that, I'd like to finish with the motto of GeoTrees: foster collaboration, share the cost, and thank you very much for your attention.
All right, we're running 5 minutes late here, but let's have a quick question.
Sorry.
Thank you, Jerome. Yeah, of course, thanks as well for stipulating that it's really essential to have this data and need for validating what actually we measured from space. You mentioned that for GeoTrees, you expect the first data to be open, let's say, in a few months maybe. But you didn't mention which sites those are going to be, and I think it would be quite interesting for people to know which regions those sites are.
Data is ready for Panama, but it's not really useful in any way for. I don't have a pointer. Do I? Okay. So Panama is over there. There is a bunch of sites in São Paulo state and southern Brazil that may be interesting. The site in Amacaiacu that was mentioned by Mark is fully ready to go. We have a bunch of sites in Central Africa, including Gabon, Angola, Congo, the Lunugu site in northern Congo that are all ready. We're still discussing with ISRO because they have put together 10 sites and they have all the data ready, but sharing the data with India is a bit of a challenge, as you may know. So we are trying to work things out in terms of data processing on site by ISRO so they would provide the metadata, not the data. So it's a challenging project. And some site in Thailand should be ready in a short amount of time. If you have some priorities, I would love to hear from you also, and push some of the operations further if we can. A lot of the delay is actually not related to the field acquisition. It's related to processing the permittings and processing also the money and the flows of money from the north to the south, basically, which is logistically challenging. So it takes time, but it's worthwhile.
Okay. Thank you, Jerome.
Thank you very much.
So next talk is Kim Calder from Ghent University, talking about terrestrial LiDAR.
So I'll be talking just about one aspect of geotrace, so the TLS aspect. And when I'm going to mention the word biomass in my talk, I'm really talking about above ground biomass, unless I will specify it differently. So this is really like a summary presentation of all the work we've been doing in the last 15 years, starting with really nothing being available to where we are now. And I've put it together as in like, what can TLS offer to you as a community, to the biomass mission, and what can it not offer as well? I think some people sometimes think it's like a magical instrument, and it's not, so I'm trying to give a very fair representation of what it can do and what it cannot do. So when we talk about biomass, this is essentially what we want. We want to weigh a tree, and we want to know the weight of the tree. So for obvious reasons, it's not what we want to do, partly because the tree is gone, but also, I guess, in the future, I mean now as well, we're also looking at change. So of course, if you remove the trees, then you cannot really look at the change anymore. So for me, TLS is quite powerful. So TLS is also operated on the ground, so it's a surveying instrument on a tripod. Here you can see a point cloud, so you're basically looking, you're flying through the point cloud, looking to the top of the trees. I particularly picked this animation just to make sure that we are really at the bottom of the forest looking up, whereas most of the remote sensing is looking down to the forest. So this looks really nice. Also what I like about LiDAR is that it's very traceable. So we have these 3D point clouds, and then we derive these products, often on an individual tree level. But if something is not correct or somebody flags something, well, this is a bit weird, we can always look back to the raw data, and it's a real virtual forest. So we can really try to resolve some of these issues that we might find later in the analysis. I just put this picture here, so you have a scanner, and then, you know, quite often when you go scan with new people, they want to be scanned, so that's what we do. But then you can also see these shadows behind them. This is just to illustrate that LiDAR cannot see through stuff. If we have a solid object, we will not collect data there, and that's why we do observations at multiple locations in the site. So this animation basically summarizes how our field work looks like. So you're looking at the forest from above, and then we have multiple locations in the forest where we do like a laser scan. There's a red like sweep you see going around. Within geotrees, we have settled on a 10 by 10 meter grid. So in a 1 hectare site, it's 121 locations. Then we ended up with a point cloud, which in reality, of course, never looks as clean as it does on this animation. And then we have a whole bunch of points, but the points are just really stupid. They don't know what they are. Are they a leaf? Are they a branch? Are they a twig? And to which tree they belong. So the first step is really splitting that big point cloud into individual trees, so an instance segmentation. And once we've done this, we can start modeling the tree, because again, it's just points. And then we model this often with a cylinder model or some other geometric primitive. And then we have what we call quantitative structure model, and then we can calculate the volume, because that's really what we do with LiDAR, terrestrial LiDAR. We don't estimate biomass, we estimate volume, like Jerome already said, and what we often do is we then just multiply it with some kind of wood density to get a measurement of the mass of the tree. And because, of course, everything is in 3D, it's not just one tree, one value, we also have these 3D distributions of where the biomass is located. This is just one slide summarizing about 15 years of validation work around TLS. So these are all the studies until 2022 that have basically done destructive harvesting of trees and at the same time collected TLS data. And you can see some of the sites were logistically a bit more easy, like the crane there, that's in Australia, it's in Victoria. And then I think then the picture where we had to sort of build the own, like the homemade scale is, I think it's in Peru. So we have trees going from like very low biomass to almost 50 tons per hectare on the x-axis. So that's really from the destructive harvesting, also bringing this to the lab and doing the weighing to get the wood densities. And then on the y-axis, you have the estimates from terrestrial LiDAR, so deriving these volumetric models and then multiplying it with the same wood density that we derived. And you can see overall, I'm not going into detail, that we're pretty confident that we can do a pretty good job with the TLS instrument if we do a one-on-one estimate of assessing the biomass or the volume. So when we started doing this work, this is what we really wanted to do, full plot analysis. We want to know everything of all the trees in the site. And we've done it for a few sites, but I will tell you later why this is not a good approach for chia trees. I mean, it's a good approach, but it's just not feasible. So when we do full plot analysis, so this is White and Woods in the UK, so Solosor Forest geosite, and we've scanned it a few times now. We scanned 6 hectares there, so it's probably one of our largest areas where we have TLS data. And I spent my whole postdoc manually segmenting those trees because we didn't have any algorithms to do it. So this is like a perfect point cloud with very high quality control and assessment on it. And what you see here is the coloring is different species. We basically have every tree. I think the smallest one is like 1 centimeter because we don't have to use a cutoff diameter. We can analyze all the trees. And then we can basically, you get like, these are all the trees. These are about 700 trees. We have all the structure of all these individual trees in 3D, which is very powerful to have. And of course, in a site like White and Woods, so that's in the UK, we scan both in leaf on and leaf off. I'm not going to mention too much because, of course, in the tropics you have leaves, we need to remove the leaves. But if you can do this work in leaf off conditions, you get like the quality of the point cloud is, of course, much better because of the occlusion that I showed with, you know, when we scanned the people. There will always be occlusion. We can try to minimize it, but it's not magic. So for White and Woods, we then compared it with the forest inventory. You can see there's more trees in the TLS data. That's just because the forest inventory used a cutoff diameter to be included in the inventory, whereas we basically didn't use it. So there's just a lot more smaller trees. But overall, the distributions agree pretty well. Then I also plotted this Bunz 1968. So what is Bunz 1968? That's actually the data that underpins most of the allometric models in the UK still to estimate biomass for woodland species. So that's already quite a while ago, and you can see, and we often see this, so there's a lot of smaller trees in there because harvesting large trees to build this allometric model is quite challenging and time consuming, often not really what we want. Also a lot less trees in there. So this paper was written in 1968. And in 2002, I finally managed to track down Bob Bunz. So that's Bob Bunz there, the guy who in 1968 wrote that paper. And Matt Disney, you can recognize there as well. So me and Matt, I went to the UK. Matt picked me up at the airport. We drove to the Lake District. He's retired there. We met in his pub. And then he took us to a few of his sites, because all of his sites are in the Lake District in the UK. If you're familiar with the UK, the Lake District is not a representative area of most of the UK. But still, until today, a lot of these data is underpinning a lot of the reporting of the UK woodland species to the FAO. It's actually, some of them are the only allometric species in Europe. So it's a bit problematic. And what I remember most from my days with Bob Bunz is that he said, "Oh, you're the first one to ever contact me about this paper." So he didn't know that this happened because he went on to do some other stuff. So it was quite interesting to have this conversation with him, and he really helped us also a lot with trying to understand what was really going on with our data and how we could put it in a biomass context. So summarizing this work is, well, we basically found 1.77 times more carbon in the UK woodlands than was currently being reported by using these older models. And not just on the small trees, also on the big, well, obviously on the big trees, but also on the small trees, which is often something that we don't see so often because the calibration data for allometric models is often including a lot of small trees, is often giving quite a good estimate. So part of the reason is that if you want to know everything about it, you can read the paper, but it's also because forest management has significantly changed. When Bob Bunce made those measurements in 1968, the UK was still actively using coppicing. Coppicing has been abandoned for almost 50 years, but still that kind of form and that structure is being incorporated in how some of these species are being modeled by allometric models. So it's quite powerful to then have these data. What else we can do with it is look at like where is the biomass distributed. So actually a lot of the biomass is in big trees. It's not something new, but now we can really start to quantify it. So for example, 90% of the biomass is only in 200 trees out of 600. So if you just measure the 30% largest trees, you already get like 90% of the biomass on a plot level. So I won't go into that much because we're running a bit out of time, but I think Wouter is talking a little about this as well. But basically, takeaway here is the biggest challenge of doing this kind of work, because this is what everybody wants, is like all the trees in the plot nicely analyzed, is instant segmentation. So basically splitting the point cloud into individual trees, because you can have false positive and false negatives. And is it something that has a big impact, yes or no? We don't know the answer yet. Then the second approach that we can do is allometric models. Allometric models is not something new, but I think, and again, this is not something that one kind of data set is better than the other. I think they're very synergistic and they can be used together. So this is some examples from work that we did in Australia. So this is UKphase. This is a free air CO2 enrichment experiment that has been running since 2012. And they basically, we've been also working there since 2012. And they said, well, we're doing all these projections of carbon, but we don't really have a local allometric model. We made our own one by pooling some data. Can you check how good it is? So it's only one species, so one eucalyptus species, so that's pretty convenient. And what we then do is we segment all the trees. Then we use this ITSME package, so we can, on an individual tree level, we can estimate the biomass, the diameter very easily, also the tree height and the crown projection on an individual tree basis. And then, of course, the volume by using this quantitative structure model. Then we compiled a whole size range distribution, so that's one of the advantages. So we were missing a few larger trees, which we then scanned individually and we added to the data. So we're trying to get a data set that's really representing the whole size range of tree species. So if you then plot this, so then you have the diameter derived from the TLS data, you have the AGB derived from the volumetric models from the TLS data, you get these typical curves, and you can fit like an allometric model. So Louise Therin did this. So we've been using this Bayesian approach, and you get like this typical allometric model. If you then compare with the green line, so the green line is what they were using. So that's basically the same species. There were 3 data sets available in Australia, but they were from Queensland and they were from New South Wales, whereas UKphase is located in different sites. It's in Victoria, and Australia is a really big country, if you would look at it on the map. So basically what you're saying is that for smaller trees, the agreement is better than for large trees. And if you take 3 trees, so the tree with 20 centimeters, 40 centimeters, and 60 centimeters, you can see that the underestimation by using the wrong allometric model is increasing with tree size. So it's about 40% for a tree of 20 centimeters, 50% for a tree of 60 centimeters. But also the biomass itself is more, so the absolute value is also more. So actually in absolute terms, it's becoming quite important. So to basically summarize everything that I've said is, I think TLS in my world is pretty validated. That being said, if you're ever planning to cut down a lot of trees and really weigh them, you should really reach out to us, because we can really use more and more validation, because there's not that much data available. It's not perfect. TLS is not perfect. Like, you know, sometimes people think it's going to solve everything and give them the perfect biomass numbers. It's not going to do this. So we really need to understand where the limitations are. That's also my last point here. We are really now looking at if we run everything in an automated way and we ignore the false positive and the false negatives, because if I'm a branch but I'm on the wrong tree but I'm still included in the analysis on a quarter hectare scale of biomass, does it matter or does it not matter? We don't know yet. And if it doesn't really matter, that will really give us a good advantage in processing a lot of these data that's now sitting on many people's hard drives for geotrees and then for the biomass community. Yeah, and big trees are very important. I mean, it's really not something new, but the analysis is really throwing it up over and over. So
thank you very much. If you have more questions, you can just come talk to me or write to me.
Okay, so we have time for one question.
Well, is there one? I have a question if nobody else is.
No, wait.
Go ahead.
Thanks, Kim. I had a question about the situation where you're what you showed here was especially temperate forest and especially then a leaf-off situation. I know you've also been measuring in the tropics, so and I think the challenges are a bit more there, of course, because you don't have this typical leaf-off situation, I guess, and also the density is higher. So what are the main problems you run into there to make sure that you will be able to get a proper scan of the relevant plots there?
Yeah, so if we have leaves on the trees, we can remove them quite well, and I think Wouter will show some stuff of that in his next presentation. But the problem is, if you have leaves on the trees, you have more occlusion, because if a leaf is blocking smaller twigs and branches, then of course there will be no data there. So that is a limitation of the instrument. So we have also looked at fusing it with the same quality drone LiDAR, for example, to overcome some of that, and it does overcome some of these small occlusions. The reality is also that most of the biomass is not in these small parts. So if we can understand the uncertainty that we have by just having that occlusion in the tropics, we are already like a step forward from where we are now. The reality is also it's a bit like the resources are limited. Now we scan in a 10 by 10 meter grid. If we could do in a 5 by 5 meter grid, of course the data will get better, but you spend 4 times as much in the field. So just to give you a reality, 1 hectare in the tropics is about 4 or 5 days of good weather. And good weather is we're really princes and princesses. We cannot have rain, we cannot have wind. Like, you know, it's challenging. So it's a bit of a trade-off, yeah.
Okay, thank you.
Thank you.
Okay, thank you.
All right, so next presentation by Wouter A.J. van den Broek, and bringing us back from the TLS to radar. Kind of, mostly TLS, okay.
Do not push.
Okay, so hi everyone. My name is Wouter van den Broek, and I'm a PhD student working with Kim Calders. So it builds a bit upon the previous presentation, also talking about TLS, but more on the side of using it to construct 3D virtual forests and how we can use this in combination with relative transfer models. So as a brief introduction, we have a real forest. We can make a real remote sensing signal getting from this in either optical domain, thermal domain, microwave, whatever. But basically what we want to do if we have this remote sensing signal is to go back to derive properties from the regional forests, so about forest health, productivity, biodiversity, or biomass in this context. So that's basically why we are all here. And so one thing that we are doing is seeing if we can reconstruct, so make a replica of real forests and use this in combination with relative transfer models to see if we can better understand our remote sensing signal. And so ideally if we compare this with the original or the actual measured signal, this should compare very well and hopefully lead to better inversion models. So in the first part of my talk, I will talk a bit about how we can actually go from these real forests to a virtual forest. And the first part is a bit similar as what Kim showed. I didn't really check his presentation, so I can go over it quickly. But so we use terrestrial LiDAR. And so it's this device we put in the forest, which just measures, which fires pulses and records it at multiple angles by this rotating mirror. The device also rotates. So we basically and put this in multiple places in the forest. So we get a point cloud of, this is like a 1/4 hectare point cloud, just colored according to height. And indeed, we need some steps to actually go from these points to something useful that we can use in a relative transfer context. So this is actually just from 3D points. We have no information to go to surfaces or volumes. So we start from our just 3D points. So these are just 3D coordinates. We need to do some segmentation of individual trees and then fit some surface or volume models. And in the end, we also want to add some leaves back again. So what some of colleagues and myself have been doing is doing some benchmarking exercises to see if we can automate this process. Because as Kim mentioned, just manually segmenting all these trees is really a pain in the ass and takes so much time. So this is not really feasible for doing it on larger plot scale level. So this is work from a colleague of mine, Wout Cherlet, who looked at comparing different algorithms for actually separating the plot point clouds into individual trees and for multiple ecosystems, so temperate but also in tropical, like Robson Creek is a plot in Australia. And then looking at different segmentation algorithms. This is work I did myself, so look more into this leaf-wood segmentation problem, so and specifically for tropical trees, so to compare different algorithms and see how they compare to manual segmentation of these leaf and woody return points. And then lastly, this is another colleague, his work, he looked at if you have this individual tree and we now fit the cylinder models through it, there's also different algorithms that exist, and to compare how do they compare to each other, how do they attribute volume to different cylinders according to height. And so from this benchmarking, we then decided to move forward with one of these algorithms, which is pretty promising. It's called the ray extract algorithm, which was also recently published in a paper, which you can see on the left top. And how this algorithm works is basically by first fitting a terrain mesh through your point cloud. And from this terrain mesh, it builds up a shortest path graph. So by identifying stem points and then growing like a complete forest shortest path graph, but through the whole point cloud at once. So not just through individual trees, but at the same time. And so this is computationally efficient, but also has some advantages that we basically have the instance segmentation step and the QSM, so the cylinder models step, and also the leaf-wood segmentation step, like all at once. It's basically one algorithm that does the 3 steps. And we can have either this cylinder representation from which you can calculate volumes, but you can also make like a watertight mesh from this, so we can use this in more relative transfer modeling, which I will come to in a bit. So then in the last step, we have our cylinder models. Then we also want to add leaves again. And this is, we do this by using LeafGen. So LeafGen is an open source package which got recently published as well. And it uses a QSM or the cylinder model as input. You can also specify like a leaf geometry. You can specify leaf distributions, such as the area of the leaf, the orientation of the leaf, and leaf area density. And also, you can specify distributions according to height. So it's parametric distribution, so it's not just static, but more on a tree level. It makes sure these distributions are correct. So that brings me to the second part of the presentation, which is then, now we have these virtual reconstructed forests. How can we actually use this in combination with relative transfer models to do some simulations of some remote sensing sensors? And I will show this quickly for LiDAR, also for optical, and then to finish, I will also show this for some microwave simulations. So first, we can do virtual laser scanning. So this is our reconstructed forest. So a mesh representation of a real forest. So we could place virtually, again, a scanner in our virtual forests and then make a simulation with this. For example, Helios++ is one of maybe the most common or famous package to do so, to make LiDAR simulations. And what you then get is this. So this is a virtually simulated scan in a virtual copy of the forest. And so here on the left, you can see the real point clouds, and this is in the simulated point cloud version. And so they match pretty well. And so, looking at this kind of gives them an idea, like how well did we reconstruct our original forest, because the point cloud should look quite similar. And additionally, what's interesting here is that we actually have, using the simulation environments, gives us more information since we know exactly like on which surface our pulse is reflected. So we have information on which are woody returns, which are leaf returns, and also exactly which is which tree. So this could in future inform us or help in building better models actually. And now we can move to the optical radius transfer, so in the solar domain. So in this case, we should virtually add a sun with an irradiance spectrum. We can also add an atmosphere, so using some vertical profiles for molecular components, or also adding some particle layers, which we, for example, can obtain from the Copernicus Atmospheric Monitoring Service. Then we should also characterize this 3D structure of our forests with some reflectance spectra. So each of the different components should have some, in the optical domain, some reflectance values, which we can derive or which we can measure in the field using a field spectrometer. And then we should also specify some sensor that we want to simulate with spectral response function. And so the software that we are using for this is called Irradiate. And what it does, it's, you specify all of these different components, and then it does bidirectional Monte Carlo ray tracing to derive a physically based rendering, basically. And so this is, for example, what you can then derive. So this is a simulation using a replica of a real forest. So it's, I want to stress here, this is like a real forest and also geolocated, so on its exact position, where we here used some background Copernicus DEM, and for the atmosphere we use actual measured or modeled values from the CAMS dataset. And so this data comes from a campaign that we actually did last year in Patagonia National Park, and you can see on the left it moves a bit. So we are studying caterpillar defoliation, so yeah, you can see the green parts and then the defoliated parts. Not super relevant here, but just to give you an idea of the ecosystem that we were studying there. And so we are measuring some plots, both these spectral values, so for the understory, for the leaves, and for the bark, we take some field spectrometer measurements, and also we conducted then some TLS scanning to derive our forest point cloud. This is then another example. So we have our reconstructed forest on the left, so the 3D forest mesh, but just seen from above. And then this is, for example, a Sentinel-2 simulation, so level 1C, so above the atmosphere, just an RGB, so band 2, 3, and 4 stacked together. And here at 5 centimeter resolution, so not the 10-meter resolution, but just that you can see better, you can see actually the trees and then how the shadows are modeled or simulated. And we can also go a step further to actually model larger areas. So this is not like a one-on-one mapping anymore, but this is using like statistics of that we know of the forests, and we populate or we use our 3D scanned and model trees, and we populate them on large areas. So this is for Patagonia National Park, and then again we can do some simulations. So these are both simulated images using a 3D input and reflectance spectra as input. In summer on the left and in winter, so without leaves on the right. And again, what's interesting is that since we're using like a virtual simulation environment, we can make simulations, but we know exactly like the ground truth properties. We can calculate from the mesh exactly how much leaves we have. We know how much volume there is. We know how much surface area there is. So we know the height profiles exactly, and we know for example, the LAI or a tree instance mass, these all properties you can calculate exactly from the mesh, and you could potentially then use you can use this then to develop some machine learning algorithms, because you have basically perfect labeled data. And that brings us then to the microwave story. So we can do the same thing using our virtual forest as input, but now we should not use reflectance spectra of the surfaces, but we don't need a sun anymore, which is useful. And so we can replace this with dielectric permittivity values for the components in our forests. And I will briefly talk about 2 projects or studies that we're currently pursuing or developing, which is about the wood penetration radar and then a tower radar experiment. So first, wood penetrating radar. This is research in collaboration with University of Bordeaux. So Francois Demontou, he developed these in situ sensors, which basically you have these two antennas which you place on opposite sides of the tree trunk, and they send microwave signals through your tree trunk and then record the backscattered and the forward scattered waves. You can do this at multiple wavelengths, so you can choose the waveband. And what the advantage is, of course, here they're in situ, they're non-intrusive, and they give, ideally, then you could relate this to some value of the dielectric permittivity, which we could use as input in our relative transfer models. So on the figure left below, you can see an example of so on the x-axis is the depth of the tree, so the tree trunk, and you can see the reflection magnitudes, so it changes through the tree, and you see these are the multiple lines and multiple time steps that it was measured, and you can see at some parts in the tree, so there's actually water flow during the day in the tree, and so there's variation in these reflection profiles. And so these parts you could also plot over time and then relate to environmental or weather variables to see how actually this reflection pattern, and so the dielectric permittivity also will change throughout the day. So yeah, the goal is to estimate these values then. So we have two of these sensors currently installed in our university forests on a maple tree, and they have been measuring for almost 2 years, but with a lot of gaps since it's quite experimental sensors, at a 20-minute measurement frequency. And so what we're also doing is measuring this tree every month in 3D, so we could hopefully then relate this information about branch fall or the phenology of the tree also to the signal that we derive from the sensor. And we also have weather variables, of course. So unfortunately, I don't have more results yet to show, but I think it's quite an exciting project. And then lastly, we go from Belgium now all the way to Brazil, to the Amazon, northeastern Amazon forests. And this is research in collaboration with the University of Edinburgh and University of Pará. And they have a research plot where they have a 1 hectare control plot and a 1 hectare drought plot, so simulated rain through-fall exclusion experiments. You can see the panels which were covering a 1 hectare area, which are excluding 50% of the rainfall to simulate drought. And it's been going on for 25 years, so the longest running drought experiment in the tropics. And we've went and scanned these forest campaigns in 2023 and 2024. There's actually also data from 2014, so quite a cool data set. So you can see the 2 point clouds of the control, 1 hectare control and the 1 hectare drought plot. And so end of 2023, the NASA installed tower radar. So on the tower, they installed for both the drought and the control plot a radar, which is measuring in SLMP bands at a 10-minute measurement frequency. And so the idea is to combine the TLS that we have with also the ecophysiological variables. So we have for 20 trees in the control plot and 20 trees in the drought plot in the field of view of these radars. We have the sap flow and stem water content sensors and also soil water content. So the idea is to hopefully combine this all into a relative transfer or a microwave interaction model developed by Ludovic, so the MIPERS 4D, and to then do some simulations and compare this to the actual data that we have, and then hopefully we can learn something more about our signal and how it sees the forests. So again, unfortunately, no results yet, but quite a comprehensive and cool data set, in my opinion. So in summary, terrestrial LiDAR allows for detailed 3D forest reconstruction. Virtual forests combined with relative transfer models are a powerful tool to better understand our forest remote sensing signal and generate labeled data. And there's a promising synergy between terrestrial LiDAR, ecophysiological measurements, and microwave interaction modeling. Thanks.
So thanks a lot, Wouter. So if there are any questions, we have time now or for the coffee break. Yeah, Shane.
I'm not quite quite sure whether the question's for you or for Ludovic, but you know, in many microwave radiator transfer models, they got to represent the medium, which is typically as a layered medium with discs and cylinders and so on. Is that the sort of representation you're trying to infer from these TLS measurements, or do you use a completely different structure of the model to represent the medium?
Yeah, so it's true that historically most of the radiative transfer model, or we should call them, let's say, microwave interaction model, because coherent model are not radiative transfer model. And so historically they were representing the forest with homogeneous layers. But since, let's say 5 or even 10 years, we manage, and also with all the progress in computer science and so on, so we managed to reconstruct the forest at the tree level, and then this TLS data is really perfect. So maybe the gap now is to reconstruct accurately the branches, because we know that yes, the branches are maybe representing a small percent of the biomass, but a huge percent is morely the proportion is completely the opposite of the radar signal. So of course both are related through allometric equation, but that's not that's not obvious.
So yeah, Jerome. I have a question for Wouters. First of all, it's a great presentation and a beautiful one too. My question is about your model, 3D representation based on AI that you described in the middle of your talk. I wasn't too clear about whether this was based only on area that you had image with TLS, or whether you had some way to upscale using some other method.
And, which one are you talking about exactly?
So at some point you have this 3D representation of, well, it's in the middle. There's a lot in your talk.
Yeah.
It's great. This.
More back? This one? No.
No.
More?
You lost me. Anyway, maybe a question that we can discuss, the two of us.
Sure. Yeah.
So sorry. Yeah. Thank you very much.
Okay, so I think we can close the session and pursue during the coffee break. Yeah, thank you, everybody.
Shall we get started? For the last segment, last but not least. Okay. Can you do the first presentation? We alternate.
First speaker, yeah. Okay, so welcome to the session, Biomass and Ecosystem Modeling. The first speaker is Ludovic Villard from CESBio. Ludovic, the floor is yours.
Thank you, Mr. Chairman, and thank you everyone for staying, let's say, late. So my talk, yes, will be about temporal variability of the Piedmont backscatter over tropical rainforest, and in this framework, the inside of the TROPISCAT2 experiment during the Calval activity. So yes, so the context is, let's say, a Calval project we propose on, yes, to better characterize the temporal variability from Piedmont's backscatter with two parts. So the first one about, so model, underline this term, because of course this is not a matter of instrumental calibration. We are talking here about model calibration of decorrelation mainly and backscatter intensity. And we will see also, and the second part is about validation of the, let's say, long-term temporal change estimated by biomass. And yes, so we will see in this framework where some details about the experimental and simulated data with the data from the TROPISCAT2 experiment and the simulated data from the MyPers model. So we'll see this more in detail, this model for decorrelation and intensities and the validation plans. So if we put this a bit in perspective, so temporal variability was, this question was already raised, yes, more than 10 years ago during the phase A of the mission, and but not really in the context of validating the long-term change estimated by biomass, but for the design of the mission, and especially to choose the acquisition time or the temporal baseline. And for this, we had support mainly from ESA to carry out, to achieve this what we call the tower-based experiment. So which, yes, as you can see, consists on let's say, a kind of radar on top of flux tower. So why a flux tower? So so of course, to benefit from meteorological measurements, which are really helpful to better analyze the data, and also to measure fluxes, which are very important at the end to try to validate the temporal changes. And so yes, so mainly with 4 campaigns, or mainly 2 with first and second generation, with so for the boreal forest with BoralScat, and for tropical ones with TROPISCAT 1 and 2. And so we were, let's say, not surprised in terms of temporal change, and we could figure out the importance of water content. That's why I was mentioning the importance of the big difference, because acquisition time at 6 hours in the morning or 10 hours in the morning, I mean, it's a parameter to choose, for instance, for the next Tropisar campaign, airborne campaign. And so we had, yes, let's say, spectral change for intensity, and also for temporal decorrelation, as you can see with this result. So in green we have the let's say typical pattern of the decorrelation of the temporal trend of decorrelation of coherences at P-bun in green, L-bun in blue, and C-bun in red. So we can yes. Quite clearly see the impact of the diurnal cycle, and actually this diurnal cycle can be as important as let's say this total temporal baseline, which is the one of tomographic I mean is the temporal gap between the first and the 7th tomographic acquisition. Okay, and if we look at longer terms decorrelation as up to 14 months, then we had this kind of curves that were very important, yes, for the design of the mission. So with the whisker bars represent the dispersion here for the covariances, and I put also something important in bold each time. It's simply the correlation between intensities, which are also very useful in order to design the let's say the multi-channel speckle filtering, and which are involved in this algorithm. And there we did that of course for the time of acquisition of biomass with quite similar campaign patterns. And we are quite happy now to see that given the very successful let's say preliminary result of the mission, we were not that far from the reality. But now, yes, the big challenge is not to let's say convert this temporal change into let's say noise in the biomass estimates. Okay, so regarding now the data we have, so from in this talk only about TROPISCAT-2, but since already 2018, so the various colors are mainly for the representing the acquisition at P, L, and C band, which is let's say the new thing with the Tropisar 2 campaign, and yes, exactly. And so we can see that we managed to get more than 5 years of acquisition. So unfortunately, we had let's say a big failure last year, or in March 2014, and the time is to repair it. So of course, unfortunately we missed this year, which was unfortunately a bit. Quite interesting, because it was a very severe drought in this year. So something we could have also at the end of 2023. But yes, so fortunately we were able to repair it, and now the plan is to replace the antenna, the actual antenna, the current antennas with a new one with radome, so like that, which has been already installed inside the forest to measure let's say the attenuation, but this time we will replace all the antenna with this kind, and on top of the radome, so of course to be more robust, to give more robust resolution during rainy events, we have an extended let's say bandwidth, from which we could better, let's say, reproduce spaceborne L-borne acquisition, because until now the L-band we have was limited to 1 gigahertz and not 2050. Yeah, 25. Sorry. And so yes, and the plan, yes, is to have something ready. So normally this should be ready in next March, but yes, and the plan is to have, let's say, to renew completely the system for March 2027, when we will have the first biomass tomographic acquisition, on top of, as Jean-François Nouvel mentioned before, the Tropisar 2 campaign, plus very likely a drone-SAR acquisition. Okay, so this was for the radar experiment, and on top of that, of course, we can still benefit from the measurement of the tower. So yes, and we will see that what is yes particularly important is the measurement of fluxes, because we will try to use these changes for the further comparison with temporal changes estimated by biomass. So yes, I think I can go back if we have more question about that. And on top of or you can also, yes, of course, I didn't mention my colleagues, so Damien Bonal or Benoît Burban at INRAE, which are the scientific, let's say, PI of this, and scientific and technical PI of this experiment. And on top of the measurement from the tower, so we have also measurement from laser airborne LiDAR and TLS in order to better characterize the forest cover. So we can see that the site is maybe not really representative of all the forest, because yes, we can see here that so this is the tower, and the line of sight of the radar is in this direction with a slope opposite to the radar. So as we'll see that the need, let's say, of more complex model in order to generalize this situation. And regarding, yes, the TLS, so we had, so until now, yes, the mock-up are not completely ready, but people are working on it, and probably, yes, the team from Kim also could help us in this work. And but on top of all this result, we are still, let's say, looking for so not only for more accurate estimates from TLS regarding branches, but also what is very difficult is to have a good parameterization of the vegetation water content. And for that, actually, I think the best system is really the one we have. I mean, as long as we can rely on what I call high revisit occurrences. I mean, if we take the most of all the data, I mean, the data every 15 minutes. So this thing results have been already presented, but it's quite spectacular because even at so we can see here that this is, yes, the occurrences for only 15-minute baseline. So I mean, each time we compare one acquisition with the previous one, and we can see so at P, L, and C band. And we can see here this, let's say, quite a spectacular drop, so mainly at very spectacular at C-band, which is not due to wind, as many people would have thought before, but really to the start of evapotranspiration, as we can see here, because as we can see here, the start of evapotranspiration, whereas the wind velocity reach more or less is minimum. So we have, yes, this pattern is much more pronounced in the dry season than in the wet. So this motivates us to try to estimate directly the vegetation water content. I mean the relative mean variation from this cycle, this currency. So for that, we try to select several times of several reference time. And try to see the various let's say, behavior. And actually, we realize that there is not so many, let's say, variation. Of course, as long as we assume that the phenomenon is stationary with periodic variation, and we can actually, with about, yes, 4 reference time, we can reproduce, yes, the cycle that would best estimate this cycle, because each time I mean this peak here, for example, here or here, when there is a drop and then a small a small peak, is actually due to this periodic shape, and which is yes, of course, not a simple sinusoid, but it has this this shape, which is yes, directly related to the variation of currencies. And now we would like also to compare it to in situ measurement from the same system as presented by Wouters, so which is a system developed from our colleague in Bordeaux, François Desmontoux. And so unfortunately, yes, the system didn't work very long, but we managed to renew it, and in order to, let's say, extend the time series to have a more reliable, let's say, comparison. And another thing quite new is the use of a new mode, a Doppler mode, which actually is something quite, I mean, the easiest mode, easiest possible mode for radar people, because historically people were using radar for that. And actually, so we are measuring the effect of motion on let's say, the spectral shift. And so we can also compare it, so not only to the wind velocity from the tower, but also to accelerometer, which has been installed on branches, in order to have another measurement of the impact of the motion of scatterers on the Doppler spectrum. So we can here see the comparison, yes, which works quite well, as confirmed by these scatter plots, where we have the correlation between accelerometer and the wind field. And yes, and we can extend it. And what is quite interesting is we can really see different patterns between day or night, which could be, and for us, which is very likely due to the change of mass between, of course, the day and night, and then the way the trees will move will, of course, be impacted by the total mass. And this result will be used to parameterize the MyPers model. So I will not go into all the detail, because yes, I'm running a bit late and it has been presented before. But you do think yes, this parameterization of water content, and yes. And this should answer yes, the previous question from Sean. So yes, we are simulating the forest at the tree level, and so we start from in situ data from inventory, and then we can reproduce and compute the attenuation coefficient for each cone which replace the former layer. And this is yes, an example of comparison between simulated and the real data, and we manage the results are quite well, but of course yes, we need to fit a lot of parameters. And I will just finish with this the validation plan. So of course this is the plan for the upcoming years, and we'll try to compare the fluxes to the temporal change. And so unfortunately, as the footprint of the tower is a bit is not on the side we know best, because we are looking we are northeast. This is simply due to the wind distribution here, which is quite constant. And if we compute now yes the uncertainty, so everything so of course we know this curve, and the sensitivity of the backscatter to the biomass, of course, is very different from the historical indicator, the gamma naught, to the tomographic intensity. But this is the key point to rate the standard, the coefficient of the variation coefficient of the backscatter intensity, whether from the standard mode or the tomographic mode, to the one of the uncertainty in terms of biomass, or to the incremental change. And if we put this uncertainty into, let's say, the speckle filtering mode, then we are able just to compute the standard deviation, which are, let's say, which give us more or less the ability, our ability to faithfully estimate the temporal change estimated by biomass after 5 years of the mission. So in this case, we choose, this is quite, let's say, an optimistic trend with an increment of 2 tons of carbon per year and per hectare. So and this has been computed at 4 hectares to make it, let's say, possible, or we reach the limit. And of course, we can see here that with the tomographic scenario, it will be much easier, because here is the standard deviation for the tomography, and of course we have this total gap, which is much more precise. And of course, yes, this has to be put into perspective with a more realistic scenario of carbon sequestration evolution, which is maybe more like that, modulated with tree falls and so on. So yes, I think I'm running late. So with this, I conclude my talk. Thanks.
So thank you, Ludovic. We have time for maybe quick question. Yeah.
Thank you. Really great talk. I had a quick question about the radiative transfer model that you're using. And I was just curious as to whether that at any point is planned to be made open source and developed elsewhere, or yeah, the state that that's in.
Yes, I didn't mention that also the recent work are supported by ESA with the WeMax project, and the idea is to let's say better document the model and to make it available for the community. So yes, yeah.
Perfect. Yeah, thank you.
It's a matter, I think, of let's say 1 year or 1 year and a half.
Thank you very much. We should be moving on now with our next speaker. So Oliver McFarlane will be keeping the mic then. Welcome. We'll be talking about assessing the impact of canopy structure on modeled P-band radar backscatter for ESA biomass calibration and validation. That's more through. The floor is yours. Thank you.
Thank you. Thank you. Yeah, hello, my name's Oliver. I'm a PhD student at the University of Edinburgh, and I'm here representing both the university and the National Centre of Earth Observation in the UK. And I'm a part of quite a big group of people attached to this research, primarily led by colleagues in UCL, by Wenchen Yang and Matt Disney and Russell Thomas. And yeah, you can read the title, but we're trying to have a look and see how canopy structure influences P-band radar. So, as we know, it's very exciting to have P-band in space. Don't need to linger on that point too much, I think. But one of the key things that we are currently missing is how much of that backscatter, the magnitude of backscatter, is affected by structural variability, as much as it is other things like moisture. So when I say structural variability, there's quite a broad statement, but things along those lines would be sort of tree size and distribution of volume, both vertically, horizontally, and branching complexity. So the aim of this research was to do sort of exactly that, make a first effort to use terrestrial laser scanning, which has been lovingly introduced by several people today, and forest inventory data, along with a radiative transfer model to predict how various structures would influence P-band signals. And of course, this has quite a big implication for how the biomass algorithms would work and how we can better resolve some of the biases we may see across structural gradients. So where we looked at two main sites, one in Gabon and one in southern Angola. And these are 1 hectare plots. We had one in Gabon where TLS was taken alongside forest inventory information in 2022. And this, of course, is, as you'd imagine with Gabon, very dense tropical rainforest with lots of mixed layers. And then in Angola, by contrast, we had 4 plots, some of which I think they are geotrees plots of dry miombo woodland and savanna. So think more maybe 2 or 3 canopy layers and grasses as well. So low canopy cover and generally low biomass. And so the scans of those plots were taken in 2024, along with a long-standing forest inventory data set. So yeah, don't need to linger on this point too much, I don't think, but that's because Kim and Wouter did such great jobs. But to very broadly summarize, as you say, with TLS, the wealth of information you get from the point cloud is invaluable for some of these things, but depends on the extraction of individual trees and stands, segmentation of those, and the construction of these quantitative structural models where we assign geometries, and we can, of course, model volumes as a result. And here's an example from Angola, a lovely Juvenalia globifora with the QSM and the vertical distribution of volumes there. Yeah. By contrast, this is just a visual example of what that process goes from and to. And so this is from Gabon. This is what the plot looked like as a point cloud on the left-hand side, so a bit messier. and lots of information there. And then, of course, on the right-hand side is once we've got these geometries, it looks a little bit more sparse, but nonetheless, still very precise. So what we do with said TLS data, once we can sort of assign them a matched pair with the forest census, is we now have a species, a diameter, and all of these structural information according to branching and architectures and crowns, which we can feed into radiative transfer models. The model we used was Mimics, so it's been around for quite a while, late 70s. And as sort of described on the tin, it sort of predicts how a p-band or a given geometry would respond to p-band backscatter. Mimics has three mediums. It has the ground layer, trunk layer, and crown layer. And then within the crown layer, you can describe and parameterize these distributions of branches and volume distributions. So once we get out of that, we get these sort of, now of course I should preface that Mimics is a first order radiative transfer model, so it's not an exhaustive list of the scattering mechanisms involved. But one of the key findings we found was in Angola, at the very least, that some of these partitioning of volumes according to their vertical structure related to some of these scattering effects more strongly. And in Angola, the strongest sensitivity was in HH, and the proportion of trunk volume as a proportion of stand volume showed systematic negative correlations across all of the scattering mechanisms we looked at here. And yeah, and trunk volume itself showed the strongest correlation with direct crown scattering, sort of alluding to the fact that the bigger trees matter with p-band, which of course is not a surprise, but it's lovely to have a physically resolved estimate of that. And then, so the same results for Gabon, where sort of more strongly correlated in general. HH and VV were comparatively similar, but cross-pole exhibited slightly weaker correlation in total backscatter. And the strongest negative correlations were between ground-involving scattering mechanisms and tree volumetrics. Of course, with the greater penetration capability of p-band, having a stronger effect on sort of ground and double bounce scattering mechanisms. And the implication for this, as sort of by use of the contrast between Miombo woodlands and dense tropical rainforests, is that plot scale structures seem to be more important than individual tree structures, which is quite a key takeaway where, at times we think of how much individual species might differ. But for biomass, if we can accommodate for some structural wear calibration, that can seem to yield quite positive results for mediating that backscatter to biomass relationship. Beyond that, we also looked at another measure of structural complexity. Again, it's a difficult one to operationalize, but the team in UCL found quite promising results by using the surface area to volume ratio. So that being sort of a standard where if you've got a higher ratio, you're going to have more smaller things like branches and lower with larger things. And across both sites and all the plots, we found quite a strong relationship between the difference of surface area and volume to backscatter. And you can see here it's fairly consistent across sites. The simulations here were done with a constant soil moisture measurement. But yeah, it's a quite optimistic look about how multi-stemmed tree stands can have it doesn't seem to relate quite as strongly. And so how do we, of course, RT models are predictions, they're simulations, and so what we did was compare them to the closest available biomass data, and so that was also in Gabon. Although 200 kilometers away, it is nonetheless fairly consistent with the ecology, so dense tropical rainforest. And when we average across the 1B data to make sort of plot scale comparisons, we found that the distributions of observation roughly corresponded to the simulations we ran across different soil moisture metrics, which is quite promising to say that we're in the rough zone. And this is, of course, with only one radiative transfer model. Others may be yield different results. But yeah, and for the sake of argument and getting as much biomass data involved as possible, we ran the same sort of validation exercise with the data in Bolivia and Brazil. And while perhaps slightly less within range in Brazil, the distribution in Bolivia, same kind of tropical rainforest, did show to be with observational limits. So with that said, there's a fantastic initiative that also developed a pipeline involved in Python that can take terrestrial laser scanning data and feed this into radiative transfer models to make that quite efficient. And the team in UCL have been working on that for quite some time. And that will be all made available once the eventual paper is released, which is close to be doing. And so with this framework, what we can sort of understand a little bit or start the ball rolling is how structure or certain structural parameters mediate this P-band radar response in terms of magnitude of backscatter. And we found the stronger response seen in Gabon, which is sort of aligns with most theories, being that dense tropical forests and the penetration of radar has a slightly more, stronger response, while the negative correlation of backscatter with structural complexity, as expressed with surface area to volume, is also quite a positive result as to how we can go about calibrating some of these biomass models. But yes, this is sort of a first pass at trying to estimate how structure mediates the biomass backscatter relationship. So naturally, there's more work to be done. Various different forest types we're looking at the moment, as well as other environmental factors that might have a role to play. And ultimately, the team in Edinburgh are working on a deep learning approach to try and quantify the uncertainty and the bias in the biomass models from biomass, which I realize is a lot of biomass in a sentence. But yeah, I hope that last bit made sense. But otherwise, that's the end of my presentation, so thank you very much for listening.
Thank you very much, and thank you for keeping time. Are there questions? Yes, Aki. It's got a team effort.
Yeah, it's not a team effort. Yeah. Yeah, thanks for a very interesting presentation. I was just wondering, I mean, I understand your question about the radiative transfer model, kind of at the previous talk. It would seem to me, I mean, seeing this kind of incredible detail that you have from the terrestrial laser scanner, and then feeding it into like mimics, which is seems like a very crude model at this time. I mean, it seems like you would just be degrading your data. I mean, isn't it time to develop a new model? Or I don't know. I mean, it just seems, it's just a comment. I mean, it's not really a question. But is whether there would be a way to kind of make use of kind of TLS data much more efficiently than feeding into a model, a crude model like mimics.
Yeah, no, absolutely valid comment. I think that was part of the aim of this, was to sort of prove that if mimic still had any utility, I say any as though it does what it says on the tin. Yeah. What the interesting fact was that despite having, as you say, this wealth of TLS data, and mimics you can parameterize, I think, up to 5 or 6 branch orders. But if you run it by a stem or tree basis, you can actually maintain a lot of the complexity that would otherwise be removed if you averaged all the first branch orders across all the trees in a plot, particularly in a place like Gabon where you've got so many mixed layers. So it was definitely a thought, and it's a lovely segue into saying that the rest of my PhD is sort of trying to figure that out, and particularly with the higher order scattering mechanisms, which I think we're still missing a solid understanding on. But yeah, thank you for the comment.
Yeah, just another comment on one of your first slides. I mean, just when you showed the TLS plots over, I think it was Gabon, and you had like with and without leaves, it seems like. This one exactly. So how did you in the TLS, can you actually identify the foliage kind of separately and you can remove it like that? Or, because it's the same forest, right?
Yeah, same forest. Yeah, I can appreciate that visually it looks as though I've sort of cut all the leaves off.
Yeah.
But I'm sure Kim is probably sort of itching in his seat to make a comment here. But in general, a lot of the point cloud and segmentation can be done algorithmically. So yes, there's a degree to which some foliage is removed. And in our case, we were primarily focused on the branching geometries, more so than the foliage. But yeah, perhaps it's worth a chat with Kim afterwards to talk about the depths of keeping or putting foliage back in to QS.
Well, I mean, it would be invisible basically in P-band anyway. But,
yeah.
Yeah. Okay. Yeah. Thank you very much.
No worries.
Thank you. More questions? No more questions? If not, thank you again very much. Oh, there's one, sorry.
That's okay.
Thanks for the talk. And yes, just a question about terrain topography, because we know how important...
the what, sorry?
Terrain topography.
Yes. Yeah.
And usually with layer models, it's not that, I mean, of course, except in the case of an homogeneous slope, then it's quite challenging to model this. So how did you modify it into the Mimics model? Or?
Yeah, so Mimics, the closest we can get to that is surface roughness, more so than overall terrain, which of course is not a terrain model. But as you say, it is a simulation which takes quite a lot of assumptions on board, and one of which is this sort of terrain is not an immediate factor. But yeah, I think there's obviously more to be said about the role of terrain in that, in predicting P-band. Obviously, it's a very important factor. But yeah, I couldn't comment beyond that. I mean, Mimics is I'm afraid I'm constrained by what Mimics is at that point.
Fine.
Did that answer? Sorry, I don't know if that.
Yeah, no.
Yeah, perfect. Thank you.
But yes, to moderate this comment, yes, the very good point is that there is several orders, whereas for coherent models, can only simulate the first order interaction. So that's yes. That's why I think it's still worth to work on a radiative transfer model.
Yeah, no, I agree. Yeah, thank you.
All right, we need to thank again.
That's all right. Thank you very much.
Oliver, thank you. And moving on.
Okay, and the next presentation is given by Stéphane Mermoz from Globe EO Toulouse.
Thank you very much. Thank you everyone for the great organization. This is a great week. And I want to thank my co-authors from Globio in Toulouse, France, from INPE in São José dos Campos, no Brasil, in CESBio, Toulouse, France, CNES in France, and Isaïs Peiro in France. And I have to acknowledge that much of this work has been achieved by Juan Dobras Prieto and Marianne Reis from Globio and INPE. So, as you probably know, addressing degradation, forest degradation, is essential for regulating climate change, for biodiversity, for preserving ecosystem services, and so forth. But the extent of the area affected by forest degradation is a notable data gap, contrary to deforestation. The area extent of degradation exceeds that of deforestation, as shown in various papers. And more recently, it was shown that the degradation of tropical moist forest is greater than previously estimated. In this slide, this is an overview of tropical forest degradation drivers in the Amazon. In gray here, you have underlying drivers that stimulate actually disturbances that cause degradation in the Amazon forest. You have mainly timber extraction, which can be, for example, selective logging, but also other type of timber extraction, fire, of course, edge effects, and extreme drought. You have in red the impact of these degradations here and here. You have local impacts, and you have also other impacts, like, for example, the smoke that can impact cities and so on that are located far away from degradation. Here are some photos taken in the Amazon by Juan Doblas. You can see here the effects of understory fire, and it's how it looks like afterwards. Yeah, like a dieback of forest, just for illustration. So the post-perturbation recovery, the impact of recurrent degradation and net carbon loss due to degradation are still subject to active research. For example, in a part of a forest that is degraded, you could drop from 400 tons per hectare to 300 tons per hectare. So the technology we had until now is maybe not sufficient to detect such subtle changes. So in this talk, we wanted to check if there is a potential in the use of the biomass mission to evaluate the impact of forest degradation on tropical dense forest. This is the methodology we used. We used the biomass L1B data and DTER data from INPI. We processed our biomass L1B data using SNAP, the SNAP version 13.02 released 2 weeks ago. Actually, we sent email to the guy taking care of SNAP for him. Yeah. And we calibrated and auto-rectified data to get the process backscatter. And we transformed this backscatter into AGB, above ground biomass, using reference LiDAR-based AGB. We obtained estimated AGB that we used to perform an analysis with a selection of DTER polygons over not flat but not steepy slopes, and area greater than 0.25 hectare in order to try to assess the degradation onto biomass. So as I said, we use DTER as reference degradation data. So this is a great data set which is open to everyone. It provides high accuracy alerts from 2016 to 2025. It's based on the interpretation of seaburst and Amazonia 1 imagery. It's composed by fires, selective logging, and also other types of forest degradation. Actually, it should be called unidentified degradation, actually. And it provides spatiotemporal trends and recurrence of degradation events. You can see here the amount of alerts in square kilometers per year and per type of degradation. And here you can really see the potential impact of drought, of repetitive drought. You can see that there were much more fires in 2024. Maybe you remember that. Here is just a zoom to show you how it looks like, how the data looks like. This is in the Amazon. You have Sentinel-2 imagery in the background. You have fire in red here, and unidentified degradation in blue, and selective logging here. We selected our study sites based on the location of DTER data, and also based on the biomass acquisition. So you can see here the biomass acquisition by mid-January 2026, so the one we used. We didn't use all of them, but and these are the 4 study sites we selected. This table shows you the particularities of each study site. We have 2 study sites in Mato Grosso, and one in Pará State and one in Roraima State. Number 2 and number 3 are located in dense forest. Number 1 in open forest with transition to cerrado, and number 4 in dense forest and savanna. All of them are impacted by fires, and some of them are impacted by selective logging, drought, and so on. We processed the biomass data, as I said, using SNAP. We use the biomass data acquired between 25 November 2025 and 12 of January 2026. We checked the quality of the data. We retained 1,952 data sets, and we discarded 153 of them due to for different reasons. And we got, as you have seen in this week, the nice first biomass images. And then we started our analysis. So you can see here Sentinel-2 image. So it's really for illustration on this slide. Here you have the data degradation recurrence. So here in dark blue, for example, you have one degradation that occurred in the last 10 years. And then you can see in light blue, you have 2 occurrences and so on. And we saw that generally when we had more, more degradation events, like for example here, we had a lower backscatter corresponding to here, you see, which is actually completely logical, but we wanted to check if there was a potential for our analysis. And then what we want to check is the change in backscatter, the change in biomass due to this degradation event. So to do so, we selected reference undisturbed areas. We made the assumption that biomass before degradation events was equivalent to AGB in surrounding undisturbed areas, which in our opinion makes sense. And we selected 3 handpicked undisturbed area per study sites, large one. And we use other data or optical imagery to ensure that there wasn't any human-induced perturbation or deforestation affecting the reference areas. So this is our reference. And then to go from backscatter to AGB, we use as reference a LiDAR-based AGB maps processed by Nicolas Labrière and Jérôme Chave, data from the Sustainable Landscape Brazil. And Nicolas Labrière, he converted a tree inventory data into 625 plot level biomass estimates, ranging from 0.16 hectare to 1 hectare. And then he derived a power law between plot AGB and LiDAR-derived height. And he applied this model to the LiDAR footprints to produce AGB maps. And we used 65 of them in our study at 100-meter pixel size. We didn't have time. He also produced the uncertainties, but we didn't have time to investigate this. And these are the first correlations between LiDAR-based AGB and biomass backscatter we got. You have the 4 polarization, HV, VH, and VV. And in HV and VH, we had a R square of 0.22 and 0.23. And what was really striking to us is that, I mean, of course, there is a correlation, and on top of that, it looks really similar to what TREE showed in the biomass report for mission selection in 2012. I don't know if some of you remember, but she showed this, right? And we have really a similar slope. I didn't have time to make a nice figure to superpose all these curves all together, but in both figure here and at VH, between 100 and 300 tons per hectare, we have an increase of approximately 2 dB. So there is, I mean, we were really surprised to have such similar results. Of course, we are more biased, but it's normal because we use LiDAR-based AGB, which is really nice, but it's not like biomass plots measured on the ground with slope correction and better estimates on the ground for sure. And of course, it's a first attempt, so we didn't perform any slope correction yet in our biomass data, no ground notch yet, no tomosar yet. So when we will use all this, we will have even much greater results. So we really think that there is a great potential using the biomass data. And it's, I found that it's kind of in line with what people showed this morning, like Mihai Bazaev or Maciej. And of course, at the LiDAR plot scale, of course, we have much less bias. You can see here with a green dots, the green dots. Here is exactly the same thing, but with the model we are used to, the log model we are used to see in the community. And once again, I show what we showed in 2012, and once again, it's very similar. We are also more biased, but still, it's kind of similar. And once again, when we average the LiDAR plot scale, we have even less biased and a better model. So we we inverted this model to estimate biomass in the images we processed. So in this graph, you have in the x-axis the number of degradation events from 1 to 5 from 2016, and you have in the y-axis the VH backscatter, the VH change actually, relative to our reference area in intact forest that I showed purely. And we got these results. You have the results in the 4 study sites, in red fire, in green unidentified degradation, and in blue selective logging. And we observe, I mean, it was interesting because it was the first time we used the biomass data, right? And we observed a loss of backscatter related to the number of degradation events. We didn't observe that in all the cases, but still we got a kind of logical result. And this is normal because the severity of disturbance often increases with the number of disturbance events. And we had different results over the different areas because each degradation type is driven by distinct factors related to the area where they are located. And what can we say? We also can say that selective logging showed much more subtle changes than in the case of fire and unidentified degradation, which is actually completely normal. So we really could see this decrease in VH with the number of degradation events. This is exactly the same thing, but with biomass on the y-axis, the biomass we estimated with our model. And the results we found are in line with what is written in the literature. For example, in Lapola 2023, who compiled the result from many previous studies, showed that repeated disturbances are often associated with high losses of carbon. And she also provided some figures, for example, saying that, for example, carbon losses in log forest are highly variable and range from 4% to 35%. It's, for example, in this area, in line with what we found. And in some areas, we had, on the contrary, an increase of backscatter and of biomass for selective logging. So we should investigate further. Of course, these are some first results we got recently. And this is almost the last slide. So we did the same thing, but this time we put the number of events here, 1, 2, 3, 4 events, okay, for the lines. And in the x-axis, we put the years from last degradation. And it's like interesting. You can see that after, for example, 1 fire event, let's say in area 1, you have just after the fire a drop of backscatter from 100% to a drop of AGB to 75%. Then and kind of stability during the first years, and then it drops. And in some other areas, we are also other behaviors. So, I mean, these are logical results, but in the literature, we found many things, different things. For example, Sato et al. Said that AGB strongly decreased due to fire during less than 3 years and then increase again. So it's not really what we found here. Here it increases again, but after 5 years. So. And according to Barlow, AGB decreases more 3 years after the fire than 1 year due to mortality. So we have to investigate more these results. And the last slide, this time we selected we selected only areas where which were unburnt, and then we tried to assess the selective logging and unidentified degradation, and knowing that biomass recovery for selective logging are correlated to the volume of wood extracted, so that we don't have in this study. So we need more in situ data. As a conclusion, as I said, the biomass backscatter reveals the same sensitivity to biomass as the P-borne airborne campaign, which was very interesting. These are first promising attempts without any slope correction, ground notch, Tomosar, and so on, so we will get some better results, which is nice. And we could see the long-term effect, of fire over forest structure, but it needs some further investigation. And we think that the biomass mission has potential to evaluate the impact of forest degradation on tropical dense forest. Thank you very much.
Thank you, Stefan. Are there any questions?
Yes, I could, yeah.
There we go. Yeah, thank you. Yeah, very, very interesting and very nice to see Thuys' kind of predictions coming into kind of reality 13 years later. It's yeah, fantastic. I was just wondering, I mean, selective logging, that is, of course, you can expect. I mean, it's a gradient from kind of no selective logging down to complete deforestation, right? So that you have a clear relationship between the volume taken out is kind of very much to be expected. I was just wondering, I mean, one thing that we have realized very much in L-band is that right after logging, you have a lot of timber just lying on the ground, which kind of actually produces an increase in the backscatter initially before it's kind of taken away. I'm not sure. I mean, it's you have had that kind of in your images here, but I mean, that would also be something to take into account, right? I mean, the first year or two after after kind of the event. I mean, you cannot expect perhaps. There must be some kind of non-linearity in there, right?
Yes, I agree with you. I mean, especially as you said, right after the biomass acquisition. Yeah, and we have to take care of that. Yeah, I agree with you. I'm not sure how much time this remains on the ground and so on. But I fully agree with you. Yeah, and yeah. Say,
I think it's a matter of months, not years. But generally, I mean, quite often they deforest during the rainy season, but they take out the timber during the dry season, right? So
yeah, so we have to take care with the first year of But we still have the second and third years to. I mean, in the literature, we often found a reference to the first years, but we found also interesting to see. For the years until 7, 8, 9 years. Yeah.
Thank you.
Thank you, Eike.
If one urgent question, then let's move on. And thank you again.
Thank you.
Our next talk is given by Xiwan Wang. The title is A Large-Scale Vegetation, Atmosphere Dynamics and Interaction. Xiwan, it's yours.
Thank you. Hello, everyone. I'm Xiwan Wang. I'm doing my PhD in Max Planck Institute for Biogeochemistry. Today, I have 35 slides. Let's see if I can finish within 20 minutes. So today I'm standing in for our team's work on large-scale vegetation atmosphere dynamics. So this presentation synthesized two key studies and focusing on how we use Earth's observation data to constrain land and atmosphere interaction. Land ecosystems absorb 20 to 30% of CO2 annually, and this carbon absorption is mediated by the photosynthesis of vegetation, and the carbon stored in biomass results from carbon uptake of photosynthesis and also released through processes such as respiration, disturbance, and mortality. So the land carbon dynamics shape and are shaped by dynamics in CO2. Quantifying the biomass CO2 sensitivity is central for understanding the past and projecting the future carbon cycle dynamics. So I think we can use this conceptual diagram to better understand the processes. So this blue flow illustrates how carbon enters the land ecosystem. So the vegetation absorbs carbon dioxide from the atmosphere and gross primary productivity, GPP, and GPP minus respiration as MPP, and MPP, which is located to different plant parts, accumulating as a above-ground biomass. And this mechanism led us our first study, that is how does the CO2 fertilization quantitatively affect this above-ground biomass dynamics in the long term. And the red flow, you can see, shows how the carbon returned back to the atmosphere. So this includes respiration, but also through turnover and mortality. Crucially, these processes are not always immediate. So this observation raises our second question, which is how do changes in above-ground biomass shape the interannual variability of CO2? So to answer those questions and to study the biomass and CO2 interactions, it is essential to investigate biomass patterns and dynamics, which at global scale have been mostly done using Earth observations and different modeling approaches. Several studies have been conducted based on the vegetation biomass data. Historically, such data relies on simple empirical relationships, so which has a regional single-year products. In the recent years, with development of Earth observation, machine learning algorithm, and artificial intelligence technology, we have several of those multiple long-term global vegetation biomass datasets. And in our study here, we focus on two global longest datasets, which covered most of the period we're interested in. So one dataset is biomass cut, and which leverage the seabed scale meter observations and satellite LiDAR data from the range 1992 to 2018 with a quarter-degree resolution. And another dataset from GPL dataset, it integrates the machine learning with modest optical data and airborne LiDAR, offering higher spatial detail with 0.1 degree resolution from 2000 to 2019. So we utilize these two independent global biomass products to ensure the robustness and to minimize the sensor specific biases. And in parallel, biomass and CO2 interactions has also been mostly investigated via the modeling approaches. So here we make use two different state-of-the-art modeling frameworks used in the Global Carbon Project and IPCC assessment to systematically separate the impact of CO2 from climate and land use change. We used 14 dynamic global vegetation models, which relied in the offline no coupling on the factorial simulation experiments. As for the CMIP family models, we use this particularly use this CMIP 6.1 PCT CO2 BGC scenario to isolate the CO2 impact from the climate. So based on those datasets and model results, we target our first question, which is how does the long-term CO2 fertilization affect on the biomass? So back to our conceptual diagram, we develop an approach to quantify the contribution of CO2 to changes in vegetation carbon stocks. And the previous, there are extensive research and explored the CO2 effects on biomass using different methods ranging from the local level to a large-scale forest inventory level. And some of those inventory-based studies have already achieved global coverage, which highlighted here as a red mark. But despite these efforts, there is a significant uncertainty remain, and seen in this wide range, widespread of the observational estimates, and this massive divergence in model projection on the future CO2 scenarios. To address these discrepancies, our study quantities the global effects of CO2 on biomass by combining the satellite-based observations together with model simulation. And we apply two methods to separate the CO2 effect on biomass. The first method is local multiple regression method. We assume the local spatial sensitivity of biomass to factors other than CO2, for instance, climate and land use change, the nitrogen deposition equals to the temporal sensitivity, and establish a regression model within a 3x3 moving window to isolate the CO2 effects. And the second approach is a residual method. We assume that biomass has equal sensitivity to climate in both the long term and short term. So basically, we firstly in the region influenced only by the CO2 and the climate. So there's no impact from the land use change or the nitrogen. We calculate the climate impact and extract it from the total, and the remaining residue is the CO2 influence. Then we employ these machine learning models to extend this globally to have a parameter beta to represent to quantify the CO2 effect on biomass. So this is results from the first approach, the local multiple regression from each of the 14 trendy models. As you can roughly see, at large scale, the spatial patterns correlate very well with true CO2 effect, which is the trendy S1 simulation. And we have the same spatial pattern or same results for the residual method. And if we see the numbers, we see the residual method has slightly higher R-square value and lower RMSE. Not lower, it's just basically the same. And firstly, those two methods confirm both those methods can explain the global effects across different models, and moreover, both methods reproduce the variation in CO2 effects across different biomes, as shown in the lower panel. So overall, we are confident to apply this approach with the realistic biomass datasets, which in our case, biomass cut and GPL dataset. So this is a CO2 effect derived from the satellite data. Once we contrast the method and the different data sources, we observe a stronger agreement within dataset across methods and across datasets. So this is similar to the result from models. So this is reflecting that methodological differences are much less relevant than differences between the data sources. So if we take this observational based estimates of CO2 effect on biomass, including the uncertainty, we can see a tight constraint marked in this black line together with the gray shaded area showing the uncertainty. And when compared to the model variations, it's much less. So the trendy results is similar to the observation-based value or number, but however, CMA5 and CMA6 underestimates the CO2 effects with the number of 12.7 and 13.2 compared to the observation-based 16.5. And we also find that the Earth system models underestimation of CO2 effects in biomass can further lead to underestimation of land carbon sinks. So in total, we found the number that is global land carbon sink would increase 3.9 per 100 ppm CO2 if all other factors not change. So this conclusion is independent on other climate and disturbance factors, as well as the rules that the biomass itself has in shaping the CO2 concentration, which led to our second study. How do change of biomass affect to the interannual variability of CO2? And looking back at our conceptual diagram, now we are looking at the red flow, how do change of biomass shape the interannual variability of CO2. And so the question is, does the long-living biomass directly released into the atmosphere? If we look at how model make this link between changes of biomass and CO2, this should be a rather direct relationship, which is most models support this hypothesis, which is high the non-living biomass can immediately release CO2 to the atmosphere. We can see the correlation between the changes of biomass and MBP has a very high correlation. And however, when we directly use this assumption one to estimate the carbon growth, the CO2 growth rate, which is CGR, for some period we see a good agreement between the data, but in general there is a very poor correlation, and some period there is a strong overestimation. So one of the reasons for this overestimating could be that in reality, as shown in this figure, there are dead trees don't necessarily convert into a flux to the atmosphere within 1 year, since they will not, which means they will not decompose immediately. And we caught those stored carbon in the coarse wood debris, and it takes time to decompose before released into the atmosphere. And this takes us to our second assumption, which is we develop a second model, include another two pools. One is a coarse woody debris pool, another is a soil organic carbon pool. So this is a simple first order kinetic model. It will parameterize based on the observed decomposition rates and turnover time. We can build this model to simulate the carbon biomass loss flows into a coarse wood debris pool, and then later into a soil organic pool via the decomposition rates, transfer the lagged flux of carbon into the atmosphere. And we can see the results. This compared to the CGR data, we see the variability is much dampened compared to the assumption one. So mainly this is because we ignored the fast carbon turnover processes. And so naturally, learning from the assumption one, assumption two, we realize a simple model considering both these fast and slow carbon turnover processes. But those processes still driven by biomass observations and constrained by other observations. In details, we can see we ended the fast decomposition liter and the fine root pools. And we also end logging and human use of woody products. And we also consider the effect of fire in different pools, including the wood burning, the CW burning, and the soil organic burning. And with this, we can see the results of this assumption three. By these three pools, we consider both the fast and slow carbon turnover processes in the leaf vegetation, CWD, and soil organic carbon pools can reproduce 62% of observed variability in the CO2, in the CGR. And then we partition the contribution of the net carbon exchange or the net carbon flux in the leaf vegetation pool and the non-living vegetation pool, and the immediate carbon release and the lagged carbon release. We can see in total the land contribute 57% of contribution to the CGR, and showing in the green bar. But for the immediate effects, it's only 17%, and for the lagged effect, it's 40%, which is 2 times than the immediate effect. So this highlights that the large amount of long-living carbon introduced by disturbance, except for fire, can be retained in the terrestrial ecosystem. In summary, we have found a strong CO2 effects in the potential above-ground biomass and the land carbon sinks. And we also find the large non-living carbon do not directly release. And in terms of the outlook, we are shifting from the simply monitoring biomass to using the EU data to uncover the hidden rules of how vegetation and atmosphere interacts. So these rules maybe challenge our current assumption in the current models. In our case, the underestimation of carbon helps plant grow, and how important the dead wood is for storing and releasing carbon. And the upcoming biomass mission will provide a deeper and sharper views of dense forest, especially in tropic, allowing us to fix the biases and detect even smaller carbon losses from disturbance. And with that, I want to thank you. And
thank you. Thank you very much. There is one quick question. It's getting late in the day.
Maybe I can ask. So how actually do you use now the radar data? You use it to estimate biomass. And can you also use it another way, like as a other?
So basically,
like for example, tomocubes from biomass, maybe they can be used in your method.
We basically use two different biomass data sets. One is this biomass cut, another the GPL. And yeah, so if I understand your question correctly, sorry, it's too far from the here. Yes. So the reason of having these two different biomass products is because we want to ensure the robustness and minimize the sensor-specific biases. But you can see the current resolution of this two data sets is still not very high, and we are looking for the higher resolution. And yeah.
Okay, and would, for example, the tomographic profiles from biomass help you to improve the method?
Not sure about this, but I will.
Okay, thank you.
Thank you.
So. Okay, and the last presentation of today's will be given by Shu Shan from Max Planck. The presentation is called Constraining Turnover Processes in Terrestrial Biosphere Model by Using LP Band Backscatter.
Good afternoon, everyone. I'm Shu Shan from Max Planck Institute for Biogeochemistry Chemistry. Today I'm going to talk about our research about how to use long wavelengths like L band and P band backscatter to constrain the turnover processes in the terrestrial biospheres model. So as Sven just shows that the model forecast the land terrestrial biosphere model forecast for the vegetation biomass or the land sink has a very large uncertainty in the future 100 years. If we decompose the biomass balance between to the carbon input flux and the carbon output flux, we can see a totally different uncertainty contributions. For the carbon input, it's more about the net primary production, which is GPP, the photosynthetic input minus the respiration. And for output, it's how carbon leaves the forest by leaf shedding and also some mortality and also disturbances like fire, bark beetles. And this process can be simply parameterized by one parameter like the vegetation carbon residence time or turnover time. It just means the average time the carbon is stored in plant before it is released. And we can see that this parameter contributes a large part of the uncertainty. Both of the magnitude and also the sign, the direction are very diverse within this model ensembles. However, for MPP, the model is quite consistent about the direction and also more about the direction than the magnitude. So this raises a question to how to quantify or improve the modeling about this carbon turnover time or turnover processes. If we write it as an equation, only a simple equation, the temporal changes in the carbon, for example, in 1 year or in 1 month, is equal to the annually or monthly MPP minus the carbon divided by minus the carbon state, the amount of carbon divided by this turnover time. And our another research question would be, how could we use the newly launched satellites like the Biomass, or NISAR, which provides long wavelength backscatter to help to constrain this parameter tau. For the newly launched satellite from ESA or NASA, the L-band and P-band from the SAR provides insights to the canopy water content. For example, this figure comes from one preprint manuscript from the Boreal Scout campaign, and the x-axis shows the evapotranspiration from the canopy, and the y-axis shows the temporal change of the P-band HH canopy backscatter. We could see a clear negative correlation between these two variables, which means that if the canopies lose water, for example, the evapotranspiration is very large, then the delta of the P-band backscatter would also be large. So this gives us the insights or idea that we may could use the P-band or L-band backscatter to help to model the plant health or to constrain mortality processes about the leaf or stem water content, for example, the hydraulic failure due to the drought or heat waves. So our experimental setup is to design different models to see how the backscatter helps to constrain the model, and also what is the added value of the simulating of the plant water content. We start from two benchmark models, which coming from LPG gas and also CASA, which simulates the GBP, phenology, carbon dynamics, and saltwater cycle, and also evapotranspiration, but in two different time scales. One is daily, and another one is hourly. And then we try to add a sub-scheme about the plant water scheme, plant water dynamics, and also two different water using efficiency strategies. And in the final experiment, we try to add the Allos Pulsar 1 backscatter into the constraints. Because right now the Biomass doesn't provide so long time series about the P-band backscatter, so we would start from the Allos Pulsar 1. And only few set simulations are available, and the other sets are still running. For the specific model setup, the first line has already been talked in the previous slides, and which is just to model the dynamics of the carbon in the leaf, stem, root in the different pools. And we add a similar equations to simulate the water storage rather than the carbon storage from the flow in and flow out. And for root, it's root water uptake. For leaf, it's transpiration out to the atmosphere. And in another module, we simulate the backscatter from the water parts. The total, it's a very simple water cloud model. It's decomposed into solid backscatter and also the vegetation backscatter. And for the vegetation and also attenuation term, we linked the microwave signals to the water content rather than the above ground biomass here. And however, in our model, we have an internal link between the water content and also the carbon content by the water potential, which is the relative water content, and also the maximum of the water content and the capacitance. Some of the parameters like the surface soil moisture come from the SMAP Kava experiments, and other ones are released as the optimization during the inversion experiment. And we plan to run the experiments in the fluxness sites globally, and we pick up the sites if they have the measurements and forcing data within the Allos Pulsar period. And for the model data integration, we consider the constraints like the carbon fluxes, like GPPNE and the respiration, and also water fluxes like evapotranspiration, and also some carbon state variables. And we try to optimize the cost with a balance to the prior defined parameters. And we could also calculate the posterior uncertainty matrix based on the optimized parameter vector. For the results, here we only show the results about the experiments with the first four model experiments, because Allos Pulsar 1 we are still running. The most obvious one is that the daily model coming from LPG gas and CASA obviously overestimates the above ground biomass compared to other three hourly experiments. However, it performs best in the GPP one. And another feature of this figure is that all of these experiments cannot behave better in the evergreen broadleaf forest compared to other ones. And this PFT contains the French Guiana and also other sites which are very hard for our model to simulate. And another result is about the simulation and observation between the model and also the simulation from the model and the observation about the plant hydraulics. Here we show the stem step flow. The observation of the step flow comes from the step fluxnet, and the observation of the evapotranspiration comes from the fluxnet. And all of these figures are normalized to the maximum and minimum value of the variables in this month. And we show the diurnal cycle varying with different months. We could see that there's a small lag between stem step flow and also the evapotranspiration, and our model could reproduce this small lag. And if we add the allose pulsar as an additional constraint, it helps to model this later lag of this water cycle. And we could also quantify the reduction of the parameter uncertainty, because the model data integration or data simulation is aiming at to reduce the uncertainty. This figure, the y-axis shows the relative reduction of the uncertainty, which is the prior minus the posterior divided by the prior. And the first block shows the parameters about the plant hydraulics model, and the red block shows the parameter about the background turnover, including the background turnover rate and also the leaf shedding rate. A large value in the y-axis shows more reduction in the parameter uncertainty. And for the first block, we noticed that for the plant hydraulics parameters, both of these two experiments didn't help to constrain so much. Only two parameters shows a sensible reduction, which tells us if only using the evapotranspiration and GBP to constrain the plant hydraulic models, it could just model fitting and without constraining the parameter uncertainty. So this calls for some more sub-daily microwave measurements, like the tower-based L-band or P-band data, or maybe from future ESA mission like Atlanta. And for the second model, which is about the turnover process in our model, we could see that the daily model reduced less uncertainty compared to the 3-hourly one. And among these 3-hourly one, if we add the plant hydraulics, it helps to constrain more about the uncertainty of the background of wood and also background turnover of wood and also background turnover of the leaf. Some preliminary explanation may consider about the plant hydraulics give us a totally new GBP, new stress function or new stress response between the GBP and the surface on moisture. So our takeaway message is that the first one is that different model structures achieve similar performances. However, the daily model gives the worst estimation on the above ground biomass and give the best performance in the GBP and the evapotranspiration. The second one is that different model structures help to reduce model parameters in a different way. If we add plant hydraulics, we could reduce more uncertainty about the background turnover. The third one is that for some sites, if we add the microwave backscatter and additional constraint, we could help to constrain the diurnal cycle of the evapotranspiration and the stem step flow. However, this is weakly consistent among all of the sites which we have the measurements of step flow and also the fluxnet measurements, because for allose pulsar, the best situation is that we only have 20 or 30 measurements per year, which just help to reduce uncertainty of the parameter rather than to improve the diurnal cycle, because we don't have so much large data density for to modeling a whole diurnal cycle. That's all. Thanks.
Thank you, Shu. Are there any questions? Yeah.
It's a very interesting study, and you show that when you use this backscatter to assimilate into the model, you can improve the model performance in this turnover time, right? So what's the mechanism between that? Because your calibration is yeah, it's based, your model is at hourly scale, and you also show that actually for the daily scale, maybe the improvement is much larger for your take-home message. So I just wonder what's the mechanism between that, behind that, sorry. Yeah, behind that when I'm using this, because satellite normally we don't have so high frequency observations.
Yes, I think the first point is that some plant hydraulics model simulates daily simulation, like the only pre-down leaf water potential. They don't have a downward cycle, because for the leaf water, I don't mean that signal or daily cycle is not important, but the daily cycle is also very important to model, because the backscatter, for example, the ERS 1 or 2 or ASCAT, the C-band backscatter could have 1 to 2 decibel or much larger decibels within the one downward cycle. And the ALOS parser provides the exact hour or minutes about the measurements, about the signal of the SAR. So we think that if we just simulate it into the model, maybe this 1 to 2 decibel could be an error source about the model data integration. So that's our motivation to develop an hourly model first, and then to integrate the ALOS parser data into it. Yeah.
Any other questions? You said that in your presentation you were mostly using L-band, right?
Yes.
But you also said something about P-band. So when does P-band come in play?
That's a good question. We are conducting some PIs for some tower observations about the P-band, because they provide like the 30 minutes or 10 minutes observations of the P-band backscatter. And all of the data and model are there we can want, but the dendrometer and step flow data are still not in their place where they should be. So we are still waiting for the dendrometer data and also step flux data to validate it. That's why we didn't show it here.
Okay, thank you. Then, thank you again. So this was the last presentation, and I guess the next thing in the program is the city tour. So see you there. Thank you.